Fully audible. Quick. Welcome back, dosto. Welcome back. We are live. Great. All right. So we are live, and today we are going to talk about physics board exam, physics boards marathon. Your physics exam is going to be on 21st Feb, right? So you have got today, half of today, and then you have got 19 and 20, right? So today what we are going to do is we are going to complete each and every chapter's derivations, important topics, important notes, as well as previous year questions, right? So please note this thing that we are going to talk about the only most important. I'm not going to teach each and everything, but in a way we are going to try that we cover the maximum syllabus. How? Few things I'm going to teach you theoretically, derivations and all of those things, and the other types of things will get covered through previous year questions, right? How long is this lecture? We never ask this. We never ask how long is marathon going to be. It will depend on what? On whatever we have learned, right? So our motive is to complete class 12th today. So duration, we are not going to time this marathon. We are going to say we are going to complete this marathon as we are going to complete our course. Hi everyone. Hi everyone from Yakin batch. Hi Sahana. What are the things we are going to do on this? I have already explained. We are going to do derivations, important definitions, notes, concepts, each and everything, right? Good. Well, my name is Subrat Sharma. All right. Hi everyone. Welcome back. Hindi, so one more information. This is a pure English medium channel. So deliberately we all are speaking in English, right? It's not like we don't want to talk in Hindi or I don't know Hindi, but this is PW English medium channel, and we have got many good and other channels for Hindi. So this is specifically for English. All right, good evening everyone. So you all know we are going to start our class with electric charges and fields, right? Quite an easy topic. Don't give this topic a lot of time, because usually I have seen that if you like a certain chapter, you tend to solve more and more problems from it, right? It will not matter. Why it will not matter? The thing is that for you 1 marks holds the same value, whether it is coming from dual nature or it is coming from electric charges and fields, right? Got it? Done? Yes, we are going to complete physics today. Chalo, let's start. Quick. First of all, as I have told you, we are going to talk about only the very important topic. When we talk about electric charges and fields, we usually start our concepts with the definition of charge. What do you mean by charge? What are the different types of charges? I'm not going to go into all of those things. I hope you know these stuff, right? But I'll suggest you to actually please remember the properties of charge. That it is a scalar quantity. If it is a scalar quantity, we can actually simply add them, right? It is a scalar quantity. Next, conservation of charge is actually very important. And also in today's class, we are going to talk about this thing. We are going to discuss one of the past year question from this topic. Now, whenever you will have conservation of charge, it basically means that the total charge of an isolated system is constant, right? Other than that, positive charges, negative charges, you know all of those things. Not going to repeat it, not going to waste your time 3 days before your exam, right? So we are going to talk about only the very important things. So conservation of charge is very important. It basically means Q total is going to be constant. What types of questions you are going to get? You are going to get questions like you have got like 2 or 3 bodies over here, and they have been touched. So they had initially they had some charges, right? Like Q1, Q2, Q3. Initially they had some charges Q1, Q2 and Q3. And after, when we touch it, there will be a charge distribution, charge redistribution. So we basically we are basically trying to say that Q1 plus Q2 plus Q3 will be actually constant. Now whatever is question, whatever they are talking about it, we are going to discuss it, right? Acha, this question is actually quite interesting. Why all physics teachers are bodybuilders? So today I'm not going to talk about this, but yes, I have also seen it. In fact, my own teacher was, my own physics teacher was also, he liked gym. Okay, now enough. Hindi, I cannot speak in Hindi. This is the last time I'll speak in Hindi in this class. बच्चों अभी अपन इस बैच में नहीं बात कर सकते हैं हिंदी में, क्योंकि ये प्योर इंग्लिश मीडियम का बैच है, ठीक है? All right. So that was all Hindi for today's class. Now please let's move. Let's move quickly. Let's move. So when we are going to talk about charge in electrostatics, basically always charge is going to be at rest. This is also a very fundamental concept. So you are going to again and again use this concept here and there, right? So in electrostatics, charges are always going to be at rest, right? Next is, you all know that the very most important thing, the very first important thing from this chapter is actually Coulomb's law. Coulomb's law, whenever we are going to talk about Coulomb's law, we are going to talk about Coulomb's law in vector form. But first of all, let me quickly explain what Coulomb's law is in scalar form. So if you have got two charges, let's suppose you have got charges Q1 and Q2 at a distance of d, then the force which will act in between of them, the direction will is going to be known by the signs of these charges, but the magnitude of the force will be directly proportional to the product of these charges and inversely proportional to the square of them, right? And the proportionality constants comes out to be K, which is 1 upon 4 pi epsilon naught, whose value is 9 into 10 to the power 9 Newton meter square per Coulomb square, right? And where epsilon naught is known as the permittivity of free space. Please go through the units, dimensions of each one of them. But we are more inclined towards the vector form of Coulomb's law. So let's understand how you are going to actually write down the vector form. So whenever we are going to talk about any sort of vector quantity and you are going to derive it, it has to be in vector form, right? Got it? Done. Now the next thing is, when we are going to talk about, these are obviously your normal x and y axis, right? You can draw the third axis as well, but there is no need. So let's suppose I have got a charge over here. Let's suppose, my dear friends, we have got a charge over here and this charge is Q1. This charge is Q1. So whenever I am going to talk about any charge in space, now I am going to also talk about its position vector. So R1 is actually known as the position vector of charge Q1. All right. And similarly, let's suppose I've got another charge Q2 somewhere over here. And now, because we are talking about the vector form, let me say that they both are positive, right? We are assuming that they both are like charges, something like this. Okay. Acha, hopefully everyone's comfortable with the concept of position vector. Position vector R1 basically means x1 I cap, x2 j cap, x1 I cap, y1 j cap, z1 k cap for this particular charge, right? So if you are going to say, okay, what this distance is going to be, what is going to be the length of this path, let's suppose it is actually mod r. But if you are going to use your normal vector addition, you are going to say, if I am going to actually add r1 vector with this vector, let me call this vector as vector r. This is also known as displacement vector. So I can say that r1 plus r vector will be actually equals to r2 vector. See, I have done nothing but I have just used normal vector addition. All right, done. Everything's clear till this point. Now, if they both are positive in nature, both the charges are positive in nature, they are going to repel. They are going to repel, and we are going to draw these forces. This is force on charge 2 due to charge 1. This is force on charge 1 due to charge 2. Right? Now, let's come back and let's discuss how to write these things in board exam. Right? Along with going, we are going really fast, but please let's understand how you are going to write it down. please, whenever you feel necessary, please write down everything, right? Like for example, is for this R1 and R2, I'm not suggesting that this is a very important topic, but you may expect question like this. So please say that R1 is the position vector of Q1, R2 is the position vector of Q2. Now according to triangle's law, in very briefly, right? I don't want you to actually explain anything else. So just write it down. So that means this position vector is going to be this this displacement vector is going to be R2 minus R1, right? So this is an important thing for you. Now if someone says you to write down these forces, let's suppose someone says you to write down this F21, so you are going to write KQ2 Q1 divided by let's say the distance is R square times unit vector R cap. Please try to understand how we have written it, right? You can also write it as R21. Also, you can write it. Now, what could be the another form? So, this is the magnitude of the force and this is the position vector. Now, again, we know one thing, that any vector quantity can be written as magnitude times unit vector, which basically means, magnitude, I'll actually write it as any vector quantity A is written as magnitude, and this is absolutely correct, right? So if I want to write a unit vector, I'll simply write A vector divided by mod A. So can we use it? So you can have another equation over here. So we'll simply write F21 is equals to K Q1 Q2 upon, now please understand, R cap can be written as R vector divided by mod. So we have already got mod over here, so it will become R cube. So that's it, right? Other than this, please understand, I'm not writing each and everything for you, but you will have to write it down. Don't start the derivation something like this. Please define what is F21. So you are going to, before writing F21, this is, you are going to write it down something like this is force on charge Q2, force on Q2 by Q1. All right, done. Hopefully everything's clear. Also, one very important thing, like every other pair of forces, Coulomb's force or electrostatics force also follows the Newton's third law. So that means force acting on 1 due to 2 will be actually equals to negative times of force acting on 2 due to 1. Quickly write it down, dear friends. Is it all good? Quick. Everything's clear? AC important topics, when we are going to reach to AC now, we'll talk about it. Don't worry. Let's first quickly cover these chapters in order. All right. Let's cover each and every chapter in order. Quickly tell me if everything's clear till this point. Acha, what type of questions can you expect from this particular topic? Na? Let me also explain some questions. Let's talk about this one. Acha, this is Coulomb's law in addition to principle of superposition, right? So I'll explain principle of superpositions along with it. The question is saying, acha, by the way, this is from last year 2024. The question is saying 4 point charges, 1 microcoulomb, -2 microcoulomb, 1 microcoulomb and -2 microcoulomb are placed at the corners of an ABCD respectively of a square. So we have got a square. Let's draw it something like this, right? So we have got points A, B, C, D, right? If you remember, we actually uploaded one more video in which I actually listed all the important topics. So for all the students who are talking about, what are the important topics, sir, important topics for alternating current, please keep calm, right? I have already uploaded a video for all of you. You can watch that video later. Let's first talk about these things. Now, in that video, I have told you that this is actually one of the most important thing from electric charges and fields. They are saying that we have got 4 charges. Let's suppose that this is actually 1 microcoulomb. This is -2 microcoulomb. This is again 1 microcoulomb. and minus 2 microcoulomb, right? Then they are saying find the net force acting on the charge of 4 microcoulomb at the center of the square. So center of the square basically means that they are saying find out the net force at this particular point. At this particular point, right? This could be any charge. Right now they are saying that this charge is actually Q, which is equals to 4 microcoulomb. So it is positive. Now please try to understand how we are going to write down the forces. This is the same way you should also write it down. Let's start with charge kept at A. This is also positive. This is also positive. It's going to repel, and we are going to write this force as force on this charge by A. So this is FA. Got it? Quickly let's do it, dosto. Similarly, we are going to write force due to C as something like this. So we are going to write this is force on this charge due to C. Then because of D, it's going to actually attract. So we are going to write this is force due to D. And next, this is also going to attract. So this will be force due to B. Now, that's it. Almost you have got your answer. You already know it. But again, please don't get excited. Please don't jump to the next question by simply writing that the net force is 0. At least write 2 or 3 lines, right? Okay. So communication is very important for boards too. So the thing is, we are going to say that FA, magnitude of FA is equals to the magnitude of FC, and hence net force will be 0 for A and C. Please write it down by yourself, right? Similarly, or you can also write one thing, that all the forces are cancelling out each other, and hence the net force on the charge kept at center will be 0, right? Similarly, force FD is actually equals to force on FB, right? So very simple. I know, quite an easy one. What they could have actually said, what they could have actually asked is, they could have asked the net force on this charge particle, right? Like for example, is next time when you are going to actually next time basically means after 3 days, you can actually get a question something like this. So the previous question was definitely quite easy. So let's suppose this is Q1, this is Q2, this is Q3, this is Q4, and they are saying that find out the net force on this charge. Find out the net force on this charge, right? Now you will have to actually add them. So when you're, and generally, see again I'm telling you, generally they tend to keep the question simple. So generally they say that all the charges are equal in magnitude. Are you getting it what I'm trying to say? All the charges are equal in magnitude. So, and let's suppose they are also like charges. So this is going to repel in this direction, right? This is going to repel in this direction. Now the thing is, what you need to do for questions like this is first write it down what these forces are, right? So let's say this is actually F2, this is, let's say this is F4. So please write it down like something like this, that F2, magnitude of F2 is actually KQ square divided by A square. I mean, according to my assumption that all the charges are equal. So I would have it, we could write it like something like this, and this will be also equal to the magnitude of F4. Is that clear? And let's say that this is all of these things are equals to F. Obviously, again and again I am saying you will have to actually write it in a better way, right? So next thing is, if this is F, this is F, you are going to simply write it down that their sum is going to be F root 2, and this force will be actually along the force exerted by Q3. Force exerted by Q3. So something like this. So again you will have to add Q3 into it. I mean force applied by Q3. Alright, please quickly write down in the chat box if everything's clear. Done? Can we move on to the next part? We are talking about only the very important concepts, right? So we are not going to cover each and everything. We'll go a little quick. Now see, I have not talked about electric field. I have directly started electric field due to an electric dipole, because I am hoping everyone knows that electric field can be written as, it can be actually written as force experienced, electric field intensity can be written as force experienced by a unit positive charge. I am hoping everyone knows it. And using this formula, due to a point charge, if we are going to talk about a point charge, it can be written as kq square by, sorry, kq by r square, kq by r square, right? How much time is this session will take? I mean, all of those students who know how much time will take, at least answer your friend in the chat box. At least help each one of you. Quick. By the time I'll request to change my, I need another pen. Which part? Which part? Everything's clear? Alright, so when we are going to talk about an electric dipole, and let's also define what electric dipole is, right? So electric dipole is actually a system of two charges. You already know it, system of two charges having equal magnitude and opposite in direction, sorry, opposite in polarity, right? And then they are saying that let's find out the electric field at an axial point. So again, thing is quite easy, but important if you are going to talk about derivations. From the first chapter, electric dipoles derivation is important, then Gauss law is really important, right? So let's suppose that this is a point P at which we want to find out the electric field. Now please understand, the separation between these two, can be written as D. It can be written as D. Generally, for the sake of derivation, we write it in the form of 2A, so that we can easily derive it, right? So the dipole moment, I am going to explain it. The dipole moment is actually nothing but all right. So we are back again. Okay, let's take 2 seconds to breathe. Sir, please tell me important topics in every chapter. Okay, sir, कौन से chapters? सारे chapter पढ़ाऊंगा, every chapter. And please, I have again and again, I am telling you, important chapters video is already on the channel. Please see it. Chalo, let's see. So I said that dipole moment can be written as the product of charge times the separation. So Q into 2A, and the direction of this dipole moment is from negative charge to positive charge. Direction of dipole moment is from negative charge to positive charge. I'm going to let you see one interesting question from this concept, just the concept of direction of dipole moment in the next chapter. Okay, we'll see to it. So the thing is, let's say we are talking about a midpoint. Of this dipole, and the separation of this midpoint and this point is let's suppose it is x, right? So the thing is, now we can say that, okay, if that is x, this thing can be actually written as, this thing is x, so this thing will be written as x minus a. Please understand. Similarly, the distance from this particular charge can be written as x plus a, right? Is everything clear? Done? Quick. Now the next thing is, we are going to write E net at point P. So first of all, let's draw E net over here. At point P, due to charge plus Q, electric field will be outwards, right? So this is going to be the direction of electric field. By what? Due to plus Q. Great. Then we have got minus Q. So electric field due to minus Q is going to be in this direction. So this is going to be electric field due to minus Q. Now obviously they are vector quantities, electric field are vector quantities. Now this is the point where, let's suppose you know the derivation, right? You were able to mug it up. But still in exam you lose half a marks in these derivations or 1 marks in this derivation because you will not write it properly. See what is going to be the correct order. First of all, we are going to write, if we want to find out the net electric field at that point, that will be the sum of electric field due to Q, positive Q plus Q and minus Q. So we are not going to write a negative sign at this point. Alright, we are saying that by this is a vector quantity, so the net vector quantity will be the vector sum of these two. Now it happens that the angle between these two vector quantities is 180 degree, right? So if you are going to use that resultant formula of vector quantities, by the way, the magnitude of electric field is going to be, we can easily write it down, right? So let's suppose magnitude is E1 and E2. So we will write something like E1 square plus E2 square plus 2 E1 E2 cos 180. So cos 180 is minus 1, so that will automatically convert into E1 minus E2. That's why in the next step we are going to write E net equals to E plus Q minus E minus Q. Now please understand this step. First of all, I have not used vector sign over here, right? I have not used vector sign because I have already applied the vector addition. Now you don't need to write all of those things over here. I mean, you can get away without writing these things, all right? Because you have said that, okay, we are doing we are adding these vector quantities, they are anti-parallel. So and if you are not writing a vector quantity and you are writing a vector quantity over here, it shows that you are talking about just the magnitude. Is it all good? Now quickly see, we are going to write it down something like KQ upon R square. So R is actually X minus A whole square minus KQ upon X plus A square. Now see, I am without looking at your doubts, I am explaining what are the most asked question from this particular thing is. Usually students get confused, but sir, you have not applied a negative sign over here. But yeah, we have done each and everything when we were talking about this direction. So you don't have to write again direction over here. You don't have to add them up. Second thing is, why we are writing something as E plus Q minus E minus Q, because we know the magnitude of this vector quantity is going to be more than this. This one is greater than this one. Why? Because this charge is nearer to the point P. This charge is farther from the point P, and they both are equal in magnitude. So whose magnetic field is going to be stronger? Obviously the charge which is nearer to the point P, right? That's why we have written something like this. Now this is E net. By the way, we are talking about just magnitude over here. So now after this point we are going to simply say, let's take KQ common. Let's write 1 upon X minus A whole square minus of 1 upon X plus A whole square, right? And then the next step is going to be, let's just please solve this thing, right? So we are going to simply, and I'm going to also open it down. You can also do it in one step. So this is going to be X square plus A square plus 2AX minus, now see, I am opening this bracket, opening this square, as well as I am multiplying with a negative sign. So it will become minus X square minus A square plus 2AX whole divided by X square minus A square and square of this. So X square can be cancelled out, A square can be cancelled out, and finally the answer that you are getting over here is, I am going to write it over here. The E net is coming out to be KQ, and we have got over here as 4, right? So this will become 4A time, or I'll write it in order. We'll write it as KQ times 4A over over what? X square minus A square and square of this, right? Till now this is just a magnitude, all right? Got it, got it, got it? This is just a magnitude. If I want to convert it into the vector quantity, in the next step what I am going to write down is E net will be written as Q, and out of this 4A, take out 2A, right? Because we know that Q times 2A is a dipole moment. So we are going to write 2K P upon X square minus A square. By the way, if you are going to again look over here, at the very start I said that this is the dipole moment, that charge times the separation is 2A, separation between the two charges. Now tell me what is the direction of dipole moment. Direction of dipole moment is from negative to positive. That means this is the direction of dipole moment. Please understand, this is the direction of dipole moment. This is assumed conventionally. So this is P cap. So can I say, and also the net electric field will be in this direction. Also the net electric field is going to be in this direction. We have already discussed this. So E net can be written as 2kp upon x square minus a square, and because it is in this direction, the direction along the dipole moment, we'll simply write P cap over here. And as soon as we write P cap, it will become a vector quantity back again, which it should be, right? Whenever someone tells you to find out a quantity, and if it is a vector quantity, just don't leave it by writing magnitude only. You must write the direction as well. You lose your marks. If you want, you lose your marks. Sir, question, we will solve question. We will solve many questions, but first let's talk about the derivations. Now, I mean, we could have solved this question, this derivation in form of question also. You are going to see a problem in which you'll read a question that obtain an expression for electric field intensity at an axial point due to an electric dipole. So this is what you need to do, right? So now after this also, if it will be better if you'll again write one more special case, that's going to be for short dipole. For short dipole. So short dipole basically means if x is far more greater than a. So if x is far more greater than a, x square will be even greater than a square, right? So we can ignore this. A square. By the way, we have got one x also over here. Has anyone written this thing down in the chat box? We have also got one x over here, of course. Quick. Still, we have got over 100 of students, but still no one has written it. So what are you doing, guys? Quick. We have got one more x over here. Please see 2ax plus 2ax, that would be 4ax. So we have got one more x over here. So if x square is far more greater than a, I can ignore this a square. So E net will become 2kp upon x cube and p cap. So please note this thing, that electric field due to an electric dipole, the relation between electric field and x is that x is basically the separation from the midpoint is inversely proportional to the cube of it. All right, everything's clear? Quick. Let's move on to the next derivation now. Let's move on to the equatorial point. Let's move on to equatorial point. If we have got two charges kept at the same distance, so let's say this is plus q, this is minus q, and they are at a separation of 2a. Same thing, friends, and a point on an equatorial plane. So let's suppose this is a point. At this point we want to find electric field, net electric field, right? So we must know what this distance is going to be. Acha, just like previous case, let's say this is also x. Is that clear? So By the way, this is going to be A, this is going to be A. So this is going to be x square plus A square and root of it. So over here also x square plus A square and root of it. And at this point, where, acha, by the way, if you want to know, sir, how quickly we can find out the direction, just assume a unit positive charge over here. If you'll assume a unit positive charge, this will repel. So plus Q will actually repel. So plus Q will repel in such a way. So this is going to be electric field due to positive Q charge. And this one is going to attract, so electric field will be also something like this. So this is going to be the electric field E minus Q, right? Also, dosto, let's assume that these angles are theta. Acha, this angle is going to be theta, so this angle is also going to be theta. Sides are equal, right? So in this case, next thing is going to be, then this angle is also going to be theta, and so will this angle be. Quickly write down in the chart box if everything's clear. Now please write it down in the, after drawing all of these things, write it down again, write it down that the net electric field due to an electric dipole will be again the vector sum of electric field due to both the charges. This is actually a very important thing. It shows the examiner that you know what you are doing, right? Next thing is going to be, you are going to write it down over here as well. Write down the components. So this one is going to be E plus Q cos theta and E minus Q cos theta. So I'll simply write over here as 2E cos theta. 2E cos theta, and I'll tell you why. See, I mean, you must be able to understand where you can actually take, you can actually skip a step, you can skip a little thing, and where you must actually write everything down. So whenever you are starting something, whenever you are starting your solution, right, please mention what you are trying to do. After this, you can write something like the vertical component of electric field cancel out each other, and horizontal component adds up, It would be better if you'll again write the magnitude of these things. That obviously you can write it down something like the magnitude of E plus Q is actually equals to the magnitude of E minus Q. By the way, this was not the case in the previous derivation, right? This was not the case in the previous derivation. In the previous derivation, the magnitudes were not same, all right? Now, if the magnitudes are same, that's why I have written 2E cos theta. So you can get away with that. You don't need to write, sir, EX, E plus QX, E minus QX equals to this. So next step is going to be E net is equals to 2E cos theta. Now please understand, as soon as I've jumped from this step to this step, again I am talking about the magnitude only, because now I know in which direction my net electric field is going to be, not mine but this dipole's, right? So this dipole will have its net electric field in this direction. We know it. So now we can just talk about the magnitude of it. And then again we will write it down in the form of dipole moment, of the direction of dipole moment. All right, done. Next, quick. So this is going to be 2, instead of E, we are going to write KQ upon R square. Now when you are going to talk about R square, now this is your R. Okay, so square that down. So x square plus a square, rule gets cancelled by square, times cos theta. Cos theta, take any of the triangle. Cos theta would be base a upon again that value. So x square plus a square and then root of them. Now base are same, you will add the powers. So 2kqa divided by x square plus a square raised to the power 3/2, and this is your magnitude of net electric field. Is that clear? Still I can't write write it down in vector form. Why? Because to write it down in vector form, I'll have to define a unit vector. Although I can define a unit vector, I'll just define a unit vector as a cap. My wish, this is a cap. But the correct way would be, after this step doston, we will say that okay, net electric field in vector form will be, again we are going to say that 2 Q and A can be written as, by the way, everything's clear till this point, hopefully everything's clear. So this thing can be written as K into P divided by x square plus a square and raised to the power 3 by 2, and because I have written it in the form of magnitude of dipole moment and I have put a vector sign over here, now I'll write a P cap. Is it clear? Quickly write down in the chat box. Quick. We are going to, I am again saying we are going to solve some questions. See, I've got many questions over here, okay? Don't think that we are not going to solve questions. We have got multiple choice questions. Then we have got your normal, these types of questions. Then we have got questions like these. So we have got enough questions. But before that, what I am trying is, I'm speeding up your revision. I'm explaining each and every derivation. Then shortly we are going to come back to questions. So coming back to this thing, again you can talk about for short dipole. So for short dipole, again we'll say x is far more greater than a. So if x is far more greater than a, E net will be actually written as, by the way, can you sense one thing over here? Can you sense one thing over here? One thing over here. Dipole moment is in this direction, dosto, and our electric field is in this direction. So shouldn't I write a negative sign? Yes. So I'll write a negative sign over here as well. So it will become Kp upon x cube dot p cap. That's it. All right. Quick. Your thoughts on this, your doubts on this, then we'll move on. Quick. Right, Kevin, right? We have done it. Any more doubts? Minus Kp upon x cube. Yes, notes will get uploaded, or either you will get it on Telegram. You will get it. Don't worry. Sir, your opinion about the question paper. Last year question paper was easy, I think. Easy. Sir, हिंदी में बोल लीजिए. So obviously you have missed the first part of my class, but okay. So now let's come back to torque acting on an electric dipole. See, again, this is an important thing. Usually you are going to see a numerical from this portion, but still they can ask you to actually derive an expression. So let's suppose this is an electric field, and that's why I'm explaining quickly. I'm explaining quickly. If you have any doubt, please write down in the chat box. Doubt should be crisp, short, brief, and crisp, right? Quickly. Quick. So let's suppose we have got a dipole, something like this. That means two charges, minus Q and plus Q, right? And electric field is in this direction. So what will happen to this electric dipole if it is in this particular orientation? First of all, forces will act on these charges. Now forces will act on this plus Q charge in this direction and minus Q charge on this direction. Why is it so? Whenever you are seeing some electric fields, now if you are having some trouble 3 days before exam in these things, I'll give you a little trick. The trick is, just assume dosto that you have got some imaginary positive charge over here, and you have got some negative charge over here. That's how you can actually get electric field something like this in one way, right? There can be another ways also having electric field like this, but one of the way can be something like this. So for a negative charge, a force will act in this direction. By the way, this force will be written as, dosto, this force can be actually written as Q into E, and this force will also be written as Q into E. Is it all good? भाई कितना आप लोग स्पैम कर रहे हो? सर, आई एम लूजिंग ऑल आई स्टडीड. What is the way to recover? Sir, can you teach ray optics? So, abhi both of you, how you are going to recover? one of the way can be attending this class, right? One of the way can be attending this class. And another doubt is, sir, you teach, I'll teach each and every chapter. So obviously I'm going to also teach ray optics, but after some time, right? Now coming back to this, if you will closely see, we are going to say that net force on an electric dipole, net force on an electric dipole is 0. Now they can frame some or certain reasoning question from this particular part, right? What does this imply? This implies that the net acceleration on the electric dipole will be 0, right? So there will be no change in translational motion, no change in translational motion. And assuming it, if it was at rest initially, it will remain at rest, right? But the thing is, these forces are actually we are going to say these are not collinear forces. These are non-linear forces, right? Got it? So these forces are non-linear, hence makes couple, right? They'll make couple, by meaning they'll make couple is torque will get applied, and let's suppose this is the center point and torque will be applied in such a way, let's say that the perpendicular distance between these two forces is, if let's suppose this is 2a, so this is going to be 2a sine theta, right? So the torque will be force times the perpendicular distance. So force is QE, perpendicular distance is 2a sine theta. So this is going to be the magnitude of the torque, right? Further you can rewrite this thing as torque equals to, again dosto, 2a into q. It will be written as P. So it will be written as PE sine theta. Quickly write down in the chart box, very easy thing. This was the magnitude, or surely you are going to write down it in vector form. In vector form, it will be written as torque equals to P cross E. I'm going to explain the direction also, so hold on, right? So this is going to be in vector form. What's going to be the direction and what this electric field is trying to do? First understand this thing. Electric field is trying to actually align this dipole in the direction of electric field, in the direction of itself, right? And for doing so, it is actually applying a torque, and the direction will be found by using P cross E. Now, how to use P cross E? What is, first of all, what is P? So dipole moment P is in this direction. This is the direction of dipole moment. Please understand. This is the direction of dipole moment. So P, your normal right hand rule for vector products. P cross E, E is in this direction. So the thumb is going to be in this, into the plane, and this is actually clockwise. So for this particular example, the torque is acting clockwise or into the plane. Got it? Everything's clear? Quick, tell me. Moving on to the next part. Moving on to the last part, then we are starting some questions. Moving on to the Gauss law. What does Gauss law says? A very important thing. Statement is quite important. Total flux emerging out from a closed surface is equal to the product of sum of enclosed charge by the surface and the constant 1 upon epsilon naught. What does this means? This means that, let's suppose that you have got a closed surface over here, which is often known as Gaussian surface, and then you have got some charges, something like Q1, Q2, Q3, and let's also say that you have got Q4 and Q5. And some of them are positive, some of them are negative, right? Now, how you are going to write it down? You are going to simply say, the statement simply says that the net flux will be actually equals to the enclosed charge upon epsilon naught. Also, the net flux can be written as the surface integral of E dot ds, and this will be written as enclosed charge upon epsilon naught. when you are going to talk about the enclosed charge for this particular example, when you are going to talk about the enclosed charge for this particular example, the enclosed charges is going to be Q1 minus Q2 plus Q3, right? So one important thing, again, they can ask these things in assertion and reasons, right? This electric field is actually due to all the charges. This electric field is due to all the charges, even these Q4 and Q5, but they do not contribute any flux, right? So please, this is important. Why? Because obviously the number of electric field lines which are going to actually pass through this surface due to Q5 will actually, the number of fields lines which are incoming are also outgoing, right? So the number is same. So net flux for Q5 will be 0. So now the thing is, I've written each and everything over here. That's all what Gauss law is. Gauss law's statement is important, actually the more important thing is the application of Gauss law. So let's quickly come to that. By the way, we talked about each and everything. Electric field due to a charge outside the Gaussian surface contributes 0 net flux through the surface. Important point, note it down. Next is Gaussian surface should be chosen. They might ask you that why you choose Gaussian surface in such a in any specific way, right? So the thing is, we actually do that so that we can easily find out the net flux, and that particular way is either the angle between the area vector and electric field is 0 or 90 degree, right? So this is a very important thing. The surface should be chosen in such a way that every point surface electric field strength is either parallel or perpendicular to the surface. Good, easy peasy. Can we move on? See, we are talking about, let's talk about a wire. Let's talk about an infinite wire, right? So if we have got an infinite wire having a charge density lambda, right? And you're going to get some questions from this as well. If you have got a infinite wire, what we are going to do over here is we are going to assume that a Gaussian surface in the form of cylinder. So cylindrical Gaussian surface is here, and now we'll apply the normal Gaussian rule. So now what you can actually see is you have got like 3 surfaces over here. You have got 2 circular surfaces and 1 curved surface, right? So when you are going to talk about the net flux, it will be because of 3 things: 1, 2 and 3, and all of this will be actually equals to enclosed charge upon epsilon naught. And let's say this is surface 1, this is surface 2, and this is surface 3. Now the next important thing is, if we have got a charge wire like this, the direction of electric field will be emerging out because it is a positive wire. Right? Which means that if you are going to draw an area vector over here, if you are going to draw an area vector on the circular region, wherever you are going to draw an area vector, it will always be perpendicular to the surface. So this is perpendicular to the surface. So this is your area vector A. So I am going to write it as A1, and this is your electric field. This is, let's suppose this is A3. Right, and you all know what in which direction electric field is. Also, we will draw one more surface, one more area vector over here as A2. Is it clear? So we have got total 3 surfaces, out of which 2 are circular, and we can note that the angle made by the area vector and electric field is 90 degree over there. So for these particular, the net flux will be 0. And you can write down the reason over here, that we are going to write something like E A cos 90, right? So we'll be left with phi 2. Now for phi 2, we are going to write E dot ds equals to enclosed charge upon epsilon naught. So let's suppose we are talking about a particular length L. So area is going to be 2 pi r L, 2 pi r L, and what is this r dosto? R is this radius of the cross section, which means we are trying to find out a relation of electric field at a certain distance of r, right? So this will be actually equals to enclosed charge. What is enclosed charge? This is the point where some of you might feel a little uncomfortable. If everything was clear till this point, enclosed charge, whenever someone tells you what enclosed charge is, please look for this lambda. This is your linear charge density or any type of density, okay? When someone is saying linear charge density and you want to find out the enclosed charge, or you want to find out what is the total charge, so all you need to do is you need to multiply lambda with the length. If you have got sigma, sigma is surface charge density, so multiply sigma with area, you will get the charge, divided by epsilon naught, and as we can see, it does not depend upon the length, right? Electric field due to a wire does not depend upon its length. It is coming out to be, E is coming out to be lambda upon 2 pi r epsilon naught. Please note it down. This is very important. The formula itself is actually important. All right. Now, if you'll ask me to solve some problems from this particular, let's start. Let's start some problems. I know there are 2 more derivations. I'll do it, but let's start solving some problems. Quick, and they'll be poll. So quickly, let's, dosto, I want you to get active. A thin plastic rod is bent into a circular ring of radius capital R. It is uniformly charged with density lambda. The magnitude of electric field at its center is. I am starting the poll. Starting the poll, giving you 60 seconds. Find it out. Quick. So you have got a thin plastic rod which is bent into a circular ring, something like this. It is uniformly charged. Don't get confused with, sir, how it is a plastic. It can get charged, right? You know it. So, and you have got charges over here, something like this. And we want to find out the net electric field at this point, at center. And I'm just drawing some reference line over here. All right. Come on, quick. The magnitude of electric field at the center. Easy peasy. We'll simply say that take any part. Let's suppose you are taking a part dq over here, right? I know the answer is very easy, but let me explain you the correct way. Quick. So let's say this distance is, whatever this distance is, the electric field due to this dq will be something like this. Right? Now you will have exactly same charge diametrically opposite to it, which will also have same electric field in the opposite direction. So they will always cancel out each other, right? Very easy. 0 is going to be the answer. Quickly tell me in the chat box if you have any doubt. So B is going to be the correct answer. Whoa. Okay, very good. Good. How to use these polls? Let me explain it. You just have to write down the answer in the live chat. Your answer will be taken. All right, along with your name, whatever name you have put over here. Let's move. An electric dipole of length 2 centimeter. That means this is actually 2A, right? So whatever you want to write it down, this is actually whole of D. This is 2 centimeter. Is placed at an angle of 30 degree with an electric field. Acha. Placed at an 30 degree with an electric field, that means that electric dipole moment is making 30 degree of the angle. So theta is actually equals to 30 degree, and electric field, the magnitude of electric field is 2 into 10 to the power 5. Whenever they say that it is making an angle of 30 degree, it means that angle between dipole moment and electric field. What torque it experiences? Quick, 45 seconds. 45 seconds, quickly do it. Use the formula torque equals to PE sin theta. Again from last year. Not last year, from 2023. Last year. By the way, This is the thing I was explaining in my most important topics video also. If you want to gain those first 18 marks, at least from the first 15 marks other than assertion reasoning, daily practice the formula chart, right? Do not skip the revision of formula chart. Do not assume that, sir, first I'll complete my course, then I'll revise each and everything. It will be too late. Now please tell me what concept you will need to find out the answer. There is no problem, right? So P, that means over here we are going to write dipole moment as Q into D. So do we know what we want to find out the charge, right? So okay, experiences a torque. So 8 into 10 to the power minus 3, and this is going to be Q that we need to find out, times D, that is 2 centimeters. So don't forget it to convert it, times electric field. Electric field is 2 into 10 to the power 5 times sine 30, which is 1 by 2. So I can cancel out these things, right? I can write down this thing as 4. So I'll get 4 into 10 to the power minus 3 minus 5 and plus 2. Is it good? So this will be actually 4 into 10 to the power minus 6, that is 4 microcoulomb. So option A is absolutely correct. Write down in the chat box if you have any doubt. A, not D. Quick. Right? Quickly tell me if you have any doubt, doston. We have just started the marathon. We have just started the marathon, right? What is, acha, someone is asking what is the difference between electric dipole moment and dipole moment? No difference. I mean, if you are going to just talk about dipole moment, you could have also be talking about magnetic dipole moment, right? So that's why we tend to write electric dipole moment. Length is 2 centimeter. We'll have to convert it into SI units. That's it. Let's move on. Quick, quick, quick. Your answer, you are not able to write down the answer or what? All right. I have changed the units here. I have changed the units, please. This is centimeter, 2 into 10 to the power minus 2 meter. Let's quickly move on. Achha, let's check this question. The magnitude of electric field due to a point charge at a distance of 4 meter is 9 Newton per coulomb. From the same charge object, the electric field of magnitude 16 Newton coulomb will be at a distance of. Can you do it by yourself? Quickly tell me. Quick, quick, quick. Let's solve this question. Quickly. They are saying that electric field due to a point charge at 4 meter, let's say this is E1, it is actually 9 Newton per coulomb, and it is KQ divided by 4, right? And at a different point, it is actually 16. So they want us to find what that distance is going to be. How simple it is? Quickly tell me. Just divide them, right? So this will become, we can cancel out these things. This will be 9 by 16 equals to by 4. So this will be R equals to 9 by 4. Can you please check once? 16 Newton coulomb at a distance of 4 meter. Acha, sorry, A square. Sorry. This is not potential, this is square. So we have to square it down also. So this will be 9 by 16 equals to, this gets cancelled out. This is R square, this is 16. So R will be actually plus minus 3. Magnitude will be 3. Right? So 3 is going to be the correct answer. C is correct. Quickly tell me. Quick, easy question. Can we move on? Okay, I didn't started the poll for this particular thing. Can we move on? Let's move to one assertion reasoning. Let's see what type of questions can we see from this part. Question is saying work done in moving a charge. All right, so although this question is actually part of electrostatics, potential and capacitance, but it's fine, we can do it. It's not a big deal. Quickly, let's do it. Work done in moving a charge around a closed path in an electric field is always zero. This is absolutely correct because electrostatics force is a conservative force. This is also true, right? Electrostatics force is a conservative force, and whenever you have got conservative force, the work done only depends upon the initial and final position. So if they are same, because if you are actually moving them in a closed path, that means initial and final position are same, and this is going to be zero. So this is absolutely correct. Both A and R are true, and R is the correct explanation of A. So this is going to be option A. I am again and again saying we have just started the class, so stick with me. We'll be able to actually finish a very good portion of your course, right? So you'll be in a very good situation, trust me. Let's quickly solve these questions without worrying. Now the next thing is, I'll give you one tip that I usually give in each of these marathons. Whenever you are going to solve these assertion and reason, is a very beautiful trick is just read down the assertion and then use a word because or due to or since, something like work done in moving a charge around a closed path in an electric field is always zero because electrostatics force is a conservative force. Now after this, is this whole sentence making a complete sense? If yes, then choose option A. If you have a slightest of the doubt, now if you are thinking that yes, reason is true, but I mean when I'm saying these two things in one go, it is not making a really good sense, right? So then you are going to choose something like A is true, reason is also true, but not a correct explanation. Moving on, let's move on to the next one. An electron experiences a force of this in I cap an electric field. The electric field is, very easy question, very easy. Quickly, quick. Bhai, come on. Sir, please tell me the difference between the equations of 1 upon root LC and 1 upon 2 pi root LC. We'll talk about it in alternating current, na? So you don't have to worry about. Sir, RBSE board के लिए है क्या? नहीं, this is for CBSE. Alright, your doubt is clear. Now stop spamming. Quick. Quickly, poll. I've not started the poll. 45 seconds will be more than sufficient. An electron experiences a force of this. We know that force can be actually written as Q times E. So E will be nothing but force, which is 1.6 into 10 to the power minus 16 divided by 1.6 into 10 to the power minus 19 coulombs, right? And by the way, whatever the direction of force is, electric field will be in same direction. So this is going to be 10 to the power 3 Newton I cap. So 1 into 10 to the power 3. Quickly tell me in the chat box. Please don't spam. Quickly write down the answer. A is correct. Yes, we are going to do each and every chapter. Very good. Kevin, why B? Why B? Please try to understand. You have got an electron like this, right? And a force is acting on it, something like this. how you are going to write down the electric field? In this way, na? Electric field will be force per unit charge. So whatever the direction of force is, you are going to write down the same direction. Do we have minus over here? No. So it's going to be option A. Got it? Very easy. Can we move on? See, you're getting confused. Let's suppose that we have got an electric field like this. But yeah, if you are going to spam like this, I'll have to remove you from the chat box. Chalo, come on. See, if you have got a positive charge and you have got a negative charge kept in an electric field, then what you can say is that force will act on in this direction, and on this the force will act in this direction. Alright, quickly now let's move on. We have already completed this particular question. Next is going to be, let's move to this one. 3-point charges 1 picocoulomb each are kept at the vertices of an equilateral triangle. Alright. Of side 10 centimeter, find the net electric field at the centroid of the triangle. Alright, at the centroid of the triangle. Done. So at the centroid of the triangle. Yes, pico is 10 to the power minus 12. And you have got, let me check just a second. Let's say we have got 3 charges, something like this, Q, Q and Q, Q, Q and Q. Find the net electric field at the centroid of the triangle. So we'll simply say that the net electric field will be, because of this, it will be in this direction. Because of this charge, it will be in this direction, and because of this charge, it will be in this direction, right? If they are talking about the electric field, let's name this thing as A, B and C. So this will be electric field due to A, electric field due to B and electric field due to C. And these are going to be your 120-degree angle at centroid. Is it clear? Clear? कितने ड्यूरेशन की होगी क्लास? ड्यूरेशन इज गोइंग टू बी till we finish this entire course, till we finish the entire course, right? Now whenever you are going to see a problem, like whenever you are going to see an arrangement like this, na, the magnitude is also same, by the way. So EA magnitude is actually equals to the magnitude of EB, and this is equals to the magnitude of EC. So the net force or net electric field will be 0. Are they talking about the force on electric field? Electric field. So net electric field will be 0. Alright. Quick. You can write down the answer as due to vector addition. Let's quickly move to one numerical. Quick. Electric field E in a region is given by 5x square plus 2 I cap, where E is in Newton per Coulomb and x is in meters. A cube of side 10 centimeter is placed in the region as shown in the figure. Alright. Calculate the electric flux. So whenever they are going to talk about electric flux now, and they are discussing that, okay, we have got electric field also, then what you can do is you can use the Gauss law. You can say that net electric flux will be actually equals to the enclosed charge upon epsilon naught, and further you know that this thing can be actually written as, you know how to write the net flux, right? Net flux can be written as, we'll write it down for this particular case. Please understand, electric field is actually not uniform. Can you say something about this electric field? This electric field is not uniform. The reason is that it is always acting in the same direction, but the magnitude is changing. Magnitude is dependent on x, right? So as you are going to move from x, electric field will increase. That means if you are going to talk about this specific face, I'll try to draw it over here. I'm talking about this specific face. This one, right? So this one will have its area vector in this direction. This one is going to be the area vector. And electric field is going something like this in the x direction. But what is going to be the magnitude of electric field at this point? Let's say this is E1, right? So electric field at this point, E1 will be actually 5 into square of 0 plus 2. 5 into square of 0 plus 2, that means the answer is going to be, the electric field is going to be 2 Newton per Coulomb. So that means if you are going to talk about this flux 1, it's going to be E1 A1 cos theta 1. So E1 is 2, area is going to be, can we know what area is? Side was 10 centimeter, right? So if it is 10 centimeter, it's going to be 0.1 times 0.1, and cos 180 is going to be minus 1. Please understand this point. This is going to be cos 180. The angle between these two is going to be cos 180 will be minus 1. Write down in the chat box if everything's clear till this point. Right? So this will be minus 2 into 10 to the power minus 2, and this is going to be, your Newton per Coulomb meter square, right? Now let's talk about phi 2. Phi 2 is this flux linked with this surface. Now for this particular case, area vector is in this direction and electric field is also in this direction. So now I am going to say that the angle between these two is going to be 0 degree. So phi 2 will be E2 A2 cos 0. By the way, E2 is going to be 5 times x is 0.1 into 10 to the power minus 1 square of this times plus 2. Please write down in the chat box if everything's clear till this point. Quick. Why distance from origin? Because this particular face is kept at origin. Quickly write down in the chat box if everything's clear till this point. Everything's good? So phi 2 will be E2 A2 into cos 0. Come on, quickly write down the answer in the chat box, dosto. Quick. I want the answers in the chat box. Is it clear? Clear? And as soon as you get to know what phi net is going to be, enclosed charge will be just phi net times epsilon naught. You just need to solve it down now. Why we took x equals to 0? We took x equals to 0 because, buddy, this face is at the origin, right? This face is at the origin, and we know that E can be written as 5 times x square. Why we have taken x as 0? Is it all good? Quickly write down in the chat box. I think 2024 and 2024 and 2023 are equally important. All right. Done. Can we move on to the next part? Acha, now they are talking about thin spherical shell, right? And that's what I said. Some of the topics I'm going to take it as theoretical part. Some of the questions we can solve it through questions also. They are saying we have got a thin spherical shell of radius r with uniform surface charge density sigma. Using Gauss law, deduce the expression for an electric field, right? So let's suppose we have got an electrical shell like this and it has got radius r. So we are going to find out the electric field at 3 points. First is inside. Inside basically means that the radius of the Gaussian surface will be less than the radius of the spherical shell. Now spherical shell basically means, I have already explained why 0 na. Is it all good now? Done? Please understand. Going to also explain the graph. For this particular thing, when you are going to draw a Gaussian surface in itself is going to look like a spherical, is going to look like a sphere. So this is our Gaussian surface for case 1, right? So in this case, we are going to simply say bhai that whatever net flux you want to calculate it, fine, you will write it something like this, that electric field times 4 pi r square equals to enclosed charge, but there is no enclosed charge over here. So there will be no electric field inside the surface. Very easy derivation, right? But still you can expect it and it's going to be free marks for you. Now the second case is, if we are going to talk about on the surface, or let's just write one thing outside the surface, and I'm in this particular one, I'm going to say that r can be either greater than capital R or it can be also equal to it. Is that clear? So in this case, we are going to say that electric field times 4 pi r square is equals to enclosed charge divided by epsilon naught. Now understand one thing over here. This E dot ds, usually we write it as E ds cos theta. Now why we are writing something like this? Because when you are going to actually draw a Gaussian surface in such a way, see, I am explaining it, okay? So please pay some attention. So this is the Gaussian surface for part 2, for case 2. So when you are going to say that, okay sir, let's suppose that electric field, we know that this is actually a positively charged shell. Electric field is, let's suppose it's going to move something like this. So when you are going to draw an area vector over here, an infinitely small area, this is going to be like ds. It's going to be in this direction. Is that clear? So just like this, everywhere the theta is going to be 0 radian. So we can simply write E integration of ds. So what is the integration of this entire surface? That is 4 pi r square, because it is also a shell. So 4 pi r square. When you are going to talk about the enclosed charge, you will simply say that sigma is the charge density over here and the total area is actually 4 pi r square divided by epsilon naught. Please understand if you have any doubt, or simply generally you can also rewrite it something like this, that q upon epsilon naught, and you can write electric field as q upon 4 pi epsilon naught into r square. Now if you will ask me to draw the graph for it, I'll draw a graph something like this. Till x equals to capital R, there was no electric field. At this point, electric field is k q by r square, and after this electric field is decreasing in this way, right? Quickly write down in the chat box if everything's clear from this particular part. Quick. Can we move on? Acha, by the way, there was one more question. There was one more question. Then we can move on to the next part. Two long straight thin wires AB and CD having linear charge density as 10 microcoulomb and minus 20 microcoulomb respectively. Okay. So this is what I was saying, that derivation as well as formulas both are important. See, if you are going to only talk about, if you are going to, let's say that you are only preparing derivations, I mean, if majority of the questions comes like this, you will be in trouble, right? Got it? Done. So we have got two wires AB. So this is A, this wire is AB and this is CD. And we have got their linear charge density. They are kept parallel at a separation of 1 meter. That means this separation is of 1 meter, right? Find the magnitude and direction of magnetic field at the midpoint of between them. So we have to find out the magnitude of net electric field. Can you do it quickly, doston? We know that electric field due to any wire can be actually written as doston lambda upon 2 pi epsilon naught into r. Is it clear? So quickly here find it out. By the way, one of them is positive. So this is, let's suppose this one has got lambda 1 of 10 microcoulomb per meter and this one has got lambda 2 of minus 20 microcoulomb per meter. Answer in the chat box if this question is all good to you. Clear? Everything's clear till this point. I'm just talking about the second part, right? If we'll discuss net electric field will be in such a way, because of lambda 2, net electric field is going to be in this direction. So this is going to be electric field due to E2, and because of this one, electric field will be in such a way. So we'll just add them up. So net electric field is going to be lambda 1 upon 2 pi epsilon naught into r, because they are at midpoint, lambda 2 divided by 2 pi epsilon naught into r. Tell me in the chat box if you have any doubt. Quickly. Quick. If you have any doubt, tell me in the chat box. So now let's move on to electrostatics, potential and capacitance. Quickly. Let's move on to some to the next chapter. And before starting the next chapter, let me first start with some basic questions. And then also we'll talk about concepts again over here, because this is just one complete chapter, that is electric charges and fields, electrostatics, potential and capacitance. So you are going to see a question which half of the part is from electric charges and fields and another part is from electrostatics, potential and capacitance. Quick. This question says equal amount of positive and negative charges are distributed uniformly on the two halves of a thin circular ring as shown in figure. The resultant electric field is along OC. It is so because the net potential is not zero. Let's talk about it. Let's start the polls for this one. Okay, by the way, this was, let's say this was A. Chalo, let's start. I'm starting the poll, giving you 90 seconds for this. Quick. Write down your answer in the chat box. Question says equal amount of positive and negative charges are distributed uniformly on two halves of this thin circular ring as shown in the diagram. Quickly. Come on. First of all, again, let's suppose, to explain this question, let's suppose we only have got one half of the circle, one half of the ring, doston. I'll explain it to you. And this half has only positive charge. Think about it. This charge, this part has only positive charge, something like this. Isn't it? Right? And if someone tells you to find out the net electric field at center, how would you do it? You don't have to literally solve it. You don't have to use integration and anything like that, but please have an idea. Let's suppose I've got a dq charge at this point. So because of this dq charge, the net electric field will be, first of all, it will be in the opposite direction of the line joining it. So this will be, let's suppose this is df. Also, I mean, similar point at symmetrical point, we'll have another dq over here. And because of this particular charge, small charge, electric field will be something like this. So what I am trying to say is that these electric fields, horizontal component will again cancel out and their vertical component will add up. So this is going to be the net electric field or net force, whatever you want to call it. The net electric field will be in this direction. Is it all clear to you? Quickly tell me in the chat box if this is all good to you. Done. Now let's suppose we have got another wire and we want to do the same thing over here. So let me draw another diagram. So if we have got another part which is something like this and you want to calculate net field at this particular point, what will you do is you will again take a dq. Now for this particular thing, dq, the electric field will be in this direction. And similarly for this, electric field will be in this direction, net electric field will be in this direction. And if you remember, electric field due to the positive charge was also along this direction. So this is going to be the net electric field. Tell me in the chat box if everything's clear, right? So equal amount of, the resultant electric field at the center is along line OC. This is actually a true statement. Many of you have got this one. This is a true statement. It is so because the net potential at point O is 0. So is not 0. They are saying it is not 0. Let's find it out how to write down the net potential. Doston, potential is a vector, is a scalar quantity. So potential will be due to all the positive charges plus potential due to all the negative charges. Is it clear? Well, we have got equal positive charge and equal negative charge, and they are also at equal distances. They are at same distances. So that means the net potential is going to be 0. So second statement is actually false. Second statement, reason is actually not true, it is false. So assertion is true, reason is false. That means option C. I'll take your doubt, but be really quick. 87.5, very, very good. Quickly tell me in the chat box if everything's good till this point. Quick. Let's move to some new questions then. You are not going to get electric field due to a ring to derive. Okay, so don't worry about that. Very good, Kevin, Hilaria, good. Now let's move on. Let's see this one. Two charges plus q each are kept at 2a distance apart. A third charge minus 2q is placed midway between them. The potential energy of the system is. So although I have not explained the concept, but now we can do it. Potential energy of a system. So you have got plus q over here, plus q at this point at 2a, and then a third charge minus 2q at midpoint. That means a and a. Everything's good, right? Clear? So now after this, if someone's saying that write down the potential energy of the system, we'll simply write down the pairs. Okay, so how I'm going to explain it to you is, let's suppose we have got charges as at point A, B and C. First of all, what is potential energy? Let's first discuss this thing. So this is our arrangement. Potential energy can be defined as potential energy of system. Dosto, now please understand, I am explaining the concept through a question. Okay, potential energy of the system is the amount of work done, to assemble the system, right? So what was the system's final, finally the system will look something like this. So what is going to be the work done? So work done would be, first of all, we will bring our first charge. Let's suppose this is our first charge, plus Q. So what is going to be the work done in bringing this plus Q charge from infinity? So you are going to say that, sir, there were no charges before this particular charge, right? So there will be no work done. When you are going to bring another plus Q charge at this point from infinity, now we have got one charge plus Q already, right? So that means the work done in bringing that charge, so I'll write it as W1, that will be K Q by R times Q, and this R is actually, in this case, this R is 2A. Now again, if I am going to bring another charge of minus 2Q, now I'll have to do work due to these two charges. So now the net work done in bringing this second charge will be 2 times of, why I am directly writing 2 times? Because I've got these two charges. Is it all good to you? Quickly write down in the chat box. Quick. So this is going to be K Q minus 2Q upon A. So this will be minus 4 K Q square upon A. So the net work done is going to be minus 4 K Q square upon A plus K Q square upon 2A. Tell me if you have any doubt. So this will be 8, this will be minus 7 K Q square upon 2A. Minus 7 K Q square, this is coming out to be minus 7 K Q square upon 2A. If I am going to convert this, rewrite this K, so I will get minus 7 Q square upon 8 pi epsilon naught times A. So 7 Q square 8 pi epsilon naught times A, that is option C. Is it good? Please quickly write down in the chat box. How come B? Quick. Quickly write down in the chat box if you have any doubt. Quick. Yes, please. If you have any doubt, please ask. If you have any doubt, you can ask. Bhai, if you have got like more charges over here, na? If you have got more charges, let's suppose you have got, let's suppose you have got a square. So this is A, and I'm not writing signs over here. Okay? So let's suppose this is Q1, this is Q2, this is Q3, this is Q4. Not writing signs, these are without signs. You want to write down the total potential energy of the system. And right now there is no external electric field, by the way. So total potential energy of the system will be, always make pairs. I have explained you conceptually, now let me give you a trick. Always make pair. So make pair of Q1 with each one of them. So K Q1 Q2 divided by A plus K Q1 Q3 divided by root 2A plus K Q1 Q4 divided by A. Now plus, now again make pair of Q2 with everyone. So that would be K Q2 Q3 divided by A plus K Q2 Q4 divided by root 2A plus, now make pair with Q3. So we have already mapped Q1 and Q2. So Q4 is only left. So it would be K Q4 Q3 divided by A. That's it. I have not written the sign over here, right? So it's according to the sign, it will depend what type of potential energy are you getting. Quickly write down in the chat box. Any doubt? Quick. All right. So, dosto, hopefully this concept is also now clear to you. Now let's move on. Let's move on to next question. Question like this. Acha, what do we have over here? The question is saying two identical small conducting balls P1 and B1 and B2 are given charge -7 picocoulomb and +4 picocoulomb charges respectively. They are brought in contact with a third identical ball. Do you remember when we started our class, I told you that we are going to look into an interesting question, right? So they are saying that if the final charge on each ball is -2 picocoulomb, the initial charge on B3 is. Try to solve it. I'll give you a hint. It is just conservation of charge. You just need to apply conservation of charge. Quickly do it. 60 seconds. 60 seconds, quick. This is from electric charges and fields. All right. Ask your doubt. If you have any doubt, please ask it. I'll explain it. Previous question. Yeah, previous question I have already explained twice here. Now mark it down in your personal doubt, and if you think now that you have got a specific doubt, mark it down, and then you can you rewatch it. Stick with me. Don't lag. Okay, stick with me. When is next chapter? We are going to start next chapter very soon. By the way, for this one, see, we know one thing. When they all three are going to be brought in contact now, let's say that they have got initial charges as Q1, Q2 and Q3. Let's suppose their initial charges were these. Initial charges. We know one thing, that the total charge initially is equals to the total charge finally for an isolated system. What do you mean by an isolated system? These three balls were an isolated system. So when you actually started to touch them, now when you are going to basically say that initially the sum of the charges were Q1, Q2 and Q3. So this is going to be Q1 plus Q2 plus Q3. So -7 plus 4 and plus Q3 equals to, now each one of them has got charge of -2 picocoulomb, and because answer is in all picocoulomb, I don't have to worry about converting it. So this is going to be 3 times of 2 picocoulomb, right? So Q3 will be, this is actually minus 3, and that is actually 6. Is it all good? Can we please check once again? That is actually -2. Sorry, this is -2. So this is -2. So this is going to be -6, and we'll get over here as +3. That is -3 picocoulomb. So -3 picocoulomb is going to be the correct answer. Hopefully everything is clear. Moving on. See, I only give poll to those questions. Very good. By the way, very good. Very good. Void, Hari, Rashik, Pharma, Aditya, Kevin, Hilaria. By the way, Kevin and Hilaria are from the batches. Hi to you. Swati here. Very good. Swati is also, I think. So this was an easy one. That's how you need to do it. Now let's move on to the next question. The next question is saying The electric field in a region, hopefully you don't have any doubt. I will teach the part 2 as well. The electric field in a region is given by this. Okay. Acha, whenever you see this type of electric field, please quickly tell yourself, okay, this is a non-uniform electric field. That's it. Nothing so special about it. Non-uniform electric field, and what's so non-uniform about it? Its magnitude is changing, direction is not changing. Direction is across is along I cap, magnitude is changing. They are saying calculate the work done in taking the unit charge from this point to this point. All right. Okay. So this basically when we'll discuss about work done, see, I am now explaining it. I have not given this question in poll. So I am explaining it now. Please, I want your attention over here. Work done in moving a charge. Let's suppose you have got a Q charge and you want it to move from point A, which might have some coordinates, to a point B. So what's going to be the work done? See, let's suppose the potential difference between these 2 points is del V. We know that potential difference is actually the amount of work done to bring a unit positive charge from one point to another point. That means work done is going to be this charge Q times change in potential times potential difference. Is it all good? Quickly write down in the chat box. Quick. First chapter is over. This is the second chapter, na? This is second chapter, right? Quickly, is it all fine? Now please understand, they have not said what potential, what is potential, right? So what we are going to do is, we are going to now also study relation between electric field and potential. And this is nothing but, remember, E is actually written as minus dV by dr. Is it all good? Quickly write down in the chat box. Done. dV by dr. So if you want to find out what dV is going to be, it will be E dot dr. And if you want to find out the total potential difference, so just integrate it. So that's what we are going to do over here as well. So please understand. Now you have got electric field. So change in potential will be negative times of 10x plus 4 dot dx, right? And the charge particle is moving from 5 meter to 10 meter. So the limit says from 5 to 10. Please answer in the chat box if you have any doubt. Quickly write down, dosto. Quick. So the particle was at this point, 5, 0, and then the particle is moving to this point, that is 10, 0. Is it clear? Dosto, quickly tell me. And by the way, electric field is in this direction, right? Electric field is in this direction. So whatever the answer is going to be, what does this negative sign indicate? This negative sign basically, how negative sign? Okay, ठीक है. This negative sign basically indicates that electric field is in that direction in which the potential is decreasing. Is that clear? That's how we always draw the electric field. Now, if let's suppose that in this direction potential is in this direction, electric field is, that means the potential is going to decrease in this direction. All right, quickly write down what answer are you getting, and also let me know in the chat box if this is all good. Also, second part, tell me the answer for the second part. Very easy. Sir, why root 2 in question? Where is root 2? I cannot see any root 2 over here. This is going to be, by the way, 5x square plus 4x from 5 to 10, that is 5 times 100 plus 40 minus, this is going to be 5 cube, that is 125 minus 20. Whatever this answer is, dosto, write down what that answer is quickly. Sir, why root 2 in question? Bhai, kahan hai question mein root 2? Where is root 2 in question? I can't see it. I can't see it. Acha, one more thing. What about the next part? Please find out the answer by yourself, but what about the next part? What is going to be the answer for the next part? The next part is saying you want to move it from 5 meter 5,0 to 5,10. That means now you need to move this charged particle in such a way. Please understand, you want to move the charged particle in such a way from 5 meter to 10 meter. So you don't have to solve this particular thing. This is going to be 0. Why? Because now you can see that in the second part, the change in potential difference will be the negative times of E. We write E dot dx. Now over here it was cos 0. Why? Because electric field and the displacement is in the same direction. So over here we are going to write actually E dx cos 90. That means work, there will be no work done. So you don't have to calculate it. So in the second part it will be no work done. Now ask me if you have any doubt, else I'll move on. Two students are saying 395, it must be correct. Minus 395 volt. Can we move on to the next question? Is it clear? We didn't use differentiation. See, if they give you potential, as a function of x, y or z, and they ask you electric field, then you differentiate it. And if they give you electric field and they ask you potential or they ask you the work done, you integrate it. That's why I have written each and everything. 395 is going to be the correct answer. Please check. 395 is going to be the correct answer. Is it clear? Now let's again come back to a theoretical concept of parallel plate capacitor. Acha, by the way, there is also one more thing, which is potential energy of a dipole, right? If you want to actually rotate a dipole by a certain angle, we knew that torque can be written as, on a dipole, torque can be written as Pe sin theta. See, I am not wasting your time and just explaining the very most important parts and the previous year questions, right? So torque is Pe sin theta, fine sir. Let's suppose we want it to rotate. Let's suppose this is an electric field and we want the dipole to rotate from theta 1 angle, from this angle to some another angle, right? So the amount of work done, let's suppose instead of defining it for the total angle, let's say we are defining it for a very small angle. Let's suppose we want to rotate it by infinitely small angle. So that would be torque into d theta. Is that clear? So if you want to find out the total work done, just integrate it from theta 1 to theta 2. If you are going to integrate sin theta, it will be minus cos theta. Finally, the formula for potential energy will come out to be Pe cos theta 1 minus cos theta 2. Alright. So this is also an important part. Please remember it. And sometimes they tell you that theta 1 is actually 0. Sometimes they say, in some cases they say, if theta 1 is 0, right, and they wanted to rotate it after, not after, they want you to rotate it to theta angle, right? So potential energy or the work done is going to be minus Pe cos theta, or that's how you get your potential energy as or work done as P dot E minus P dot E. right? And also please remember all the cases for stable and unstable equilibrium also. This is very important. Clear? Quick. Everything's good till this point? Everything's good. What I was talking about stable and unstable equilibrium, doston. There will be two cases now. Cases are going to be stable. For stable, potential energy will be minimum. For unstable, potential energy will be maximum. So minimum basically means at theta equals to 0 radian, and maximum basically means theta equals to 180 degree or pi radian. Chalo, quickly tell me in the chat box if everything till this point is clear to you. Quick, because now I am moving to parallel plate capacitor. Then we'll again solve some questions. See, from the second part of this chapter, capacitance, parallel plate capacitance is very important. So please understand it. How you are going to write down a definition of what is a parallel plate capacitor? Let's suppose they tell you to define what parallel plate capacitor is. So a parallel plate capacitor consists of two large plane parallel conducting plates separated by a small distance. That small distance can be anything. Is that clear? Right? Quickly, doston. So you have got two plates over here. One is positively charged, another one is negatively charged. If you are going to ask me, sir, what is going to be the electric field, the net electric field inside the parallel plate capacitor, it's going to be sigma upon epsilon naught, and sigma is going to be charge q upon a epsilon naught. Quickly tell me. We all know capacitance can be actually written as q divided by v, right? So q divided by v. Can we write for potential, because this electric field is uniform, and assuming this is uniform. By the way, one more important note for you. If electric field is uniform, in this particular case, write it down. I'll write it down over here only. If electric field is uniform, and you want to write down the relation between electric field and potential difference between, let's say, these two things. This is positive, this is negative. So what you can actually do is you can write potential as E into D. We are just talking about the magnitude, obviously, right? Quickly. Any more doubts? So if you're going to come back over here, you will simply write electric field, which is nothing but q a epsilon naught and d. So that's how you are going to get the formula of capacitance, that is epsilon naught a by d, right? And now all of those things starts if you have got a partially filled dielectric, if you have got a fully filled dielectric, and all the different cases. Tell me if you want me to explain all the cases for dielectrics, right? Either what we can do is we can study those through questions as well, right? Quickly, doston, because when you are going to talk about the dielectrics things, when you are going to talk about dielectrics, by the way, dielectrics are nothing but insulators. First we'll discuss what are polar and non-polar molecules, and why I have kept polar and non-polar, because last year also they have asked some questions from what are the examples of polar and non-polar, right? So if we have got a fully filled dielectric slab of constant K, then the capacitance will become K times of epsilon naught A by D. So this is a very important thing, that no matter what happens, capacitance always increases. Okay. Now for charge and potential, we are going to talk about two different cases, and we are actually discussing it in speed. So please understand. Case one is if battery is connected, now you can remember these cases as, first of all, tell me what is the purpose of a battery. So obviously the purpose of a battery is to supply the charge and maintain the potential difference. So if battery remains connected, this means that I can say that potential difference will be constant. This will not change. And we have already seen that, sir, capacitance will always increase by K times in the case for fully filled dielectric. So this will always increase. So what will happen with charge? So charge is actually Q dash will be C dash into V. V is not changing. So C dash is increasing. That means Q dash will also increase. So it will become Q times of original charge. Is it all good? Now after this, again, next thing is energy. Formula of energy stored in a capacitor is half CV square. You don't have to derive it. Derivation is not in course, so you don't have to worry about it. Half CV square, and remember that C can be written as Q by V. Is that clear? So if you are going to talk about potential energy for this particular case, U dash will be half C dash times V square. So we know that C dash is actually increasing by K times. So this will be half KC V square of, or K times of U. So potential energy is also increasing by K times. Is it all good to you? Right? What is the next case? Next case is going to be second, when battery is disconnected. When battery is disconnected. So if battery is disconnected, we are going to say, now there is no battery, that means there are going to be no new charges which are going to get stored in the capacitor. Is that clear? So charge will get constant. Write down in the chat box if you are getting this. So these are the two most important things. Charge will be constant, and we always say that, sir, capacitance will increase. Capacitance will increase by K times. So what will happen to potential? Potential is nothing but Q dash by V dash. By the way, charge is not changing. So it will be Q by C dash. So that means it will become, V dash will become V by K. So it will get reduced. Do the energy by yourself. Quick. Is it all good? Can we move on? Now let's discuss some polar and non-polar molecules very quickly. Polar molecules are those, basically you are going to define them as in which the positive and negative charges are separated, they are not coinciding. Something like this. You have got positive charge over here and you have got negative charge over here, and the thing is, it is important to remember their examples, and very easy. You might have done these things in chemistry, like HCl, H2O, which has got different electron negativity, right? So this is polar molecules. Next is non-polar. Non-polar molar molecules would be oxygen, hydrogen, in which the positive and negative charges get coincided with each other. What's so special about it? Nothing. It's just that when you are going to actually place them in external electric field, right? Let's suppose this is external electric field, and we'll see one question from it. And let's suppose this was a charge which was kept in an external electric field. It is a polar molecule. A force will act on it, something like this. A force will act on it, something like this, right? And it will get distorted, and after the distortion it will look something like this. And then we have got like many polar molecules over here. So positive charge in this direction, negative charge in this direction. This was the electric field, and the dipole moment inside this polar molecule will be in this direction. So there was one question last year, I think last year or 2023, we'll check abhi. In the assertion reasoning, they said the dipole moment in a polar molecule is along the direction of the electric field, external electric field. True or not? Right? So if you have the concepts, you will be able to do it. Yes, it is absolutely true, because dipole moment is actually along the direction of electric field. Is it all good? Quickly tell me in the chat box if everything's fine. Acha, what will happen if you have got a partially filled dielectric? If you have got a partially filled dielectric, let's suppose the thickness of this is D. This is D, and we are placing a dielectric slab of thickness T over here, of dielectric constant K, right? So the formula for this comes out to be epsilon naught A upon D minus T plus T upon K. Can you derive it? Well, they can ask you to derive it. They have actually in past years quite some time, right? Done. Everything's clear. We are going to cover each and every topic, so we are not going to leave anything and leave any chapter, right? So this is very important. How will you define it? In the same way. In the same way, you are going to say, sir, now also the net electric field will be actually because of two things. One is electric field is actually, see, electric field will be if let's say we are writing potential, let's write net potential. So we will write, one is sigma upon epsilon naught times a region where there is no dielectric, that is the total region minus the region in which there is dielectric, plus sigma upon K epsilon naught times T. That's it. And just write sigma equals to Q upon A, substitute, put it to the value of Q by A, you will get your answer. If you have any doubt, please let me know. Is there any doubt, sir? Derivations are easier. Yes, derivations are easy. Let's move to some more questions. Quickly, doston, let's move to some more questions. We have done quite a few. Acha, by the way, let's see what type of questions are you going to get. Understand. A dielectric slab of dielectric constant K and thickness T is inserted between the plates of a parallel plate capacitor, separation D, obtain an expression for its capacitance. You got it? How you will do it? Please tell me. Quick. Is it all fine? How you are going to solve the first part? Let's look at the second question. I have already explained the first part. Second question says two capacitors of different capacitances are first connected in series. Acha, they are of different capacitances. First they are connected in series, then they are connected in parallel across a DC source of 100 volt. If the total energy stored in the combination in the two cases are 40 millijoule and 250 millijoule respectively, find the capacitance of the capacitors. Is it all fine? Can you please read it? See, I want everyone who are not spamming to also write down. I don't want you to spam, but at least tell me if everything is clear. Can we move on? Please chat with me. Quick. And for all of those students who are constantly spamming, please don't spam. Timing for third chapter is after 5 minutes. We are just starting the third chapter. So don't worry. We are just starting the third chapter. See what this question is telling you. Okay, good, doston. Very good. Let's say the capacitances are, let C1 and C2 are the capacitance of the capacitors, right? Now in case 1, when they are connected in series, doston, C equivalent can be written as C1 C2 upon C1 plus C2. Now please don't ask me, sir, how did you write this thing, right? Obviously, if it is series, we are going to apply the formula 1 upon C1 plus 1 upon C2. So energy, in this case, the energy will be half C equivalent CV square. By the way, V, if I am not wrong, it was 100 volt. It was 100 volt, right? So half CV square, 100 CV square, and this energy is coming out to be 40 millijoules, right? So 40 millijoules. So this is 40 into 10 to the power minus 3. So this is your equation number 1. This is your equation number 1, right? Case 2 is, what can we do from this particular thing? We'll see, we'll check. Case 2 is when they are connected in parallel. So in that case, C equivalent will be C1 plus C2. And that, I think that was 250, sorry, that would be 250 millijoules. So 250 times 10 to the power minus 3 is equals to half C1 plus C2 into 10 to the power, sorry, into 100 square of 100. Okay, so now hopefully now you have got it what we were trying to do. Quickly tell me. Quick. Is it all good? So you have got two equations, you have got two unknowns, find out the answer. Quickly. Half C1 C2 upon C1 plus C2 times 100 square is equals to this, and 250 millijoules is equals to half C1 plus C2 into 100 square. And this was your question. Please read it again. We have used each and everything, two capacitors of different capacitances. That's why we have taken C1 and C2. Please write down the answer. What answer are you getting? Quick. Find out. Quickly दोस्तों, find out the answer for C1 and C2. Sir, yes, you have to find C1 and C2. But this is not that difficult. See, what you can do is, you can simply write this thing as 500 into 10 to the power minus 3, and you have got 4 over here as well, right? So this will be minus 7. Is that clear? This will be 500 and this will be 10 to the power minus 7. This will be your C1 plus C2. Or what you can do is, you can write C1 plus C2 as 5 into 10 to the power minus 5. You have, as soon as you have got your C1 and C2, again substitute it at this point. So you will get this one was, by the way, 80 into 10 to the power minus 3 into 10 to the power minus 4, right, into C1 plus C2. I am going to cross multiply this C1 plus C2 on this side. So I will get 5 into 10 to the power minus 5 is equals to C1 C2. Now you have got C1 C2 and you have got C1 plus C2. So I will tell you what to do. What you can actually do is, now you can write C1 minus C2 whole square is equals to C1 plus C2 whole square, right? So this is going to be nothing but C1 square plus C2 square minus 2 C1 C2, and you are going to get, so you write minus 4 C1 C2. Okay, that's it. Now you can do it. I have explained enough. This is the last thing. First, find out what C1 plus C2 is. Substitute over here. Find out C1 into C2, and this is something that you need to know. This is where many of you might be able to feel that, okay sir, after this I don't know how to solve it. The reason is that the trick is just a small algebraic manipulation. Got it? Quick. If you have any doubt, write down in the chat box. If you have any doubt, write down in the chat box. I'll help you out. Can we move on? Can we move on to the next question? Chalo, let's move on. Acha, see, let's check one of the comprehension type questions. These are those questions in which you will get a passage first, and then there will be 3 or 4 or 5 questions about the same topic. We have already learned whatever there was in dielectric. They are saying dielectric plays an important role in design of capacitors, the molecule of dielectrics may be polar or non-polar. In both of polar and non-polar, same thing happens. It just the effectiveness of polar molecule would be more. When a dielectric slab is placed in an external electric field, opposite charges appear on the two charges of the slab perpendicular to the field. Due to this, electric field is established inside the dielectrics. Hopefully you are getting everything. Now I have explained this thing. The capacitance of the capacitor is determined by the dielectric constant of the material that fills we know everything. Let's move to questions. Which of the following is a polar molecule? Polar molecule would mean that the center of mass of those atoms must not coincide, right? So if it is polar, it can't be O2, H2 or N2, like similar kind of thing. So it has to be HCl. Is it good? Quickly tell me, is it good? Right? Where are you all? Quickly. D is correct. Good, good, good. Let's move on. Let's look at this one. Which of the following statements about the dielectric is correct? A polar dielectric has a net dipole moment in absence of an external electric field which gets modified due to the induced dipoles. So the thing is, a polar molecule has got net electric field, right? But in totality, if you are going to say the sir, what do you mean by this polar dielectric? Individual atoms have got dielectric. Let's suppose individual atom has got dipole moment in this particular direction, right? And there is no electric field. So there must be another atom which will have dipole, any other pair which will have dipole moment in this direction. So it is quite random. So the net dipole moment is actually 0 when there is no electric field, right? So statement 1 is wrong. The net dipole moment of induced dipole is along the direction of the applied electric field. Can you please check? Quick. Can you please check the net dipole moment of the induced dipole? So let's suppose that's what we did a few minutes ago. Let's suppose this is the electric field, right? And this is a distorted molecule, let's say polar molecule, although I said that in non-polar also this will happen. So a positive charge will be on this side, a negative charge will be on this side. It will have its own electric field, right? And but the by the way, this was positive now, so this is going to be opposite of this. This is going to be negative, this is going to be positive. So the dipole moment will be along the direction of the electric field. Is it clear? That's what we said. So statement 2, again read it. The net dipole moment of induced dipoles means that the dipole moment that these molecules got after the electric field was applied is along the direction of the applied electric field. This option is absolutely correct. Tell me in the chat box if this is all good to you. Good. Everything's fine. Dielectrics contains free charges. No, they don't contain free charges, right? The electric field produced due to the induced surface charges inside the dielectric is along the external electric field. No, it is not along the external electric field. It is opposite to the electric field. See, there are two things. Dipole moment is along the electric field. The electric field which is inside the polar molecules is opposite to the applied electric field. That's why the net electric field gets reduced. Now, let's suppose you have applied electric field as you applied E0 electric field. So this is E0. And the electric field due to all the polarization came out to be in this direction. And it came out to be EP. So the net electric field will be E0 minus EP. Although this is very small, but still it reduces the net electric field. Got it? Chalo, let's now move to our next chapter. But oh no, we have got few questions more. Let's solve this one. Quick. I am starting the poll in this one. Starting the poll in this question. Let's quickly start. When the dielectric slab is inserted between the plates of an isolated capacitor, the energy stored in it, what happens to it? Quick. Do it by yourself. Yes, you are going to get the PDF for this one. Come on, quickly solve. C1 C2 wala. Let's buddy, please once again try that. That has, I mean, after that manipulation there is nothing left in that question. By the way, for this one, if you are going to when a dielectric slab is inserted between the plates of an isolated charged capacitor. So isolated charged capacitor, I am considering that charge will remain constant. Is that clear? So that means potential will go down and capacitance will increase by k times. So if I am going to write half C V square, this whole thing is going down. So decreases and the electric field increases. Think about it. What will happen with the electric field? Decreases and the electric field also decreases. Quick, quick, quick. Tell me the answer. Electric field will also decrease, na? If potential is decreasing, then electric field will also decrease, right? Acha, why I have considered the case for Q to be constant? Because they have said that we have taken an isolated capacitor. So we are considering that there is nothing other than the capacitor. So decreases and electric field also decreases. And both decreases by k times. Cool. So option B is correct. 86.36, very good. Siddharth, Sanjay, Kush, Ayush, Smriti, Kamlesh, Hilaria, everyone else. Very good, dosto. Let's move on to the next one. Quick. This is part of the same passage, previous year question. An air filled with plate area A and plate separation D has a capacitance C naught. A slab of dielectric constant K, area A, thickness D by 5. That means it is a partially filled question. Alright. How to attend poll? Just write down the answer in the YouTube chat box. The question is saying the capacitance of the capacitor will become, see, these questions are pretty easy. All you have to do is, it will be epsilon naught A by D minus T plus T by K. That's it. Okay. So now let me apply it. Let's not use pole for this one. So D minus D by 5 plus D by 5, and I think dielectric constant is just given as K. This is K. Tell me if you have any doubt. Hopefully now you can solve it, right? Clear? Everything's clear? C is the correct answer. Can we move on? C is the correct answer for this one. Okay, I am believing you all. C is the correct answer. Whatever it is coming. Okay. Now let's move to the next question. Acha, theek hai. Let's see. So let's look at some theoretical questions as well. Draw an equipotential surface for an electrical dipole. This was from the last year, right? So please remember that whenever you are going to get of drawing equipotential surfaces, draw it very carefully. Let's suppose you have got two charges over here. Acha, if someone tells you to define equipotential surface, you can do it, right? And similarly on that side also. So equipotential surfaces are those surfaces which have same potential. And always remember that electric field is perpendicular to these equipotential surfaces. Other than that, obtain an expression for potential energy. Hopefully you can do it. Quickly tell me if you can solve the second one. How many of you want me to solve the second part of 2-point charges? Draw the same diagram for this one for over here as well. For the second part, 2-point charges Q1 and Q2 are located at R1 and R2 respectively. We have to find out the expression for potential energy of the system. Can we do it? Please understand. See, I'll explain it. This is the system, let's suppose Q1 and Q2, right? Acha, by the way, they are also saying that are located at R1 and R2 respectively in an external electric field. That means if I'm going to talk about this now, this is going to be R vector. This is going to be R, the displacement vector between these two. I'm not drawing the entire diagram. If you'll ask me what is going to be the net work done in this case, so I would have said very easy, that is the potential energy. It is K Q1 Q2 upon R, this R, absolutely. But this is the case when there is no external electric field. When there was no external electric field, at that point when you were actually bringing this Q1 to this point, there were no charges. So there was no work needed to bring this charge. But when there is an electric field, you will have to actually do some work to bring this charge as well, right? So work done because of electric field in bringing charge Q1 plus work done by electric field in bringing charge Q2. Is it all good? Can you please tell me if everything's clear? Quick. Everything's fine? So that's what you need to do for the second part. Tell me in the chat box. Now let's talk about the third part. Third and last part. They are saying the dipole moment of a molecule is 10 to the power minus 30 coulomb meter. It is placed in an electric field of this such that its axis is along the electric field. The direction of E is suddenly changed by 60 degree at an instant. Find the change in potential energy. So change in potential energy would be initially it was along the electric field, right? So change in potential energy would be final potential energy minus initial potential energy. So finally potential energy is actually minus PE cos 60. This will become PE cos 0. Find it out and tell me whatever answer are you getting. Dosto, quick, let's move now. Hopefully everything is clear till this point. Come on. Everything's fine? Easy peasy, not going to solve it. Two capacitors, each of capacitance 1 microfarad are connected in parallel. Total energy stored. Very easy. First find C equivalent, then find energy formula. Right? Put the energy formula. Right? Very easy. Hopefully we can move on. Moving on. Let me check if you have got anything which is the second part of this, because we have done the first part. Second part of this. Take a look. Last question, then we are moving to current electricity. Last question, then we are going to move to current electricity. An electric dipole consists of a point charges -1 and +1 picocoulomb located at 0, 0, 3 millimeter, 4 millimeter respectively in XY plane. The electric field is something like this. It's switched on in the region. Find the torque acting on it. Quick. Jasmine, I can't because this is a pure English medium channel beta, so I can't explain question in English, in Hindi. ठीक है? Hopefully you can manage. Quick. An electric dipole consists of a point charges -1. Let me draw it for you. This is, the question is saying, we have got -1 and +1 at 0, 0. So at this point we have got -1 picocoulomb, and at 1 at 3 millimeter, 4 millimeter दोस्तों. So 3 millimeter, 4 millimeter is somewhere over here. We have got another charge which is +1, obviously picocoulomb. This is in XY plane, right? So if you will ask me what is the direction of dipole moment, this is going to be the direction of dipole moment दोस्तों. Is it clear? You know why? Because when they are going to talk about torque now, you are going to write something like Pe sine theta. So you must first understand in which direction this P vector is and in which direction E vector is. So we can see that 100 volt per meter, don't get confused by when they write something as volt per meter, it is in I cap. That means this is the direction of electric field. This is the direction of electric field. Can I find out this angle? Of course, this point was 3, 4. So that means this is 4 and this is 3. So this is going to be 53 degree. Is it clear? Write down in the chat box. Quick, quick, quick. Yes, this is going to be more than sufficient for your board exam. At least if you're talking about the three, I mean, this is the best, one of the best way to revise, right? That's what I'll say. Chalo, is it all good? So the angle between P and E is actually 53 degree. Now there's nothing left. Let's start current electricity. Let's start current electricity. Third chapter. All right. Quickly, without wasting any time. Hopefully, till now, I have actually explained many questions and many concepts from the first 2 chapters. So we have almost covered it. You tell me which part we have left, right? So in like 2 hours, roughly 2.5 hours, we have completed the first 2 and we have not left anything. See, if you want to increase more speed, then we'll have to leave something. Henna, I don't want that. I just want your today's time. Today is 18th. Revise everything with me. Ask whatever doubt you can on the live chat, and please don't spam. Next is tomorrow and day after tomorrow. I've made a video for strategy how to actually utilize the last day's time and do that, right? Quickly now let's move to current electricity. See, in current electricity, I don't want to waste a lot of time, right? We all know current can be written as dq by dt. This is instantaneous current. Current is a scalar quantity. Why it is a scalar quantity? Hopefully they will not ask it, but in most of the books it is written as it obeys vector law of addition. Not the best answer, but still you can remember that. This is what current is, right? Again, same thing here. If someone will talk about the graphs of this one, if you have got graph of like time and charge, the slope of this QT curve will give current. Slope of this QT curve will give current. And if someone asks you to find out the total charge, integrate I dot dt. Is it fine, dosto? Is it absolutely fine? Now, if someone asks, what do you mean by, sir, current density? Current density is quite tricky for me. Let me explain it. Let me make it really, really easy for you. See, current never changes in a wire. No matter what shape or length of the wire is, current will never change, right? If obviously under the same physical conditions, voltage and everything else is remain same. So the current will not change in a single wire. Let me say something like that, right? So let's say current is I in this particular case. Dosto, let's suppose current is actually I, and I want to find out the current density. So the easiest example or the very general example, a very specific example is something like this, in which you say, sir, I have taken a area something like this, because current is nothing, current density is nothing but this is current per unit normal area. Are you understanding it? It is current per unit normal area. That means in this specific case, in this specific case, current density was I divided by area and cos 0. But generally they are not going to give something like this, so this is the general case. So current can also be written as dot product of J dot A. And that's how also you can see that current is going to be a scalar quantity. Is it all clear? If someone tells you to draw another diagram for this, you can actually draw a diagram in such a way. Please understand, now this area has been rotated by an angle of theta. So now this area vector is A over here. Is it good? Quickly tell me in the chat box if everything's cool. Cool. All right. Chalo, let's move on. Let's move on to the next one because we have completed some basic tiny topics. Now let's talk about drift velocity. See, now again, the basic concepts is it will take a lot of time, although it's not that difficult, but still, if you have got, okay, good, very good, dosto, that's the spirit. If you have got a conductor, if you have got a metal piece over here, and this metal piece is kept at room temperature and there is no external electric field, right? So electrons moves in random direction. Please understand the theoretical part because they might ask some a certain reason from this particular thing. This topic is quite good for asking conceptual questions, right? Not really complex conceptual questions, but basic conceptual questions. So electrons moves in random direction, one thing, with very high speed. So the average speed is quite high because they are moving, they are literally moving in random direction, all because of thermal agitation. When we apply an electric field, when electric field has been applied, then we talk about something that is called as drift velocity. And then drift velocity actually goes really down. It is a very small value. The formula, do I derive also drift velocity for you? If you want me to derive it, it's quite simple. We'll simply write that force acting on an electron is actually equals to minus E times E, which can be written as mass of electron times acceleration of electron. So acceleration of electron will be minus E by m. If you want to talk in vector sense, put up a vector sign over here. This is the acceleration acting on an electron. Now we say that, sir, there are n number of electrons. There are many electrons. Let's talk about each one of them. So we are going to say, let's take one electron. Let's say that this electron was initially it was moving in this direction. So this is its initial velocity. And now suddenly we actually switched on the electric field. So now let's suppose that this is positive side, this is negative side. So this electron will experience an electric force in this direction, right? Clear? Because of which its velocity will change, and let's suppose its velocity changes to v1. Acha, what happens after that? And what is this t1? Its velocity changes, it moves, and then it collides with another electron or another fixed positive ions. And the velocity with which it gets collide, with which it actually strikes another particle is v1. And the time to travel the free path, right now I'm not going to talk about mean free path, this is just a free path because we are talking about only one electron. The time taken by the first electron to travel this free path was t1. So after t1 it got collided. So now I've got like n number of particles over here. I mean, I would suggest you to write for one more. I'm just simplifying it. So Vn would be actually equals to Un plus A into Tn. Acceleration will be same for everyone, for every electron. Now, after this step, we'll add all of these things and we'll take an average of it. So if we'll take average of it, this will become Vd, What do you mean by average of it? I mean to say V1 plus V2 plus V3 and so on, Vn whole divided by n equals to, same thing will happen over here as well, and this will come out to be 0. Acceleration can be taken out, and this T1 plus T2, this thing will be written something like this. So this is drift velocity Vd in vector form. Acceleration is minus E by m, and the value of this thing is actually known as relaxation time, denoted by again the symbol tau. So minus E tau by m. All right, quickly doston, write down in the chat box. Quick. Everything's clear? How many of you are getting it? Write down in the chat box if this is all good to you. Relaxation time, this is the average time between two collision. Average time between two collisions. Alright, other than that, everything is cool. If you are going to increase the temperature, one very basic kind of a thing, if you are going to increase the temperature, relaxation time will actually go down. But if you are going to increase the temperature, thermal agitation will increase, and if thermal agitation will increase, they will collide more often, right? More quickly. So average time will go down. Got it? So now let's move on to the next part. Acha, some of the few important notes over here. It is property of the material which indicates the average time between two collisions. It's if temperature is increased, then tau is going to decrease. The order of the drift velocity is 10 to the power minus 4 meter per second. Everything's cool. Can we move on to the next part? Good. Acha, before this, there is also a very important thing, which is a relation between Hello, everything's good? Next thing is relation between current and drift velocity, which comes out to be actually I equals to NEAVD. Remember this relation, and let me know if you want to know its derivation also. Quite an easy derivation, but first let's move on. So till now we have got two things. We have got two things. If we are going to talk about Ohm's law, we have got two things over here. One is current can be written as NEAVD, by the way, where N is, in this particular formula, N is the number of electrons in 1 meter cube of volume. Number of electrons in 1 meter cube of volume, right? Also Vd is E tau by m. I'm just talking about the magnitude, not using the direction, not using the signs. So I'll get, if I'll substitute this, I'll get NEA times EE tau by m, right? After this, everything's cool. We'll simply say that I equals to NE square tau by m into A. Acha, electric field can be written as potential upon length. What length, sir? What are you really talking about? What are these things? We are assuming that we have got a cross section of wire, something like this. That's what you do, na? That's what you, before starting Ohm's law, that's what you always say. Let's suppose I have got this, and let's say this is positive potential, negative potential. These electrons are moving with drift velocity Vd. N are the number of electrons per meter cube, and the length is L, area is A. Now tell me, everything's clear? Do you want to ask anything? Got it? Done? Acha, if this is the case, electric field between these 2 points can be written as change in potential difference, just the potential difference divided by L. Is it clear? Potential difference divided by L. So this thing will be V by L. Now after this, let's rewrite it all over here. And please write down in the comment section if everything's cool. So V will be ml divided by ne square tau into A times I. That's it. This is your Ohm's law. This is your Ohm's law. This is the proof of Ohm's law. This is the proof of Ohm's law. How do we know that? We can see that potential is directly proportional to current. So we start stating Ohm's law something like under the same physical condition in which we say that we are not going to change the length of the wire, right? We are not going to change the temperature in which this experiment is taking place, right? If we are not going to change the wire, m is basically the mass of electron, it will never change. L is length of the wire, we said that we will not change it. N is the number of electrons per unit volume, it is a property of a material, it is also not changing. E is electron charge, tau is relaxation time, it depends on temperature, we said that we are not going to change it. A is area of cross section, it is also not changing. So that means V is directly proportional to I, because everything other than these two is a constant, and this is actually known as resistance, which we can rewrite this thing as ml divided by ne square tau by A. So resistance, again, not going to bore you with the definition of resistance. You know, it's a property of the wire to offer hindrance to flow of current. Or if you're going to look at this formula, again, resistance depends directly on length and inversely on area, because m, n, e and tau will again be a constant if you are going to say that we are talking about the same physical condition. Is that clear? Yes. No, temperature coefficient is not deleted. Temperature coefficient is not deleted. Alright. Quickly tell me in the chat box. Please, quick, tell me in the chat box if everything's clear till this point. So this means that resistance is directly proportional to length, inversely proportional to area. This implies that the proportionality constant in this case is resistivity, which is m by ne square times tau. Right? Everything's cool, dosto. So which further means if you are going to look at the resistivity and tau, they have got an inverse relation, right? So resistivity depends inversely on tau, which for conductors and basically for everything depends directly on temperature. So if you are going to increase temperature, resistivity will increase because of temperature. But now we are going to also talk about something that are called as semiconductors, right? Quickly here, doston, tell me if in the chat box if you have any doubt. Acha, also see, all of these things are from your NCERT. That's what I have done. So if you are going to complete my class, you won't have to actually, you will be able to glance through the NCERT. So whenever I saw some graph on NCERT, I try to include that, right? So I'll come back to that resistivity, temperature and all of those things, but please see here that there are certain limitations to Ohm's law. This is a graph for semiconductors, you know it, right? Now don't tell me, sir, we don't know what semiconductor is. Okay? So this is semiconductor, this is forward bias, this is reverse bias. We can see that V is not directly proportional to I, right? This is something that is called as for diodes, right? All right. Resistivity does not depend upon dimension. Yes, it does not depend upon the dimension. That's absolutely clear. Now let's come back to temperature dependence of resistivity. So we have got a very simple formula over here. The formula is something like rho equals to rho naught times 1 plus alpha delta T, and we have seen some questions also from this particular formula in past few years. So this is actually important. All right, I'll mention each and everything. This is actually resistivity at T2 temperature. This is initial resistivity. This is resistivity at T1 temperature. This is temperature coefficient or coefficient of temperature, and this is change in temperature. Tell me, right? If you're going to ask me, sir, what is this alpha? I'm going to say that alpha can be actually written as, please see, this thing can be written as rho minus rho naught divided by what, dosto? Divided by rho naught into delta T. Which means that alpha will tell you the change in resistivity, right? For per degree Celsius. Its unit is going to be, if you will closely see, its unit is going to be just 1 upon degree Celsius. Because resistivity and resistivity's unit will get cancelled out, and this will come out to be 1 upon degree Celsius. If you are going to talk about alpha for conductors, that means for all metals, alpha is positive. For semiconductors, alpha is negative. What do we mean by this? Going really fast, so you will have to actually pay attention. Huh? Now we'll again come back to what we have done in our resistivity formula. If you remember, the resistivity's formula was m divided by Ne squared tau, right? Can we write it down over here? Resistivity was m divided by Ne square by tau. This was the formula. Acha, what does this means that for semiconductor alpha is negative? This means that if alpha is negative, this means that rho is less than rho naught. Is that clear? This basically tells you that resistivity is inversely, resistivity is inversely dependent on temperature. And this tells you that for conductor, resistivity is directly dependent on temperature. Why so? See, there are two factors which are working over here. One is relaxation time. Another thing is this number of electrons per unit volume. Now you are going to say that, sir, but the number of electrons per unit volume is constant. You only said this. The thing is, it is constant for conductors. It is constant for conductors because in conductors we have got all the possible number of free electrons that we need, right? If you are going to even increase the temperature, it's not that we are going to get some more electrons. That number is already saturated, we can say, or not saturated. There is going to be no difference. You know, band theory, that already the energy difference between the conduction band and the valence band is 0 in conductors, right? So we'll see no difference in N, but we'll see a difference in relaxation time. Relaxation time will go down as you increase the temperature. So something is going down in the numerator, so the whole number will increase, right? So that's why resistivity increases. Similar thing happens in semiconductor also. The only difference is there is also one more factor of number of electrons per unit volume. When you increase the temperature, now there are many electrons in the valence band which were not initially able to jump to the conduction band. Now they will be able to jump to the conduction band, and suddenly this factor of N will overpower the other factor of relaxation time. So we say that semiconductors resistance go down as we heat them. Okay, everything's cool. Can we move on? Can we move on to some questions? Quick. Very important. Let's quickly move on. ब्रेक मिलेगा ब्रेक जब अपन फर्स्ट पार्ट कंप्लीट कर लेंगे एनसीईआरटी का. Alright, so now we have got some important notes, and these all are from NCERT. So that's what I have done. I have brought these important points from NCERT. So these are going to be really important for your 1 mark questions. Alright. Metals have low resistivity. Just remember the order. Just remember the order. It's from 10 to the power minus 8 to 10 to the power minus 6 ohm meter. Acha, I have not wasted your time in telling you resistivity unit kya hai, what is the unit for resistance, what is the unit. I have not wasted your time. Hopefully you know all of those things. Is it clear? So now insulators like ceramic, rubber, plastics have resistivity 10 to the power 18 times greater, this is not the order, 10 to the power 18 times greater than that also, you can actually find it out. It will be 10 to the power 10 ohm meter. For metals, alpha is positive, hence with increase in temperature resistivity increases. Hopefully you have got it. Acha, this is now very important. Alloys like nichrome, manganese, constantine exhibit a very weak dependence on resistivity with temperature. So that means their resistivity are not going to change rapidly with increase or decrease in temperature, right? Hence they are widely used in wire bound standard resistors, since their resistance values would change very little with temperature. Is it all cool? Good. Very important, you can actually get it, okay? For direct questions. For semiconductors like carbon, in carbon we basically talk about graphite and also silicon. Insulators and electrolytes also alpha is negative. This is very important, alpha is negative for these things as well. Everything is cool. Quickly dosto, can we move on? Quick. What else? What else do we have from the NCERT? The heating element devices like heater, geyser, electric iron, usually known as a press in India only, are made up of nichromes. Okay, so this is actually very important. These things are made up of nichrome because it has high resistivity and high melting point. So you need both the things. And this is related with Joule's law of heating. You need high resistivity because we know that Joule's law says that heat will be directly proportional to the resistance as well. And if there will be a lots of heat, its melting point should be also quite high, right? It does not react with air and acquires a steady state when red hot at 800 degrees Celsius. Fuse wire, another important thing, fuse wire is made up of tin lead alloy because it has got low melting point. Why we need a low melting point? Why we want it to use an electric fuse as a preventive device, na? So we would want that before our appliances gets damaged, the fuse wire should burn and it should break the circuit. Very simple logic. Okay, so the resistances of resistance box are made up of, this is all done. This is all done, dosto. Can we move to now questions? Because I have explained the theoretical part and now all of those KVL and KCL, let's do it from questions. Because if I'll even explain the numerical part in theory, then what's the difference, right? So I have completed the theoretical part. Now wherever we are going to get the questions from theory part, either we'll quickly do it and we'll move, else I'll leave it because I've already explained everything. Let's quickly move on to some numericals. Quick. First question from last year. Sir, EMF. EMF is, I'll talk about the EMF from questions. Let's not talk about all the theoretical parts of EMF. I'll explain each and everything from EMF. Okay? Acha, by the way, is this from EMF? This is from EMF. A battery supplies 0.9 ampere current through a 2 ohm resistor and 0.3 ampere through a 7 ohm resistor. When connected one by one, the internal resistance of the battery is. Is it everything's fine? What the question is saying that, by let's suppose if you have got a circuit like this, and you have got a battery. It has got some internal resistance. See, you are talking about EMF now, I am explaining EMF. Let's suppose it has got EMF E and you have got an internal resistance, you have got an external resistance over here, which is also known as load. It is saying battery supplies 0.9 ampere when connected with 2 ohm. So in one case it is 2 ohm, in another case, dosto, it is 7 ohm. Okay? Now what is the concept behind EMF? EMF of a battery or a cell is the potential difference between the electrodes of the battery, or what you can say, it is the potential difference across the battery in an open circuit, right? So you will simply write that EMF is actually equals to V plus I into R. Is it clear? So this is the case, although you don't need to use this, because why? You will simply say that right now R equivalent in case 1 is actually nothing but 2 ohm plus R. So current will be the total EMF of the battery, which is 0. Let's say which is E divided by 2 plus R, and this thing is coming out to be 0.9 ampere. And in the second case, we are saying that now the current is, let's say this is I dash, E will remain same. Now we have changed that to 7, internal resistance will remain same, and now the current is coming out to be 0.3 ampere. Is that clear? So can we equate these two E's, right? So I'll be left with 0.9. You could have directly done it, right? You could have directly done it because I have not explained EMF. I am explaining all the steps. 0.9 times 2 plus R will be actually equals to 0.3 times 7 plus R. You can cancel out these points from here, right? This will be 3. This will be 6 plus 3R equals to 7 plus R. So R would be actually 0.5. Right? So in your school, in your board exam after 3 days, you can simply write down this one equation for multiple choice. That's it. Is that clear? So 0.5 is the correct answer. Very, very good. Great. Chalo, let's move on. Acha, let me now explain 2 or 3 different things regarding this EMF. If someone tells you that what is this thing, what this voltmeter will measure, this voltmeter will measure terminal potential difference or terminal voltage. This will measure terminal voltage. All right, got it? So terminal voltage is basically V equals to E minus IR. Obviously, it will be always less than EMF, right? Moving on, quick, without wasting any time, let's move on to the next question. When electrons drift in a conductor, it does not mean that all the free electrons in the conductor are moving in the same direction. The drift velocity is superposed over large random velocities of electrons. Think about it, do it by yourself. I'm starting the poll, 60 seconds. Come on, explain everything about the drift velocity. Quick. Share the, I'll share it. Can we do it? So almost every one of you are either saying A or B. Some of you are also saying C and D, right? So the thing is, when electrons drift in a conductor, it does not mean that all the electrons are moving in the same direction. This is absolutely correct. Although I might not have emphasized on this fact earlier, but still, all of those Yakin student might remember that I specifically told you that these electrons don't move like any other. I mean, obviously, whenever you are going to talk about the subatomic particles, all of those things that you have learnt in kinematics, mechanics, those all of the things breaks, right? So this is not the absolutely correct idea. What we can actually understand is that these electrons are not moving like this. They are moving for a particular time, then they are getting collided with another particle, and then that's how it's going, right? And also not they are moving in the complete straight direction. So statement 1 is absolutely true. If you have any specific doubt, please you can ask. It should be doubt, don't ask me to explain all over again, right? The drift velocity is superposed over a large random velocities. This is absolutely true. That's what we did. And I think according to me, it is a good reason for the first statement, right? So if both A and R are true and reason is the correct explanation, A, we are going to mark it down as A, not B. How else you are going to explain that thing? Or I mean, you might come up with a more good reason, but still this one is also good. A is going to be correct. 58.82. Okay, Karan, Siddharth, Kevin, very good doston. Let's move on. Let's move on to the next question. What about this one? Now some people will say that, sir, this particular question is from combination of resistors, so it's not in course. What I'll suggest is this is both, it is combination of resistors as well as it is KVL and KCL, right? Now that Akash is saying, he has actually raised a good point. He is saying, but the reason is not explaining the direction part, right? So they have said that it is random. Now, so that random meaning, the random thing has got its meaning, that they must be moving in random direction. Okay, the force is acting in a particular direction. Is that clear? Good. So for this particular part, we have to find out the current in branch BM. So what we'll do is we'll first simplify this circuit. All right, and whenever you have got things like this, now see, okay, if it seems complex, I'll break it down and I'll make it easy. That's my job. Your job is to pay concentration. Okay. Whenever we see questions like this, which looks like a ladder based question, always start from the end. Always start from the last part. So the last part, if you are going to see last part, this R, 2R and this R, these are in series combination. How do we know that? See, whatever this current is going to be, na dosto, whatever this current is going to be, this current will travel, all three resistance will have same current. Is that clear? All three resistance will have same current. That means this will become 4R. This will become 4R. Hopefully everything's good. Everyone's good with this thing. So this will become 4R. Now this 4R, this 4R and this 4R, these two resistance will become in parallel because they are connected in between same points. Is it good? So whenever you see 4 and 4 or R and R, it becomes R by 2. So that means now we are going to say that the equivalent resistance becomes two R. Right? Again, this 2R and this 2R will again become 4R. So again, I'll have a resistance of 4R over here. Then again, this 4R, achha, I am not writing specifically 4R, but you know, this will again become 2. So this will again become 2. Is it all good? Quickly tell me in the chat box. Quick. We'll have to use loop rule, but first we'll have to simplify it, na? Simplification was fine. Simplification was fine or not? Tell me. So now we have got this circuit as something like this. We have got a battery over here, which is actually 6E. Then you have got 4R. And you have got 2 ohm on this side. You have got 3 ohm on this side. You have got 10E, something like this. That's it. This is your circuit. Done? Repeat. Shall I repeat this? I'll repeat it once again now, but please, in 5 seconds it will get again completed. This is in series, last part in series. R, 2R, R becomes 4R, 4R, 4R becomes 2R, 2R, 2R becomes 4R, 4R, 4R becomes 2R, 2R, 4R, that's it. This was the last part. Okay, clear? Now please don't spam. I did what you were asking. Okay? So now the thing is, let's suppose that we have got I1 current from this branch and we have got I2 current from this branch and we have got I1 plus I2 current in this branch. See, this is the thing where you can actually assume anything. So you don't have to worry about, you can assume anything. Is that clear? Clear, clear, clear? So this is I1, this is I2 and this is I1 plus I2. So you have got two unknowns, two equations. We'll write two equations and we'll get to our answer. Okay, it's not that big. I'm also talking in between. That's why you must be thinking that it is taking too long. But please think about it again. Simplifying this circuit hardly took like 10 seconds. Is that clear? Bhai, what's problem with you guys? Yeah, why are you spamming? If you don't want to study, you have the whole internet. Huh. Sir, you told series and parallel. Bhai, series and parallel is not in course, but they can give you series and parallel mixed with KVL and KCL. Okay? They can give you. So now the thing is, let's suppose that this is your final question. Okay? If you are thinking that this is not in course, so assume that this is your final question. I'm quickly writing the equation for all of you. Let's say this is point A, this is B, this is C, D, E and F. This is very important to first name the points so that we can actually name the loop. So now we are saying that applying KVL across loop A, B, C, F, A. Alright, and I'm going to write it down, so please clearly see. And I'm going to start from here. Whenever there is a potential drop, I write it with a negative sign. Wherever there is a potential gain, I write it with a positive sign, and potential drop, negative sign. So we move in this direction, there is a negative, then positive potential, right? So there is a increase in potential. So I'll write it with 10E. Then I move, we'll pass through resistance along the direction of current. So there will be potential drop minus 3I1. Then we'll again move along the direction of current from 4R and the current is I1 plus I2. So minus 4I1 plus I2. And when we reach back to the same point, not before leaving this thing, this is again potential gain. So plus 6E and then E equals to 0. So this is your first equation. Tell me if you have any doubt. Quickly, quick, dosto. Yes, I'll solve prism question also when we'll reach to that topic. Okay, not before that, of course. Is it all fine? We have applied KVL in this one. Now let's apply the KVL in the second loop. If you have any doubt in KVL, do ask in the chat box. I'll reply. KVL across loop. Let me say CF. I can do anything. CF EDC. So now again I'll get minus 4 I1 plus I2 plus 6 minus 2 I2 is equals to 0. You have got two equations, two unknown, and not that difficult. Okay? Quickly tell me if everything's okay. I'll let you solve. Dosto. Let me know if everything's fine. Then we'll move on to the next one. Clear? Yes, you could have also used KCl over here. You could have also used KCl over here, right? But ठीक है, I'll not use another what we can say method to solve the same question. Let's move on. Hopefully you will get the correct answer after this. Let's move to the next question. Let's solve this one. See, from resistivity, the temperature at which the resistance of the wire made up of silver will be twice its resistance at 20 degrees Celsius. Acha, they are also saying take 20 degrees Celsius as reference temperature. Even if they would have not said it, we would have done the same thing, है ना? So let's say that resistance at 20 degrees Celsius is R or R naught, right? And find the temperature. So we want to find out the temperature at which this becomes 2 times R naught. Very easy peasy. So 2 times R naught equals to R naught into 1 plus alpha. Alpha is what? Temperature coefficient is 4 into 10 to the power minus 3, and delta T will be actually T minus 20. Can you solve it? R naught can be cancelled out, so we don't have to worry about it. So this will be 2 equals to 1 plus 4 into 10 to the power minus 3 times T minus 20. Tell me in the chat box if you have any doubt. So this will be 1 into 10 to the power 3 divided by 4 equals to T minus 20, whatever answer you are getting after this. So what you can do is actually you can write this thing as 100 divided by 4 times 10, right? This will become 25 and this will become plus 20. So this will be 270 degrees Celsius. Is this the answer? Quickly tell me in the chat box. 270? Or yeah, they have not asked in Kelvin. If Kelvin, then add 273, fine. Quick. सर तमिल तो आती ही नहीं है. Quick. Chalo, very good. Let's move on to the next question. Acha, what about this one? From 2024. By the way, last question was also from 2024. Till here we have just solved the question from last year, not from 2023 yet. Okay. Consider the circuit shown in the figure. The potential difference between the points A and B is, all right, between points A and B. So this is, you know what this is? This is actually, you can solve this question using combination of cells. Combination of cells, right? Quickly do it. Quick. Sir, please give a 15 minutes break. We'll take some break, but after some time. Surely we'll take some break, but not now. Acha, solve it using the direct formula. What I'll also suggest, if someone doesn't remember the direct formula, just remember that the potential difference between these 2 points will remain same. Potential is going to be same. And what is that potential difference? Let's suppose this is current I1 and this is current I2. So you can solve it by writing the terminal potential difference between these 2 points. Else just write down this is 12, this is 6, the net is going to be 6 and this is going to be EMF is going to be 6 and your internal resistance is going to be 1 times 0.5 divided by 1.5. Or you can solve it by the longer method also, no worries over there. Acha, define current density, we have already defined it. They are saying it is a scalar or vector, it is a vector quantity. Okay, see how you are going to get marks. Define current density, it is current per unit normal area. Current per unit normal area. And it is a vector quantity and electric field is maintained. Okay. All they are trying to say is that we define this I equals to NEAVD, right? Are they asking about this relation only? Hopefully not. So if you are going to quickly see this, I upon A can be written as current density. So the relation with current density will come out to be J equals to NEVD. So that's it. After this you can derive each and everything, acceleration, each and everything from this formula. Alright. Please explain the KVL question again. If we'll reach to KVL again, I'll explain it. That because that was long time ago. Acha, see what was the what was the next question? What is a Wheatstone bridge? What is a Wheatstone bridge? And obtain the necessary condition under which the Wheatstone bridge is balanced. Quite an easy one, na? Very easy. Not to worry about. Tell me. This type of a circuit will be known as a Wheatstone bridge. So let's say you have got R1 over here, R2, R3, R4, and these 2 points are P and Q. And let's say you have got R5 also over here. So this is the Wheatstone bridge, and balanced Wheatstone bridge basically means potential of point P and Q are going to be same. They could have also told you to derive the condition. See, this is, you will have to remember it, that for balance, this is the condition for balance. After deriving it, after using all the KVL rules, we'll get to know this, that R1 upon R3 is actually equals to R2 upon R4, right? So out of these two, please remember that this is, we already know, this is a fact, because we found the balance condition using a galvanometer, and then we get to know that, okay, if the ratio of resistance is something like this, we'll get a balanced Wheatstone bridge condition. Got it? See, easy questions from 2023, not to worry about. If they are talking about heat produced, simply use I square RT. I square RT, T is time over here. They have given us the current. Current is 0.8 ampere. Resistance is 40 ohm. And time is for 1 minute. Please use this as 60 seconds. Is it clear? Now, obviously, you can use another formula if they have given you different values like V square by R into T or VIT. Not going to solve it, very easy. Quick. Can you tell me the weightage of physics? Next. A cell of EMF E is connected across an external resistance R when current I is drawn from the cell, the potential difference. Come on, do it. Do it by yourself. And then we'll start magnetism. We'll start moving charges and magnetism. So don't let your energy to go down. All right, quick. Let's start. After this, we'll quickly start magnetism. A cell of EMF E and external resistance R when current I is drawn from the cell, the potential difference across the electrodes of the cell drops to V. The internal resistance of the cell is. Very easy peasy here. E will be actually equals to V plus I into R. Is that clear? And now what they are trying to say is R is here as internal resistance. So I will be E minus V divided by R. That is I, but we have to find out the internal resistance. So that will be E minus V divided by I. Have they given us the current? So what's the problem? Although the problem is that our option is not matching, na? So no issues. We'll again find it out. Current can be written as net EMF divided by total resistance, right? So I'll again write it down. This will be E upon R plus R and times smaller. Is it clear now? Right? Hopefully now this is good. Now what we can actually do is we can rewrite this thing as E minus V, or E times R plus R equals to V R plus R plus E into smaller. Find out smaller from this part. You will get your answer. Quick. Write down the answer in the chat box. Discharging of what? Charging and discharging of capacitor, that's not in course. Quick. Let's move. Let us move on. We have already talked about current density. Current density due to drift is given by, we have already cleared it, right? I was actually equals to NEA VD. So I upon N will be current density, that will be NEVD. Alright, so NEVD, that means D option is going to be the correct. Now let's move on to moving charges and magnetism. Because see, in current electricity also there are many topics which are been removed. Potentiometer has been removed, meter bridge has been removed, right? All of those complex quotients which only deals with the finding out the equivalent resistances, all of those things is removed. Let's complete moving charges and magnetism, then we'll talk about brake. Not now. Not now, we'll talk about brake when we'll complete moving charges and magnetism. Let's quickly start. Acha, in this one na, you'll have to pay attention. Because you know, in this we try to find out the magnetic field intensity. And there are two things, finding out its magnitude and direction. Alright, let's quickly start. Quick. No 5 minutes break. We don't have that much time. We have to cover entire class 12th. Alright, I'll give you break when I'll be tired. Come on. Restroom. But you can obviously go, na. 𝐿 law is the first thing that we should actually do. Although I know that in NCERT they start the chapter with moving charges, right? Motion of charges in magnetic field. We'll start it with 𝐿 law. Now what does 𝐿 law says? According to 𝐿 law, the magnitude of magnetic field dB is proportional to the current I and the current element dl, and inversely is proportional to the square of the distance. What are they talking about? Let me explain. Let's suppose, dosto, you have got a piece of wire over here and current carrying wire, and current is I. Alright, dosto, current is I. Let's quickly start 𝐿 law. Very easy. Its application is also not that difficult. And let's suppose we want to find out the magnetic field at point P. So what now we are going to do is, we are going to say, let's take an element from here. Let's take an element of dl length, and this element will be known as a current element. This element will be known as current element, and you are going to use it quite extensively in this chapter. So please understand this. Current element is written as IDL. It is a vector quantity. Two things about current element, then we'll move on. It is a vector quantity. Its magnitude is I into dl, and its direction is along the direction of current at that point. So if in this wire, if the current was I, something like this, at this particular point, the direction of current element will be something like this, tangential to that curved path, right? And this distance this vector quantity is known as r vector. Please understand, this vector is known as r vector, and this angle is known as theta. First of all, what is this angle, sir? Theta. This theta is actually the angle between current element, so I'll write it as IDL, and r vector. All good? Now what does Biot-Savart's law say? Biot-Savart's law say that this magnetic field dB is proportional to IDL cross r and inversely proportional to r cube. Or I mean, obviously when you are going to convert it into scalar form, you will get what we have got over here, right? So dB will be, by the way, this is in vector form, dB will be mu naught upon 4 pi, which is a proportionality constant, IDL sin theta upon r square. Dosto, this is the magnitude of the magnetic field, and direction will be known as by the cross product of current element and r. And I have told you what current element is. Very easy. Current element is something like this, right? Quickly tell me. Quick. So if you want to know the direction over here, na, at this point, IDL will be in this direction, right? IDL will be in this direction, cross R. So thumb is going down, is into the board. So that means at this point, magnetic field will be into the board. We learn magnetic field using right hand rule also. Na? You can simply use right hand rule. Put thumb like this, open your fingers. This is palm rule. Fairer end is coming inwards. Magnetic field is also inward. That's it, right? This is mu naught upon 4 pi IDL sin theta upon 4 pi r square. And over here, mu naught upon 4 pi is proportionality constant, whose value is 10 to the power minus 7 Tesla meter square, Tesla meter per ampere. All right. Acha, then we'll talk about circular loop, which is again derivation. Yes, we are going to cover all the chapters today. We are going to cover all the chapters today. Is it all good? Biot-Savart's law is all good for the first part. This is again very important thing, current carrying circular loop. And I have not kept the definition over here, but you all know this is magnetic field due to a current carrying circular loop at a point on the axis. So let's suppose we have got a loop something like this, and we want to know the magnetic field at a point on the axis. Let's suppose at some this point, right? And by the way, let's say I'll explain this derivation to all of you so that you don't have to mug it up that much. This is, let's suppose this is the axis of the circular loop, and that's how the circular loop is coming. So whatever this plane is, this, let's say this is YZ plane. So this is the circular loop and this is the axis, and we are trying to find out the magnetic field at this point, and the current is flowing something like this. Got it? So current is moving like this. At this point, current would be coming towards you. Done? So again, we are going to do the same thing. We are going to say, okay, fine, this circular loop has radius r. This circular loop has radius r. It has got current I, and we are trying to find out the magnetic field at a point x from the center. So let's say this point is x. Again, we are going to do the same thing. We are going to say, sir, Biot-Savart's law, we have defined Biot-Savart's law for a current element. Now you know what current element is. Let's also define a current element over here. Let's define this to be our current element. Let's say this is ideal. Now, if I'm going to talk about the ideal in our case, it would look something like this. This is the axis, this is the ideal, and the direction of ideal would be something like this, right? Because the loop is coming like this. Is that clear? So, if I'm going to apply my normal right hand palm rule, I'm going to align my thumb in the direction of current. I'll open my palm in this way. Do it by yourself, huh? Do it by yourself. Fairer end is coming diagonally, something like this. So, because of this current element, if I want to find out, if I want to know the magnetic field at this point, it will be in such a way, in this way. And let me write this thing as dB. All good? Let's quickly mark some reference axis over here. Now, again, in different books, you can get different things. Let me mark this angle as theta. If this angle is theta, this will be 90 minus theta. Or what I can actually do is, I can simply mark this angle as theta for your simplicity. This angle is theta. So this will be 90 minus theta. So this angle is going to be theta. So you're going to get sine theta over here, and it makes no difference, huh? Trust me. You will get dB sine theta over here, and your vertical component will get cancelled out. Why cancelled out? Because please remember, similar current element you are going to get at this point also. So over here also you will have dB sine, dB cos theta. Quick. Done. And also there will be a magnetic field over here. So what you should actually write down in the board exam is, after writing all of these things, now what you should actually write down on the board exam is that due to symmetry, also first you will write down what is the radius of the loop, current, in which plane it is, what is this point A, what is this point P, at what distance this is. You are going to write down everything, right? After this you will write due to symmetry, vertical component of magnetic field will cancel out. Is it good? Clear? We are talking about each and everything now. Formulas, quotients, derivations, each and everything. If I talk about derivations, you will say, sir, do formulas. If I talk about formulas, you will talk about derivations. So please hang on. So the net magnetic field, after this point, I will say the net magnetic field will be, by the way, if you want me to write down in the vector form, I can easily write it down using an I cap. So net magnetic field will be dB, the integration of dB sine theta. That's it. Doston, that's it. Now dB can be written as, it will be written as mu naught upon 4 pi IDL. Acha, there is one difference. There is one doubt. This theta and this theta are not same. I should have drawn some another angle over here or at any one of the point. Okay? This theta and the theta from the Biot-Savart's law are different. Can you tell me what is the angle that Biot-Savart's law that we usually draw in Biot-Savart's law? What I can do is I can actually convert this angle into phi. Let's say this is phi. So this will be 90 minus phi. So this will be phi. So this will be 90 minus phi. Because I don't want you to get confused. So this will be sine phi, this will be cos phi, this will be cos phi. Because theta is something else. What is theta, sir? Theta is the angle between ideal and this r vector which is always 90 degree. Are you getting it? Bhai, this is out of the plane. Okay? Anything which is out of the plane will make 90 degree with this line, na? Because this is another plane. This is your xy plane. This is your yz plane. So these are going to be perpendicular. So always you are going to write, I'll also convert it over here. This is dB sine phi. So mu naught I dl, I'm going to write sine 90 over here. And then I'm going to write r square is going to be this distance. So this will be r square plus x square and root square of, raised to the power 3 by 2. Good, good, good. Quickly tell me. So this is going to be r square plus x square, and then I can write down this sine phi. So this sine phi will be, sine phi is actually perpendicular, that is r upon hypotenuse, that is r square plus x square whole raised to the power 3 by 2. So that would mean that r divided by r square plus x square whole raised to the power why 3 by 2? It's just 1 by 2, no? Not 3 by 2, 1 by 2. So this is going to be 1 by 2. So 1 by 2, now it will become 3 by 2. Please again understand, we'll take everything out of integration, mu naught 4 pi I r upon r square x square raised to the power 3 by 2 integration of dl. Everything is finished. This integration of dl basically means if you are going to add all of this dl, what are you going to get? You are going to get 2 pi r. So we are going to integrate it from 0 to 2 pi r. So you will get your answer as mu naught upon 4 pi 2 pi r square into I divided by r square plus x square whole raised to the power 3 by 2. Write down in the chat box if you have any doubt. Quick, quick, quick. 1 by 2, not 3 by 2. I've corrected it. But very good for your concentration. Good, good, good. Is it all fine? If it has got n number of turns, if there are n number of turns, if there are n number of turns, then what you are going to do? You are going to just multiply this thing with n. So B net will become mu naught upon 4 pi 2i pi r square divided by r square plus x square whole raised to the power 3 by 2 multiplied by number of turns n. If you want to find out the magnetic field at the center, right, this is an special case, at center. At center would basically mean that you are saying that x should be actually equals to 0. So if x will become 0, you will get mu naught upon 4 pi 2. Please understand this will become, this r will get cancelled out. So we'll be left with also, see, r square will get cancelled out with this, 2 will get cancelled out, pi will get cancelled out, we'll get mu naught I, that's it. I'm talking about just one loop, divided by 2, and over here I've got r. So mu naught I upon 2r. Quick, quick, quick. Mu naught I upon 2r at center. Is it all good? Everything's fine? We can find out for every sector as well using the same formula. Okay? Using the same formula we can find out for any sector using a very simple trick. You don't have to actually derive all of those things now. You'll simply say, sir, at center, the magnetic field due to a circular wire is coming out as mu naught I upon 2r, where r is the radius. Acha, by the way, there is one thing in which some of students have told me that they do one silly mistakes. What they do is when they have got their exams, they say that, sir, I mean, by mistake I wrote the magnetic field due to a straight wire, an infinite straight wire, as mu naught I upon 2r. They swap the formulas. This is mu naught I upon 2 pi d or 2 pi r due to an infinite wire. Is that clear? This is mu naught upon 2r. By the way, if you are going to talk about again this thing, you are going to say that for 2 pi radians, the magnetic field is coming out to be mu naught I upon 2r. So that means for theta radians, that means if you have got a sector something like this, again I am telling you this is not the correct way to derive it, but still we can manage. Something like this. Acha, theek hai, everything's fine. So we'll say that because of a unit wire, we have got mu naught I upon 4 pi r times theta into radian. So this is going to be the formula. Is it good? Quick, doston, quick, tell me if you have any doubt. What about the direction, sir? Direction will be, in this case, direction will be found out by, so if you have got a current carrying wire, something like this, because direction is important, because again you are going to use these things in electromagnetic induction also. If current, curl your fingers in the direction of current of your right hand, so the thumb is going to tell you the direction of magnetic field. So this is the direction of magnetic field. One more thing. If someone says that, okay, find out the magnetic field due to a wire which due to a structure which looks something like this, they can ask, and this is also, you might have seen questions like this, something like this. Let's say this is wire I1, current I, same current will flow, of course, and this has got radius r, and we have to find out the net electric field at point O. First of all, these are known as semi-infinite wire. We'll talk about them. But they will have no magnetic field. Magnetic field will be 0 at point O. Why? Because this point is along the line of the wire. We could have talked about this thing if we have discussed the original formula of straight wire. That's not in course, I believe, right? Ampere circuital law is in the course, and using that we can derive that formula. But still, do we have Fleming's left hand rule? We have Fleming's left hand rule, but that will come in moving charges, not over here. In this, we have got right hand thumb rule. Done? Come on. So because of this, it's going to be, if for at center a complete circle had this, so this will have mu naught I upon 4r, half of a complete loop. That's it. This is going to be your answer. Done? Everything's clear? Quickly write down in the chat box. That's how the magnetic field lines will look like if you'll have to draw the diagrams. This is a current carrying loop, and this is the direction of magnetic field line. See, you'll curl your fingers in the direction of current, and thumb is pointing up. That means magnetic field lines are going like this, because they'll always form closed loops. These things will always form closed loop. Is it clear? Direction is clear. If someone asks you to draw these diagrams, you must be able to draw them. Hopefully everything is good. Right hand thumb rule. Now let's come back to Ampere circuital law. which is nothing but it is completely analogous to, comparable to Gauss law. Any more doubts? Till now we have completed the derivation part of this chapter. Solenoid is not coming, derivation of solenoid will not come. What is left? Biot-Savart's law, we have completed it. And completed all the cases so that you can also solve some questions. Okay? Chalo, now let's move on to Ampere's circuital law. What does this law says? This law basically says that if you have got a loop like this is a loop, huh? By the way, it might look something like this as well. Let's say you have got some wires like this. Different ways to draw diagrams. And you have got a loop. So there is going to be a difference between a loop and surface, of course, right? And let's say doston that this is I1, I2 and I3 and I4, right? Similarly, someone might also draw this diagram something like this. Are you getting it? Right? It is a loop, just like like a ring. Okay? So now this law says that the line integral of B dot dl, will be equals to mu naught times of the enclosed current or the current which is inside the loop, right? So what is inside the loop in these specific cases? You are going to say right now, based on these diagrams, the enclosed current will be I1 minus I2 plus I3. Quick, doston, if you have any doubt, do let me know. Again, we are going to say the same thing. We are going to say, bhai, that magnetic field will be due to all the wires, but in enclosed current, you will only talk about these wires. Is that clear? And now, if you will ask me to actually, acha, chalo, first let's also have some important notes from Ampere's circuital law, so that you can have an idea of everything. Choose the loops. There was a way in which we used to find out the Gaussian, we used to select the Gaussian surface. Similarly, here also we will choose the Ampere loop in such a way that either magnetic field is tangential, because if it is tangential, cos will become 0, or it is perpendicular. So either it becomes 0 or it is maximum. Magnetic field at a point doesn't depend upon the shape of the Ampere loop. This is important again for your AR questions. Alright, magnetic field same at every point in the Ampere loop. Now we can talk about an infinitely long straight wire. Although we know its formula, but let me derive it for you. Then we will start some question. Sir, before slide direction, we talked about direction here. Quick, let's say we have got a infinite current carrying wire. An infinite wire basically means that at both the ends it is tending to infinity. And also let's suppose that we want to find out its magnetic field at a distance of r from here. Now we are not going to talk about all of those things. I mean, if any one of you are facing a trouble, why are you sometimes you take a cylinder over there, now you are talking about a loop. Why is that? This is the main principle. We want to enclose a current. We don't want to cover a current. In that case, in Gauss law, we wanted to cover the charges from every side, right? So we'll draw a Gaussian surface, something like this. sorry, ampere loop, something like this. So this is our ampere loop. And now we are going to actually say one thing, that this ampere loop has got a direction, right? Let's suppose that we are assuming that the direction, the ampere loop is in this direction. Current is flowing in this direction. So if current is flowing in this direction, at this point, magnetic field will be cross. And also DL will be in the same direction, if you can understand what I'm trying to say. This, let's suppose this is the wire. This is the direction of magnetic field, dosto. How? Right hand thumb rule, we place our thumb in the direction of current, we curl our finger, that means magnetic field is moving like this, and so does ampere loop is also moving in this direction. That DL is the ampere loop, right? So we are going to write B DL cos 0, that's why I've written cos 0 everywhere, and the integral of this will be actually equals to mu naught times of I. So out of these things, magnetic field will be constant at every point on the ampere's loops, because it is a symmetrical ampere loop. It should be. So we will be left with integral of DL cos 0 is 1 mu naught times I, and this will be 2 pi R mu naught into I, and that's how you got your formula for infinite wire, mu naught I upon 2 pi R. Clear? Everything's fine? No more doubts? Come on, let's move on to the next one then. Let's talk about force between two parallel current carrying conductors. Acha, this is important, huh? Important, because why it is important? They can also ask it in the form of derivation. They can also ask it in numericals. Acha, before this, we must understand one thing. That is, force on a current carrying wire, what is the force which acts on a current carrying wire? It is actually BIL sin theta. BIL sin theta. Right? Well, we can easily derive it using two formulas that we have used for current, and by the way, before actually deriving this formula, we'll have to actually derive the formula of motion of charges in magnetic field. We'll have to do that. But sir wrote it as dot. In which part, dear? Which part? Acha, before starting this, let me first explain that motion of charges. That will be better, because that is also important and very easy. And all of those helical things are not going to come, so we don't have to worry about that. A very simple thing, that is what will happen. We are talking about motion of charges. Motion of charges in magnetic field. If charge will move in a magnetic field, it will experience a magnetic force. Okay? Acha, okay, half circle, it will be cross. Make it cross. Don't mind it. Make it cross. It will experience a force. What type of force? A magnetic force. And this magnetic force will be written as QV cross B. QV cross B. Or QVB sin theta, which means, of course, this magnetic force is perpendicular to both velocity and magnetic field, which further means that work done by this magnetic force will be 0, and hence there will be no change in speed. Velocity will change, but there will be no work done. What else we can say, bhai? You must have seen that diagram, that if you have got a magnetic field region, something like this, See, after this, we talk about that Fleming's left hand rule, है ना? You guys have been talking about Fleming's left hand rule for quite a time. Now you can talk about Fleming's left hand rule, but in a way you don't have to. Let's suppose this is magnetic field, and by the way, this is a uniform magnetic field, and a charged particle enters into this magnetic field in a transverse direction. Transverse basically means that in a 90-degree. Magnetic field is like this and charged particle is moving like this, right? So what will happen? A magnetic force will happen. What is the direction of magnetic field? V cross B. How to write V cross B? Just see, I always suggest you to use the vector rule first, right? V, and then curl your finger towards magnetic field. So magnetic field is in this direction. So V cross B, that means thumb is pointing upwards, magnetic force will act upwards. Now the students who don't remember this process right now, I'll suggest for you right now, you can use your normal Fleming's left hand rule. Okay, I'll explain that as well. See, we considered this to be a positive charge. That's what a Fleming's left hand rule is. This tells you the direction of magnetic field. This is along the direction of current or motion of positive charge. This is along the direction of force. So forefinger should go inside into the board. This is already aligned towards the direction of motion of positive charge. Thumb is pointing towards up, right? This force will actually try to change the direction of the body, and it will make the body to go in circular motion. That means this force will behave as or will provide necessary centripetal force. And from here you can actually get to know what radius of curvature would be of this circular path. And then again you can actually rewrite many other formulas. For example, as momentum divided by QB, or under root 2m kinetic energy divided by QB, or under root 2m Q into potential difference divided by QB. Is that clear? Everything's fine? Bhai, I have done all the derivations here. I have not missed a single derivation. Okay, I might have missed few derivations, but almost every derivation has been done. Sir, naam le lo. Okay, Ananya. Sir, do like this for derivations also. Kirchhoff's voltage law. Sanjay bhai, abhi KVL means what, sir? अच्छा, Batman पूछ रही है. Batman. Sir, pitch for helix is not in course, so the thing which is not in course, we are not going to look into that. Is that clear? Is that clear? The things which are not in course, we don't have to worry about that. Quickly tell me if you have any doubt till this point, then we'll move on. Helix is in the NCERT. Well, I don't think, I think it has been deleted. Well, see, if you are insisting on helix, no worries, it will just take 2 minutes. I'll quickly finish what helix is. In the case for helix, please remember that magnetic field will be, we are going to assume magnetic field in such a direction, not into the plane, because in that case, we won't be able to understand the diagram, understand the path. By the way, this is uniform magnetic field. And now again, instead, if the charged particle was thrown something like this, it would have traveled in circular path. But now the charged particle is thrown at an angle. So let's suppose it is charge Q, it throws with some velocity V at an angle theta. So now you have got two components. One is V cos theta, the another component is V sin theta. Now what we are going to say is that there will be no change in this V cos theta, and this will experience as because of V sin theta, there will be change in direction. So instead of just moving in circular path, it will start to move in helical path. So no difference. When you are going to talk about radius of curvature, all you will have to write is mv perpendicular divided by qb. By the way, for time period also, you can also derive the time period formula over here as well. Time period is nothing but 2 pi r, that is mv divided by qb divided by v. So v can be cancelled out. That means time period doesn't depend upon speed. It is independent of speed. Another AR question. It does not depend upon speed. Time period doesn't depend upon speed. All right. Next, you can talk about frequency and other things also. Over here, it will be time. This is going to be m v sine theta divided by qb. And because it doesn't depend upon speed, so this will be just 2 pi m divided by qb. That's it. And if you're going to talk about pitch will be this velocity. Pitch is nothing but the distance between two loops. This is what pitch is. So 2 loops basically means one time period, right? One complete circular motion, one complete revolution. So v cos theta into time period. So that would be v cos theta times 2 pi m divided by qb. And there is nothing like pitch in the previous part. Clear? Quickly tell me in the chat box. Now you can actually talk about this thing. This force between two parallel current carrying wire. Why? I'll tell you. Let's suppose you have got two parallel current carrying wires, something like this. You have got current I1 and current I2. So in this specific case, we have assumed that the current are moving in same direction. All right. In this specific case, we have assumed that the current is moving in the same direction. So let's find it out. This is, let's suppose this is wire 1, this is wire 2. So force on wire 1 due to wire 2. Force on wire 1 due to wire 2. So how we are going to write it down? You are going to write it down something like force on wire 1 due to wire 2 is equals to magnetic field. Now please understand something over here. This is something like, let's suppose you have got a wire like this which has current I, right? And it is kept in some magnetic field. So this magnetic field is not of this wire. This is external magnetic field. So we have kept a current carrying conductor in a magnetic field, so it experiences this much amount of force. Got it? So when you are going to talk about force on wire 1 due to wire 2, so it must be kept in some magnetic field. Which wire is creating that magnetic field? Wire 2 is creating that magnetic field. Are you getting it? So I am going to write magnetic field due to wire 2 times current flowing in wire 1 times length of wire 1. Let's just write it as L. It has also got no use. ठीक है? Quickly tell me दोस्तों if everything's clear till this point. The separation between these two wires is, by the way, assume anything. Assume it to be R. So if someone asks you what is this B2, so B2 is going to be what? B2 is going to be mu 2 I2 divided by 2 pi into R times I1, and what I'll do is I'll shift this length to over here. So this will become force per unit length. This thing is actually force per unit length. And you know what? We can rewrite this formula something like mu naught upon 4 pi so that it looks a little better. Mu naught upon 4 pi 2 I1 I2 divided by the separation between them, that is R. Acha, now many more things. Now let's talk about the direction. Hopefully everyone's sir, if current moves in opposite direction, net force is 0. नहीं ऐसा कुछ नहीं होता. Now in this case, we have written the force over here. Let's also talk about the direction. How you are going to find out the direction? Again, cross product rule, that is right hand, or your normal Fleming's left hand rule. Let's use Fleming's left hand rule. Please understand. First, let's write down the direction of magnetic field due to wire I2. Current is in this direction. I'll open my thumb like this. So because of this wire, just so that you don't get confused, I'll use this ink. Magnetic field is cross. Why cross, dosto? Because right now I am not at all talking about the magnetic field due to wire 1. I am talking about magnetic field due to wire 2. Is it clear? Tell me in the chat box, bhai. Are you all sleeping or what? Tell me in the chat box quickly. Is it all good now? So I'm going to align my forefinger into the board, middle finger along the direction of the current. Force is coming like this. So that means direction of force is like this. So this is the direction of force. That means it is actually everything's fine. This is your open here. Sorry, so sorry. This is outwards. So this is going to be dot. I have done same thing earlier just once again in the previous thing, right? That's what you were saying. So this is going to be dot, not cross, dot, right? Dot. Yes, now I know that you might be writing this thing. Okay, got it. So forefinger outward, current upward, thumb is pointing in this direction. That means, and that's how I got to know that, okay, I've done something wrong. It must attract it. So this is force acting on wire 1 due to wire 2. Now everything, like every other, I have said this thing twice in today's class. Every forces in pair follow Newton's third law. So this wire will also apply the same force in opposite direction. And this is going to be force on 2 due to 1. You can find it out. This is going to be the magnitude. Now I have explained everything. Now you can define that 1 ampere from here also. Clear? Why, buddy? Why you want to know when this marathon will get over? Will you bring something to me? Quick. Everything's clear? We can define what 1 ampere is after this. Acha, by the way, from here only, na, you're going to write something like that. Wire, I mean, I'll simply write it down, or I'll see if I've got notes. Yeah, I think I've got notes. I've got notes of 1 ampere. Okay. So 1 ampere is nothing but, please try to understand, this is force per unit length, mu naught upon 4 pi, 2 I1 I2 upon D. So how you are going to define 1 ampere? You are going to define 1 ampere is that 1 ampere is that current. This value is actually 2 into 10 to the power minus 7 times 2 times 1 divided by, this is, let's say this is force, divided by 1. 1 ampere is that current by which 2 parallel current carrying wires will experience as a force of 4 into 10 to the power minus 7, or you can actually 2 into 10 to the power, we have already written it, so 1 into 1, 2 into 10 to the power minus 7 newtons per unit length. All right, is it clear? Acha, same, if the currents are in same direction, they are going to attract. If opposite, they are going to repel. So this is actually indifferent to what you have been learning, like same charges repel, same poles repel. This is different, right? So don't get confused. If current are flowing in the same direction, they attract. I am not showing the options. You are going to get options in multiple choice. So I'm just giving you as questions as it is. Acha, by the way, torque on a current carrying loop. This is also important. In a way, I have been telling you we are completing almost 80-70% topics we are completing. Torque on a current carrying loop. Although you can actually draw the diagram for this one as well. I'll suggest you to actually, if someone asks you to derive it, na, I'll suggest you to actually draw it something like this. Let's suppose you have got a loop, something like this. This is a loop. And current I is flowing in this loop. Find out the net force on this loop. It's very easy. It's very easy. If you have got a closed loop, na, net force, if you have got a closed loop, net force will definitely be 0. No doubt about it. But we are going to get a torque over here. Why? Let's mark it down. Let's say that this is point A, B, C and D. Obviously, wire BC and wire AD will experience no force because current element is parallel to the magnetic field. Wire AB will experience a force, and that force will be, magnetic field is in this direction. And please, sir, please teach galvanometer and its conversion. I'll teach it. Hang on, I'll teach it after this. Magnetic field is in this direction. Current is flowing inward, so that means force is going to be inward. Now I am correct, force will be inwards in this particular case. This is AB. Again, forefinger in the direction of magnetic field, middle finger in the direction of current, that is upward, thumb is pointing inwards. There will be no force for BC, similarly no force for AD, where if you are going to talk about AD, obviously magnetic field in this direction, current going down, this is force on CD and this is dot. That means these are two non-collinear forces. So they will create a torque. So if they will create a torque, you are going to write something like, torque equals to, acha, by the way, let's suppose that this length is actually, this is actually A, this is A and this is B. Okay? So you are going to write something like torque equals to force into R perpendicular. So force is actually BIL. Instead of L, can I write it as A? That is the length of the conductor. Come on. Dot is for outside. Yes, Sanjay. Yes. BIA. I have written BIL sine theta, that is 90 degree, into R perpendicular. R perpendicular in this case is nothing but small b. Is that clear? Right? So this will come out to be BI into A, where A is going to be area. So this is going to be your torque. This is going to be area. And if you have got n number of turns, if there are n number of turns, then we will say that by net torque will become BINA. What will contribute to this n times factor? That is, now n times of the wires will experience the same force. So we will multiply this with n, right? So BINA is going to be your answer, but this is a very specific case. Generally, what we will say is we'll actually change this diagram a little bit, right? So can we change it? Can we change it, dosto? Quickly tell me if everything's clear with this particular thing. Quick. Sir, teeth solenoid. By solenoid is just mu naught Ni. Derivation is not coming. So what's left? Acha, by the way, I'm going to explain something else also. This thing, that this I into B, na, this I into A, this is something that is called as magnetic moment. magnetic moment. We are going to also talk about it. All right, very important thing. Magnetic moment is something which is, let's suppose, if you have got a current carrying loop like this, if you have got a current carrying loop like this and current I is flowing, something like this. So magnetic moment will also be found out using right hand rule, same right hand rule, right? So magnetic moment will be also in this direction. The only thing is that magnetic moment is defined as I into area vector. So it is nothing but direction of area vector. But you will have to find out using the direction of current. Okay. Is it all good? Quickly write down in the chat box. Quick, quick, quick. Fine. So if we were talking about a diagram like this, we'll slightly change it. We'll slightly change it and we'll say that now let's suppose or something like this. A more general case, right? What we are trying to say is that it has rotated at a certain angle. And what is that angle? If you want to know what is that angle, in this direction the magnetic field was, right? Initially, if you have seen the diagram, this was the loop, this was the area vector, and this was the magnetic field. Is that clear? So they were making 90 degree of the angle. Now we have actually rotated it. So now we are saying that in this case, the area vector, let's suppose this is the area vector. Now it is making an angle of theta. Now it is making an angle of theta. Is that clear? So everything will get changed. Torque will be written as B na, I'm not going to write each and everything, hopefully you can understand it, B na sine theta, or it can be written as where I and A can be written as M, so this can be written as MB sine theta. So this is your main formula which has also magnetic moment. So torque will be M cross B. And now again everything will get repeated from that dipole, from that electric dipole. So not going to repeat it. So this is MB sine theta, potential energy will be minus MB cos theta. Everything should be clear, right? An electric bulb is rated by, very easy question. Very easy question, Krishna. All right. Can we move on? By the way, galvanometer works on this principle. Galvanometer works on this principle, and how we are going to solve these questions, we'll see to it. Right? Let's start solving some questions. Let's start solving some questions, then we'll repeat which part, buddy? An electric bulb is rated 220 volt and 100 watt when it is operated at 1110 volt. See, it's very easy. What you need to do is, by the way, rest of you solve this question by the time I'm explaining his doubt. What you need to do is, from that rated power and rated potential, now find out the resistance. So resistance is going to be rated power is actually VR square divided by R. So R will be VR square divided by rated power. And then as soon as you got to know what R is, just apply it into the same formula another time, that is P equals to V square by R. That's it. What will happen with this one? The energy of a charged particle moving in a magnetic field does not change. This is absolutely true. This is absolutely true, and the reason is that work done by the magnetic force is zero. It is because the work done by the magnetic field on the charge is zero. This is also absolutely correct. So option A should be correct for this one. No doubt. No doubt, dosto. Everything's fine. Can we move on? A particle of mass m and charge q describes a circular path of radius r in a magnetic field if its mass and charge were 2m and 9 by 2 respectively. The radius of the path would be. Chalo, let's solve it, and let's solve it on poles. Quick. You all know that the radius of path is actually given as mv divided by qb. And they are saying a particle of mass m and charge q describes the radius, hai na? So from this we can say that from this this is the thing, r is equals to mv divided by qb, and charge were 2m and 9 by 2 respectively. This is hopefully this is all good. Maybe there might be some typo in this one. 9 by 2 or q by 2, I am not sure. Let's check. That's q by 2, dosto. This is q by 2. This is q by 2. Right? So r dash will be, instead of m, we are going to write 2m into q by 2. There is no change, mv, sorry. And if it is respectively, the radius of path will be a particle of mass m, circular path, radius in magnetic field. They are not talking about the speed, so I am hoping that it will remain same, divided by q by 2 by b. That is 4 mv divided by qb. That will be 4r. D option. Is that clear? Is that clear? D is the correct answer. Quickly tell me, dosto. Quick. Moving charges and magnetism is going on. Next chapter is going to be magnetism and matter, EMI, AC, and so on. Chalo, let's move on to the next one. Acha, now we can understand the problems of galvanometer. You were telling me to explain galvanometer. So what I'll do is, I'll explain galvanometer using questions. Right? Done? Everything's good? Sir, end pole. Right. D was the correct answer. Oh, wow. Good. But only 2 of you have given the correct answer here. You can use the poll. You can just write down the answer in the chat box. It will I mean this thing will note it down. A galvanometer has a resistance of 50 ohm and it is converted into a voltmeter of range 2 volt. Please understand. And I'll give you tricks also to how to actually do these kinds of problem. First of all, whenever you are going to talk about a galvanometer, this galvanometer, the first thing that you need to know is this galvanometer is a very sensitive device, right? Sensitive in a way that if you are going to actually let it read a larger value of current, it will actually it will malfunction. I mean, it will get destroyed, right? That's what we can say. So the maximum value that a galvanometer can take is known as a full scale deflection current, or IG, and it has got certain resistance which is usually denoted as G. Now if you want to convert it into a voltmeter, then you will have to use a resistance in series, and this whole thing is actually known as a voltmeter, which is connected in parallel. All right. So first of all, the students who are trying to study it for the first time, this whole thing is actually known as a voltmeter, which then is connected in parallel, but not this R. This is a high resistance wire which is connected in series, right? So now they are saying that, okay, this G is actually of 50 ohm. G is actually of 50 ohm, and we want to convert it so that the voltmeter comes of the range of 0 to 2 volt. All right. That means this should read a total voltage of 2 volt. And they have also said that what should be the value of this wire, right? So what we'll do is, now they are saying that now we want to increase its range to 10 volt. What should be the value of that resistance? So first find out this Ig. So Ig will be दोस्तों Ig into G, that is 50 plus 1 kilo ohm is going to be equals to 2 volt. Is that clear? Hopefully everything is good. So Ig would be 2 divided by 50 into 1 plus 10 to the power 3. Next is, now they are saying that now we want to measure a voltage of 10 volt. So in that case, Ig should be same. Why Ig should be same? Sir, that is the maximum value that a galvanometer can measure. I mean, it will not depend upon what resistance you are connecting with it. Is that clear? Done? So now we are going to say, in the next case, we are going to say Ig, which is actually nothing but 2 upon 50 into 1 into 10 to the power 3 times G. G was again 50 plus R that I want to find it out equals to 10. Please see everything's clear. Hopefully everything is clear. So this will be 50 plus R equals to 250 times 10 to the power 3. Am I getting something like R would be 250 minus 50. Quick, दोस्तों, please check. Have we done any mistake? Quick, sir. If you have any doubt, please ask your doubt. Yes, you will get this PDF as soon as the class will get over. You will get this PDF, so don't worry about it. Acha, that is plus here. Sorry, my bad. My bad. That's what I was thinking. Why are we getting a wrong answer? This is plus. This is plus. This is plus 1000. Fine. So now you are going to say that 2 divided by 1050 times 50 plus R is equals to 10 volt. Now you will get your correct answer. My bad. This is 5. So this would be 50 plus R equals to 5 times of whatever this is. And then R equals to 5 times of 1050 minus 50. Please quickly tell me the answer. Correct? Quick, दोस्तों. Let me know if you have any doubt. I think 5.2 kilo ohm is going to be the correct answer. Check it. Please check. C is coming out as your answer. Sir, how would you connect 3 resistors? Acha, 3 resistors, each of resistance 6 ohm, and the combination should be 9 and 4. Yeah, these types of questions are quite simple. Why are you asking? I mean, these are quite easy. But if you want to get 9 ohm, just use one 6 ohm resistor and another should be in series with it with 2 6 ohm in parallel. Those things are very easy. Sir, once more. Which once more? Sir, वापस से. ये वाला. I think, see, first of all, find out what Ig is from the first information. Then use the same Ig in the second information that they are saying now they want to find out, they want to increase the range to 10 volt. That's it. That's it, दोस्तों. Let's check some of the questions from last year. 2 long straight parallel wires separated by a distance of 20 centimeter carrying current 5 ampere and 10 ampere respectively in the same direction. Find the magnitude and direction of net magnetic field at the center. They are not talking about force. Net magnetic field at the center. Net magnetic field at the center, they are saying. So current is flowing in the same direction, I1 and I2. and at the center. That means if they were at 20 centimeter, this distance will be 10 centimeter, this distance will be 10 centimeter, right? Magnetic field due to wire 1 will be B1 is going to be cross and B2 is going to be dot. Think about it. Tell me the answer in the chat box. Quick. दोस्तों, be really fast. Magnetic field due to a wire is really easy. The formula that you will use is mu naught I upon 2 pi r. Upon 2 pi r. Now, obviously, this one has got larger current, so net magnetic field will be in this direction, right? So net magnetic field will be B2 minus B1. That is mu naught. I can take mu naught upon 4 pi. Mu naught upon 4 pi, and I can also take this 10 centimeter as common. So this will be 100 and this will be I2 is actually 10 minus I1 is actually 5. So we'll be left with mu naught. Obviously we can cancel out this. Mu naught upon 4 pi is 10 to the power minus 7 times, I've got one more 10 and I've got 5. So I have 5 into 10 to the power minus 6. Tell me, this is going to be in Tesla. Quick दोस्तों, once more, which part दोस्तों, which you are saying once more? If you'll ask me, I'll answer it. Acha, I have not multiplied 2 over here. Yeah? I have to multiply 2 also over here. Because I have written mu naught upon 4 pi. Na? So 2 times of this will become 20 and 2 times of this will become 10. So this will become one more 10. So this will be just 10 to the power minus 5 Tesla. This is the correct answer. Check, and then let's move on. Quick. How 4 pi? I've just multiplied 2 to both numerator and denominator so that we can rewrite it. Is that clear? Done? 10 to the power minus 5 is correct. Let's move to the next question. Acha, now let's solve a question like this. Not that difficult, but still. From 2024, a straight wire is kept horizontally along east-west direction. If a steady current flows in wire from east to west, the magnetic field at a point above the wire will point towards. Easy one. Easy. You can do it. We'll take break after this particular chapter. Okay. Solve this in homework. Take a screenshot. It's quite easy. Take a screenshot. We'll see some more questions. Acha, we have got one more question from galvanometer. So you were asking about the galvanometer. We have got one more question. Let's also take a look on this. A galvanometer has a resistance of 100 ohm. That means capital G is of 100 ohm. Now everyone, I want your concentration over here. Quickly, galvanometers of 100 volt, it needs to be converted into an ammeter. Now, if a galvanometer needs to be converted into ammeter, we'll have to connect a shunt, which is a low resistance wire, in parallel to it. And the range should be 0 to 1 ampere. Now think about it. This is where I was talking about that. Let me explain the concept through the question. This whole thing is actually a is an ammeter, which will get connected in series. This thing is an ammeter. And if you are saying that, sir, total range should be of 1 ampere, that means 1 ampere should come something like this. See, no matter what happens, na, the galvanometer cannot take any current more than Ig. It can't take it. So still for this particular galvanometer, we'll have IGS something, IGS current, and it will have the remaining current, that is I minus Ig. That's why we use a low resistance wire over there, so that it can take the maximum amount of current. Now they are saying the resistance is of 0.1 ohm, the ammeter will show a full scale deflection. They want us to find out what Ig is. They are in parallel now. So I'll write something like Ig times galvanometer resistance is equals to I minus Ig, that means 1 minus Ig. Why 1 dosto? Because 1 was the total current. Out of total current, Ig will pass through galvanometer. What is the remaining current? I minus Ig. That will pass through the shunt. And because they are in parallel combination, the potential must be same. So this is 0.1 ohm. Can we solve what Ig is going to be? Quickly tell me. Can we solve it? What Ig is going to be? I've explained both of the things over here. Quickly tell me, what answer are you getting from this? You are going to get this PDF in the description box only after the class will get over. Okay. What is your answer? 1 milliampere is the answer. Are you sure? Okay. Hopefully you have got it. See, by now it's your responsibility to find the answer. I have sufficiently done. Right now, it's your thing. Now let's move on to the next question. We have got, let's take a look from this particular thing. A 10 centimeter long wire lies along x axis. It carries a current in this in y direction. Magnetic field is this, exists in the region. The force in the wire will be. Quickly do it. Use the formula of force of B of IDL cross B. So you have got magnetic field and current is moving in the positive y direction. That means IDL is along J caps. So only you have to do the cross product. Please solve it by yourself. All right. So now from after the break, almost we have completed many such things. Like, see, you are going to get direct formulas from two parallel current carrying wires. This is again from last year 2023. Two long parallel wires kept at 2 meter apart, carrying 3 ampere each in the same direction. The force per unit length. Force per unit length will be, just use the formula mu naught upon 4 pi 2 I1 I2 by distance divided by distance. So this is going to be 10 to the power minus 7 times 2 square of 3 9 divided by separation is 2 meters. So it's going to be 9 into 10 to the power minus 7, and because they are carrying current in same direction, it will be attractive. So option D. Now see, that's what I was saying. If you are going to learn the formula only, na, you will be able to at least get those first 18 marks. All right. Quickly tell me in the chat box if everything's clear. Quick. Done? Similar question. Beam of electrons and protons move parallel to each other in the same direction. So if you have got a beam of protons, that means current will be also in the same direction. But if you have got a beam of electrons, because of this current will be in opposite direction. So they will actually repel each other, right? So they will actually repel each other. Got it? Ajab, if you are going to look for some graphs, which of the following graphs correctly represents the variation of magnitude of the magnetic field outside a straight finite current carrying wire of radius a as a function of distance r from the center of the wire? Okay. By the way, have they ever anywhere have they said that this is a straight wire? I mean, this is a, so this is going to be, by the way, magnitude of magnetic field is, let me explain it in detail. If you have got a wire now which is actually solid, which they have not told us, if you have got a wire which is actually solid, then situation becomes a little different, as you might already know it. In this specific case, enclosed current will obviously change, the net current will change, not enclosed but net current will change, right, if it is solid. But if it is actually just a hollow wire, magnetic field will be just inversely dependent on R, that's it, and there will be no magnetic field from the center. So the best thing that I can look over here is option C. Why? Because if you have got no current, till the surface, there will be no magnetic field. But as soon as you at the surface, magnetic field will be maximum, which will be mu naught I upon 2 pi r, and then it will decrease. And whenever you have got a relation of something like this, the rectangular hyperbola is made, right? Okay. That is straight wire only. That's what I am saying. That is just a straight wire. That's it. Quickly tell me in the chat box if you have any doubt. Now we'll start magnetism and matter after a short break. So let me give you some break. Let's take a minute break of 15 minutes. Come back quickly, but okay, come back. Quick, take some break. Then we'll come back to magnetism and matter, electromagnetic induction, and then so on. Right? Quick. Welcome back दोस्तों. Very welcome back. Hopefully you have got your refreshment now. Hi everyone. Come on, let's quickly now start. Hi. Welcome back. Now let's start magnetism and matter, the next chapter after moving charges and magnetism, right? So basically lots of things are going to be same when we are going to talk about bar magnets and things like that. So we'll keep our attention towards magnetic materials and properties, right? Because I think that is something which is important as well as quite time efficient. Come on, let's quickly rejoin. Let's start now. See, in magnetism and matter, as I've told you, the first few parts are going to be related with bar magnets. So whatever we have learned so far, like for example as electrical dipole moment, now we are going to talk about magnetic dipole moment, and actually we already did talked about magnetic dipole moment, right? Now we are going to have one more formula. What is that? Let's suppose this is a bar magnet. Here we have got north pole, here we have got south pole, and now we are defining a term called as pole strength, just to show that how much strong this magnet is, how much strong these poles are. So let's say its pole strength is plus small m, this pole strength is minus small m, and the distance between these two poles is, let's say, d. केवीएल का क्वेश्चन एक्सप्लेन करो सर. भाई आप पीछे जाके देख लो ना धनंजय. So magnetic moment for a bar magnet is going to be just m times d, and the direction will be from south pole to north pole, again by convention. Can you please observe the similarities between electric dipole moment and magnetic dipole moment? Is that clear? Everything is similar, दोस्तों. Again, I mean, at that point we used to keep electric dipole moment in uniform electric field. Now we are going to talk about keeping bar magnet in uniform magnetic field. Is that clear? Just a second, let me take care of this. Yeah. So now the thing is, things are going to be quite comparable what you have done in electric charges and fields. For example, you can also find out, this was m, you can also find out the magnetic field at axial and equatorial point. So if you are going to talk about magnetic field and axial point, acha, by the way, I think derivation is not required over here. They don't ask, the derivation has been removed, right? So you have to just remember the formula. And now how simple it is, you are going to simply say mu naught upon 4 pi 2m upon r cube or x cube, whatever you want to write, and equatorial would be minus mu naught upon 4 pi m upon r cube. Then also we are going to discuss some of the facts like what torque it's going to experience. So same mb cos mb sin theta, and then potential energy, same things, right? It's just that we have got now another formula for this. Done? Quick, tell me if you have any more doubts, else we'll move on. Let's quickly move to magnetic properties. Now see, this is where you are going to get some of the questions other than the first part, the theoretic, the part which is linking to magnetism, moving charges and magnetism. This is something new, and sometimes students actually feel a little trouble over here. Let's first define each terms, and then I'm going to explain the theory part of this as well. There is a concept, there is a term which is called as magnetizing field, right? There is a term that is called as magnetizing field or magnetic intensity. It is defined as applied magnetic field divided by permeability of free space, right? Next is intensity of magnetization. Now let me explain what are these things that we are talking about. Let's suppose we are talking about a material. We know, sir, what magnetic moment is. have you ever wondered, see, I can't help but to actually explain you this in a little basic way. Okay? Have you ever wondered what makes a magnet different from any other materials, right? Like for example, as by the way, this pen is actually, it has got a small magnet inside of it. So what's so special about this magnet, this material, than this normal plastic material, right? What's so special about this? Why it is showing certain properties that we call as magnetic properties, right? So it is related with it is related with magnetic moment of individual atoms, right? So generally what happens is, there can be two cases. One is the individual atoms do not have their own magnetic moment. They don't have individual magnetic moment. So this is one of the case, right, where they don't have any magnetic moment. Another case can be they have magnetic moment, but they are randomly distributed. They are in random direction. So the net magnetic moment will be of this entire material will be 0, right? Got it? Now let's suppose I am keeping this material into an external magnetic field, right? So I have applied an external magnetic field over here. I've applied external magnetic field over here, and I've kept a material over here. Now if because of this external magnetic field, if these dipoles are getting aligned, the magnetization, which is actually, magnetization is nothing but the magnetic moment. So the magnetization per unit volume is going to be called as intensity of magnetization. So what is capital M? That is the magnetization. That means the magnetic moment per unit volume. So the more number of dipoles, if they are getting aligned in a specific direction, the more is going to be the intensity of magnetization. Now I'll again come back to this thing. Why are we talking about something that is called as H? Okay, if you have already defined this B, this magnetic field B, why are you defining something that is called as H, that is magnetizing field, right? Hi, welcome back everyone. Let's again start. Okay, why are we talking about something as H? The thing is, this H is actually independent of the medium. This is actually independent of medium. It does not depend upon the medium. We wanted to actually define a term which does not depend upon the medium, so that we can compare how different materials behave in different magnetizing field, not in different medium, right? So that's why we defined something that is called as H. Now again, something that is called as magnetic susceptibility, which is nothing but I upon H. By the way, I has also got the unit as ampere per meter. This thing also has got unit as ampere per meter. This one has also got unit as ampere per meter. So that means this will be unitless, dimensionless. Is that clear? So this basically just tell you one thing. Let's suppose I've kept two types of material in same magnetizing field H, right? Same magnetizing field, and I am seeing one of them is getting more magnetized. Now you are going to ask me, sir, how do you know that it is getting more magnetized? Because it has more number of magnetic dipole moments are there in unit volume, right? So I is more. So if let's suppose if this one is getting more magnetized than this, when kept in same magnetizing field, I will say this one has more magnetic susceptibility. All right, that's it. So that's how you define magnetic susceptibility. It will be easier for you to actually remember these things. Now this entire page contains all the formulas, so hear me out carefully. Your concept will get cleared in one shot. What are we talking about in this formula? We are saying the net magnetic field in the material is the vector sum of two things. One, the applied magnetic field plus the induced magnetic field, which if you are going to read in NCERT, you are going to also find a line they have said that the net magnetic field is actually a function of two things, or two things contributes the net magnetic field. One is external factors, one is internal factors. So this induced magnetic field is the internal factor that we are talking about. Acha, we have already defined how to write B naught. Just now we saw that H can be written as the ratio of B naught upon mu naught, so that we can get a term which is independent of the Which is independent of the medium. Next thing is, we'll say that this particular material will have more induced magnetic field if there will be more intensity of magnetization. A very simple logic, please understand. This value will be more if there will be more intensity of magnetization. That means again we'll use a proportionality constant as mu naught. So B naught comes out to be mu naught H, Bi comes out to be mu naught I. Let's substitute it over here. We'll get a formula something like this, and this is very important. This particular formula is very important. You might use it, right? After this, take mu naught common. Then again we have seen, if we'll take H common, I upon H we'll actually see that I upon H will come over here. This I upon H is nothing but magnetic susceptibility, and that's how we actually make one formula and then another formula, right? So another type of formula is going to be B upon H, BM equals to mu naught into H times 1 plus magnetic susceptibility. Now again, if I'm going to write BM upon H, this will be absolute permeability of any medium. What was B naught upon mu naught? This was mu naught was absolute permeability of free space. So BM upon H will be absolute permeability of that particular medium, is equals to 1 plus magnetic susceptibility. And that's how you're going to get to this formula. Please remember it. And now another thing, mu upon mu naught can be also written as relative permeability. See, in a way there are only three formulas. First is these two terms. 1, 2, magnetic susceptibility is actually nothing but just a number. These two terms. Next is, just understand that the total magnetic field in a material is because of B naught and because of induced magnetic field. Induced magnetic field will be directly proportional to intensity of magnetization. Proportionality constant will come out to be as mu naught. And also B naught is equals to mu naught H. We have already covered it. After this, we have done nothing. Each step is just a slight manipulation, nothing else. Got it? All right. Quickly tell me if you have any doubt. Quick. Now next thing is going to be, we can classify the materials as diamagnetic, paramagnetic or ferromagnetic on the basis of their susceptibility and many other things as well, right? But first is magnetic susceptibility is actually quite important. Like for example, as if you are going to talk about the diamagnetic materials, they don't have the individual magnetic moment. Their atoms don't have the individual magnetic moment. All right. And if someone is saying that they have got negative susceptibility, by the way, it is negative and small. Negative susceptibility basically means that they are actually getting repelled from the applied magnetic field, or they are moving from strong magnetic field to weak magnetic field, right? So paramagnetic has positive and small value, and whereas ferromagnets have large and positive values. So quite a distinction we have got over here. So diamagnetic have negative magnetic susceptibility. That means they get repelled by an external magnetic field. Paramagnetic materials do get attract, but it is a very weak phenomena. Ferromagnetic materials get strongly attracted by external magnetic field. Got it? So that's why their magnetic susceptibility for ferromagnetic is positive and large. Paramagnetic is positive and small. Diamagnetic is negative and small. Got it? Hopefully everything is clear till this point. Now let's understand some of the more important points from diamagnetic material, and see, these are quite factual things, so you will have to remember it. they have a tendency to move. If any material is moving from a strong region to a weak part of an external magnetic field, that means it is getting repelled, right? So a magnet repels a diamagnet. Is it clear? The resultant magnetic moment in an atom of an, please understand what this statement means. This statement basically means that the individual dipole moment is zero. Individual magnetic moment, individual magnetic moment is zero. Please be comfortable. When I say dipole moment and I'm talking magnetism, I am meaning magnetic dipole moment. Do you remember we started our class with this concept that there are going to be two types of material. Basically, there are going to be two types of material in which individual atoms doesn't have a magnetic moment and in which individual atoms have magnetic moment. Now, from this, two other categories will be we'll discuss, right, which are paramagnetic and ferromagnetic. Is it clear, right? So there's going to be difference between them, but we'll see. Then examples are very, very important. So out of all of these things, examples of these things are very important. For example, please remember bismuth and copper. Right, bismuth and copper are the most important one, but still other than lead, silicon, nitrogen, water and sodium chloride is also important. Superconductors are metals cooled at very low temperature which exhibits perfect conductivity and perfect diamagnetism. Just remember that perfect diamagnetism basically means that this relative permeability comes out to be zero. What do you mean by relative permeability? Relative permeability is permeability in that medium divided by permeability of free space. So it is a concept related likely like relative refractive index. You can understand it in that way. So in this case, mu just becomes zero. So it is a perfect diamagnetism. Got it? So see, mu naught can't be zero. Mu naught has got a value. What is its value? 4 pi into 10 to the power minus 7. All right, done. Next is a superconductor repels a magnet by Newton's third law, and this is just a case for this is called as Meissner effect. Not that important, but please remember that yes, we usually use this concept in some of the trains as well, right? Moving on, now let's talk about paramagnetic materials. Now, as we have discussed, paramagnetic materials get attracted, but they get weakly magnetized or weakly attracted, right? And they have a tendency to move from a region of weak magnetic field to strong magnetic field, but this is a weak phenomena. The individual atoms or ions or molecules of paramagnetic materials possesses permanent magnetic moment. But the thing is, when you are going to talk about the entire lattice, the entire structure or material, the net magnetic moment will come out to be zero. Done? Examples are aluminium, sodium, calcium, oxygen and copper chloride. So please do remember the examples. I am again explaining again and again. Moving on, next is Curie's law. Very important for let's say they might just tell you to define Curie's law. Got it? Curie's law is the magnetization of a paramagnetic material is inversely proportional to the absolute temperature and directly proportional to the applied magnetic field. It means that we all know what magnetization is. Magnetization is capital M. So it is directly proportional to the applied magnetic field and inversely proportional to temperature. That's it. And this C is actually a Curie's constant. Got it? Quickly, doston, tell me if you have any doubt. Quick. Please understand one thing. Please let me now stop. Let me stop teaching and let me start explaining something to you. Today is 18th, right? We have almost finished. The 18th is almost finished. When you are going to when it will be 20th, you will think that at least, I mean, if I'll get 2 more days, I'll complete my course. Are you getting it what I'm trying to say? Or even not complete my course, you will say that, sir, if I'll get even 1 more day, this physics paper will be really good. So the only thing that you can do right now is that you can study, and study with a plan. Without studying, without a plan, you will be wasting your time, and then again there will be lots of things remaining at the last. So right now time requires two things. One is to study, and second is to actually study with a speed. So quickly complete things that you are studying. Don't wait on a particular chapter, right? Let's move on. So Curie law, this is also one more important thing. Curie law holds good for high temperature and not for strong magnetic field. These are some facts. You're not going to, you're not going to use lots of brain to remember all of these things, right? Just revise once and twice, everything will be fine. Now let's talk about ferromagnetic materials. Substance which gets strongly magnetized, we have already studied. That means these will have the value of magnetic susceptibility in order of some hundreds, right? So it will be far more greater than 1. That's what we can write. They have a strong tendency to move from the region of weak magnetic field to strong magnetic field. Individual atoms possesses dipole moment, I have told you, right? So what is the difference between paramagnetic material and ferromagnetic material? What happens in ferromagnetic materials is, now please understand, I am explaining it something to you. In ferromagnetic materials, we have got something that are called as domains. These are small, what we can say, small sections. In these small sections, the dipoles are in one particular direction. Although still the net magnetic moment of a normal ferromagnetic material will be 0, because still it is the randomness will the magnetic moment will get sum up to 0. But when you are going to apply an external magnetic field, it will be easier for the external magnetic field to align all of these dipole moments, right? So this is an important point, and also there are some another neighboring coupling kinds of things, but those are not in your course, so you don't have to worry about. All right, coming back to ferromagnetic materials, that's why I explained that something that is called as domains kinds of thing happens in ferromagnet and not paramagnetic, because this point is same in both of them. So what makes ferromagnetic materials different than paramagnetic material? I answered that, right? In non-uniform magnetic field, the sample tends to move towards the strong magnetic field. We have already discussed that. Hopefully everything is clear. Now see, again, ferromagnetic materials will be categorized into two ways. One is hard ferromagnets, another is soft ferromagnets. Hard ferromagnets are those materials which retain their magnetic properties. So even if when you are going to remove the external magnetic field, hard ferromagnets will behave like permanent magnets. Example of hard magnets are, now this is also again important, alnico, that means all alloy of aluminium, nickel, cobalt, copper and lodestone. Alright, soft iron are in which magnetization disappears as soon as the external magnetic field is removed. Examples are iron, cobalt, nickel, gadolinium. The relative magnetic permeability is greater than 1000. So this is also important. Lots of notes from here, right? You're going to get each and everything. How ferromagnets attract. After, if a ferromagnetic material is kept in an external magnetic field, all of its dipole will get aligned in a particular direction. It will start behaving like a magnet, and then it will start to attract another magnetic materials. Is that clear? Can we start some questions on this then? Acha, by the way, ferromagnetic this property depends upon temperature. At enough high temperature, it becomes paramagnetic, right? And that temperature will be known as Curie temperature. And again, you have got a law over here. So two laws only from this small topic, but please remember it. How attracts, they attract quite strongly. Fine. Can we move on? Can we move on to some questions? Very easy questions. Which of the following pairs is that of paramagnetic materials? Quick, 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 quick. 60 seconds. Which of the following pairs are of paramagnetic materials? Kevin, we have completed these things in our class recently, so let's quickly do. And by the way, these questions are different. Clear? Bhai, aluminium is good, but copper is aluminium is fine. It is paramagnetic. But bismuth, copper, we have remembered, na? This is actually a diamagnetic. Isn't it? And sodium is also paramagnetic and calcium is also paramagnetic. So it should be B. Iron is actually again ferromagnetic. Out of this, then lead is again diamagnetic. This is ferromagnetic. So is cobalt and nickel. They both are also ferromagnetic, isn't it? Just now we discussed it. All good? Can we move on? So the correct answer is going to be option B. Only 20%. Hilaria, Kevin, very good. Quick. Magnetic susceptibility of diamagnetic material is small and negative. Easy questions. Small and negative. Which of the following has its permeability less than that of free space? What are they talking about? They are saying that which one of them has their permeability less than of free space. That means they are saying that tell us which one has got mu upon mu naught less than 1 or relative permeability less than 1. Is that correct? That's what they mean to say, na? Think about it. Quick. Very good. Copper. Copper is going to be the correct answer because copper is a diamagnetic material. Whereas aluminium is paramagnetic, and for paramagnetic, although this ratio is small, but it is greater than 1. For paramagnetic, mu r is greater than 1. Got it? What about copper chloride, and what is copper chloride, by the way? What is going to be copper chloride? We'll have to check, yeah. Copper chloride is also paramagnetic, dosto. And nickel, we know that it is ferromagnetic. So its value is quite large. Just now we saw that its value is greater than, I think, around in some 1000 range. Done? Everything's clear? I'm explaining with as much explanation as possible. Okay, now let's move on. Let's move to the next question. From this, you are going to expect questions like this only. I mean, else what else they can do? They can just tell you to explain the working, they explain the structure of ferromagnetism and something like that, right? So hopefully you can write all of those things as well. Diamagnetic substance exhibit magnetism. Diamagnetic materials do not exhibit magnetism. They do not have permanent. So reason is true or assertion is false. Is that clear? Well, they might exhibit magnetism, but you will have to actually do not have permanent. Well, this is absolutely true. They don't have permanent magnetic dipole moment. I think we don't have an option for this. Why reason is false? Tell me why do you think reason is false? Why do you think reason is false? Acha, they don't have permanent magnetic moment. Well, you know what? Well, most probably they are talking about when this dipole is kept in external magnetic field. When this material is kept in external magnetic field. By the way, also remember the diagrams like this from NCERT. So it will show magnetism when kept in external magnetic field. So this one will be true, and then this will false. Do not have permanent magnetic dipole moment. Well, yes, they do not have permanent magnetic dipole moment. So, but I think B should be the most appropriate option out of these. B should be the most appropriate answer according to me. Now we have completed from this particular part. Let's start electromagnetic induction. All right, I have solved sufficient questions from this small topic also. Let's start electromagnetic induction. Again, let's come back to some conceptual topics. See, from electromagnetic induction, the important topics are going to be Faraday's law. Very important, because numerical can be also framed. Along with it, Lenz's law. And then you can, I mean, there will be only two more topics left, that is self-induction and mutual induction. So it depends upon you. But these two topics are very important and conceptual, right? So let's start one by one. If you are going to talk about Faraday's induction law, it basically tells you the magnitude of the induced EMF in a circuit is equal to the time rate change of magnetic flux through the circuit. What do we mean by this? Let me explain. First of all, you will have to define something that is called as magnetic flux. So again, magnetic flux is going to be nothing but BA cos theta, or just B dot A. Right? Now what Faraday, actually there were two things. One is Faraday laws, the another is Faraday's experiment. In Faraday's experiment, he saw that, let's suppose that we have got a solenoid over here. We have got a solenoid over here, and we don't have any current source for this particular thing. Right? And we have got a bar magnet at this point. I am summing up the whole experiment for you. What he observed is that if there is a relative motion between bar magnet and solenoid, then there was a deflection in this galvanometer. So this resulted in deflection in galvanometer. Acha, so I mean, obviously there were no sources of current in that solenoid. So he said that, okay, now we are going to call it as induced current. which was produced from induced EMF. That for finding out the magnitude of that induced EMF, we have got Faraday's law. Is that clear? So that induced EMF can be written as minus, or I can simply rewrite it as directly proportional to minus d phi by dt, the rate of change in magnetic flux. If we are talking about just one loop, if there are n number of loops, we can talk about it that as well. But first of all, proportionality sign comes out to be 1. So this become E equals to d phi by dt with a minus sign, and if there are n number of turns, then you can also write E equals to minus n d phi by dt. So if you have got a loop which has got a resistance and magnetic flux is changing, so you can also find out the induced current using E by resistance. And over here we are going to just talk about magnitude. So 1 upon R times d phi by dt multiplied by the total number of turns. Now please see, we have got two things over here. One is the magnitude of the induced EMF, and second thing is, why are you using this negative sign? This negative sign is used to represent the direction of the induced current, right, which was governed by the Lenz's law. So now we'll have to move to Lenz's law, and then again we'll club them together and we'll solve some questions from last year, right? Lenz's law basically says that the polarity of the induced EMF or the direction of the induced current will be in such a way that it will try to oppose the change that has created it. I'll give you an example. If you remember, we talked about this thing. If there is a relative motion between these two things, I am explaining Lenz's law and please try to understand it. Let's suppose this bar magnet is coming close to this solenoid with some velocity. So we are going to say, because this bar magnet is coming close, the flux that is linking with this surface, this flux is getting changed, right? And because flux is changing, induced EMF is getting produced. And what is the role of this induced EMF slash induced current? The role is, the direction of the induced current will be in such a way that it will oppose the change. Now what is the change? Change is this. I mean, the real reason, the real culprit why magnetic flux was changing is not this magnet or solenoid or magnetic field. It is the velocity with which the bar magnet is moving. So current will produce in such a way, current will flow in the circuit in such a way that it will form a north pole on this side. See, this is where you face trouble. Why only north pole, sir? And why, if it is north pole, that means the direction of the current will be something like this. Why is that? Because again, induced current's role is to oppose the change. So change was, it is coming close, so it will make north pole on this side, so that this north pole can repel the coming magnet. Is that clear? So very simple. Lenz's law, we can have another examples also for Lenz's law. Let's take another example. Let's suppose that you have got a current carrying conductor. First, tell me in the chat box, number of students who are still present, tell me in the chat box if this is clear to you. Let's suppose we have got, or forget it, let's not use a current carrying wire. Let's just say that we have got a we have got a loop, not current carrying, a normal loop, and we have got a magnetic field. You can see that direction of magnetic field is something into the plane, and magnetic field is actually a function of time t, which is given as 2 plus 3t. Write down in the chat box direction of induced current, clockwise or anti-clockwise. Write it down. Very good, Kevin, Hilaria, Hariram, Saundarya, good, Surya, very good. I have written the magnetic field. By the way, can you see by can you observe by seeing at the magnetic field? Yes, sir, this is actually a changing magnetic field. what we can see is this magnetic field is actually increasing with time, right? So the main culprit is this, that magnetic field is increasing. The main culprit is magnetic field is increasing. Acha, it is increasing in which direction? Into the plane. So induced current will be in such a direction that it will oppose the change. So it will be anti-clockwise, just so that it will create its own magnetic field in opposite direction. See, it's not like it always, the induced magnetic field is always in the opposite direction. I'm not saying that, right? Many times what students feel is, I'll give you another example. Let's say something like this. Now the magnetic field is 2 minus 3t. Now tell me the direction of magnetic induced current. Now it will oppose the change. So what is the change? Change is that magnetic field is decreasing in magnitude. So if it is decreasing, obviously you, this is going to take place for a very short time. After 2 by 3 seconds, magnetic field will become 0 and then direction will change. But hopefully you are getting it what I am trying to say. So till the direction is not changed, current will be in such a way that it will support the magnetic field and oppose the change. So always remember that it opposes the change. It might support or oppose the magnetic field. Is it clear to all of you? Quickly tell me in the chat box. So now clockwise, something like this. Now if someone tells you to find out the induced EMF also, so just ask them what is the area of this thing. So let's suppose the area of this particular loop is 10 meters square. So induced EMF will be minus d. This is what this minus sign signify, that it opposes the rate of change. Can you please understand? This is known as d phi is change, by dt is rate. So d ba cos 0, right now it is cos 0. You need to mind all of these things, divided by dt. Area is not changing, so it will come out minus 10 times dB by dt. If I am going to differentiate that will come out to be 3, isn't it? That will come out to be 3, right? So this will be minus 30 volt, or the magnitude is going to be 30 volt. Now let's suppose it has got a resistance of 10 ohm. So current will be magnitude 30 volt divided by 10 ohm, that is 3 ampere. Is that clear? Quick doston, is that clear? Will you be able to find it out? You have a doubt, Surya, you have a doubt in direction. I'll again explain it. Direction is found out by simple rule, simple law which says direction of induced current will oppose the change. That's it. Good doston, keep going. Let's solve some problems. Let's solve some problem that will also that will actually benefit us. This is from 2024, past year 2024. Only the change, yes, only the change. Two coils are placed near each other when current in one coil is changed at the rate of 5 ampere per second and EMF of 2 millivolt is induced in the other. Acha, they have talked about mutual inductance. We have not yet discussed mutual inductance, let alone mutual inductance. We have not at all discussed self-inductance, but still it is not a big problem. If you are going to talk about self-inductance, first let's discuss what self-inductance is. Initially what we were discussing is that the magnetic flux is changing because of some external factor. We are not talking about change in magnetic field, we are not talking about change in area, we are concerned with magnetic flux, and magnetic flux can change in various ways. Either B can change, area can change, orientation can change, or any of the combination can change, like B and area both gets changed, something like that, right? The thing is with self-inductance, if let's suppose the current flowing in the wire itself changes. Are you getting it what I'm trying to say? Let's suppose that you have got a solenoid like this. and magnetic field is produced from because of this wire in such a way. So we are saying that okay, magnetic flux is also getting linked. Now if I am going to change the current in this solenoid, this magnetic flux will change. Is that clear? So this means that the induced current, which is the magnetic flux which is getting because of the change in current in the conductor itself, right now we are not talking about any external factor. So we are going to say that the magnetic flux is actually directly dependent on current. Well, more the value of current is going to be, more is going to be the flux. Someone was talking about, sir, let's do the solenoid. Magnetic field due to a solenoid is going to be mu naught Ni. Flux is Ba cos theta. So that means flux directly depends on B directly depends on I. So can I write phi directly depends on I? So this proportionality constant comes out to be Li. So in now when you are going to write like minus N d phi by dt, now you can also rewrite one more formula from here, which is minus N L di by dt. Okay, right now you don't have to write number of turns. So we'll simply write minus L di by dt. What does this mean? I'll explain it to you in a very short way, then we'll move on. Okay, then we'll move on. Good. What we are trying to say is, let's suppose that you have got a wire like this. This wire has got some self inductance, or usually called as inductor, right? This L is actually called as inductor. Its SI unit is Henry. We are going to use this unit and use this property in alternating current quite often, right? Why in alternating current, sir? Because if in mostly in DC circuit, current is constant, na? Or it gets saturates to very quickly. So there is no role of inductor. So if there is no change in current, there will be no problem. Every other wire looks something like this. This symbol shows the inductor property L. And when we are writing L, we mean to say this is the coefficient of self inductance, right? Done. Now the thing is, if let's suppose a current I is coming and this current I is actually increasing, its nature is actually increasing. Got it? It is increasing. So this inductor will actually produce a fictitious battery, something like this, to oppose this change. And this EMF, the EMF of this fictitious battery will be actually equals to L di by dt. And this minus sign was just to show you that it is opposing something. It is opposing the change. Is it all good? Quickly write down in the chat box if this concept is clear. That's why I'm saying that if you have got a DC circuit, inductor has got no role, because then di by dt will be 0. There is no change in current. Di by dt will be 0. So please don't say, sir, there will be energy gap. But there will be a clean wire. There is no potential difference. Quick, doston, everything's clear with this concept? No more doubts? Let me see if I have some questions from self-inductance. Let's check this one. A circular loop of radius r carries current I. Another circular loop B of radius r equals to r by 20 is placed concentrically in plane of the magnetic flux linked with B is proportional to. Please, let's see if you can do it. Quick, dosto. Find out the answer. circular loop of radius A of radius R carries current I. Another circular loop is placed concentric in plane of A. So what they are trying to say is, you have got two circular loops, let's suppose something like this, and another one is really small, placed concentric like this, right? And it has got current I. Now at the center, magnetic field will be something like this. And magnetic field at the center will be mu naught I upon 2R. So magnetic flux linked is going to be mu naught I upon 2R times area of this plane दोस्तों. They could have also told you to find out the total flux, area of this plane. So that will be pi into R square. Although we don't have to worry about the value, because all we need to do is we need to find out the relation which is coming out to be this. You tell me if you have any doubt other than this. Everything was easy. Quick. A should be the correct answer. Very good Aditi, Kevin, Kirti. Good Aditi, Hilaria, good. Acha, by the way, although we have not talked about mutual inductance, but now you can have an idea. Although you might have done it. Now, when you are going to talk about mutual inductance, now we have got two coils, right? Like for example, as you can understand it using this diagram also. If you want to know the induced EMF in this particular thing, right? So the flux linked with this secondary coil is directly proportional to the current in the primary one. And that's how we can write down over here as mutual inductance M. Is that clear? So similarly, you can use E equals to magnitude E equals to M di by dt also over here. You will get your answer. Quickly tell me, just M di by dt. See how simple it is. You don't have to worry about anything else. A very simple concept from Lenz's law can make you solve each question. Quick. Let's quickly solve it. They have told you that two coils are placed near each other when the current in one is changed at the rate of, so see, di by dt is 5 ampere per second and induced EMF is 2 millivolt. So you just have to find out the self-inductance. That's it. Is it clear? A is going to be the correct answer, or what? Is your answer coming as A? I don't know, but still A. Good. Let's move on. Let's quickly move to next question. Let's check this one. Let's quickly do it, dosto. Quick. How that B naught? Swaminathan, can you please ask your doubt again? I just saw it. Quick. 0.4, yes. Okay, now let's move on to this one. A coil of n turns is placed in a magnetic field B such that magnetic field B is perpendicular to the plane of the coil. Okay. B changes with time, something like this, where T is the time period. The magnitude of the induced EMF, it will be maximum at. Think about it. Quite easy. Right? Don't chat in the chat box here. Don't use my chat for these purposes. Quick. So induced EMF is going to be minus n d phi by dt, right? So I'll simply write it as minus na db by dt. So that is going to be minus na. If I'm going to differentiate it, this will become plus b naught. Achha, by the way, I'll leave some space also. B naught over here, I'll be having 2 pi by t into sine 2 pi by t into small t, right? Now they are saying that this induced EMF should be maximum. So maximum value is going to be this. Now whatever this is, we don't need to worry. It will be maximum when this thing will become sine 90 or like sine 90 plus 2 pi. Is that clear? Sine 90 plus 2n pi. Sorry dosto, sine 90 plus 2n pi. So this will be when it will be sine 90 or pi by 2 plus 2 pi. So let's first find out for pi by 2 only. So 2 pi by t times small t should be actually equals to pi by 2. So small t would be capital T by 4. So this is going to be they are talking about maximum value at sign. So obviously negative positive sign is not going to create a difference. So it will be maximum at this point, then it will be maximum at this point. So n1, 2, so on. So I think it will be B. Write down in the chat box if you have any doubt, else we'll move on. No, it's not none of these. Can you please repeat the last question quick? My last question was quite easy. You tell me about this one if you have any doubt in this particular question, else we'll move on. Last question of magnet of B. That's what I've said, B. Quick. None of the options are matching or what? It will be at T by 4. Basically this will be at 2 pi T into n pi by 2. So pi can get cancelled out. So T will come out to be n T by 4. Acha, but the thing is, yes, this should be odd, na? This should be odd. That's the problem. This should be odd. Not just pi by 2. This should be odd. So this is going to be 2n plus 1 pi by 2. Yes, this answer is going to be none of these. Answer is going to be none of these. Sorry. Because in this one, you will obviously have, when n will be 2, it will become 0, na? So it can't be. Answer is going to be none of these. But wait a second. Okay, might be some problem with 2024 this question. I'll check it again. MCQ will be of 1 marks only. Bhai, let me check what answer have they given for this particular thing. Let me check, then I'll come back to you. But for now, this was the correct way to do it. Now let's come back and see. The thing is, we have not yet completed this chapter. We are going to actually use these concepts again in alternating current also of L and all of these things, right? Let's look at this question. A square shaped coil of side 10 centimeter having 100 turns is placed perpendicular to a magnetic field which is increasing at 1 Tesla per second. Easy, solve it by yourself. 60 seconds, take it. Induced EMF is going to be, magnitude of induced EMF is going to be NA times dB by dt. So N was 100, area is 10 centimeters, so 0.1 times 0.1, dB by dt is actually 1. So answer is coming out to be 1 volt. D is going to be the correct answer. Is it so? Clear? Kevin, good, very good. Very, very good. Let's move on. See, now let's talk about alternating current, right? Let's talk about alternating current. And in this chapter also, we can start with directly with some questions also, but let's begin with LCR circuit, right? You will get poll in the chat box only. Just write down your answer. Just write down your answers. Correct answer is option D. Very, very good. Very good, everyone. Bert, Kamari, Kevin, Surya. Chalo, let's move on. Your derivation will not come. You just have to remember the formulas and also the phasor diagram. Phasor diagram is important. Let's suppose we have got a source which has got V0 sine omega t plus phi, right? So the phasor diagram will be something like this. This is the reference line. And now potential is already at, we can say potential is already at some angle, some initial phase, right? Or see what I'll suggest you to do is just remember one thing. If you have got a purely capacitive circuit, in purely capacitive circuit, in that case the voltage lags and current leads, right? So I'll also don't require these things. I'll simply draw the phasor diagram. So let's say this is actually R. Let's say this is XL minus XC. This is XL minus XC. So this is going to be your impedance triangle, which is Z, and Z will be under root of R square plus XL minus XC whole square, right? Now if someone asks you what IRMS is going to be, so IRMS is going to be VRMS upon Z. See, why I am telling you to not to worry about anything else is that derivation has been removed. You don't require to derive whether the voltage is lagging, whether in capacitance current is leading or voltage is, you don't have to derive all of those things. All you need to do is remember the phasor diagram, right? So phasor diagram would be, this was the impedance triangle, and similarly you can draw the phasor diagram also. This is going to be VL minus VC, this is going to be your VI, and in this direction you will have your resultant value, right? Now after this, two things over here. If you are going to talk about XL, the value of XL will be omega L, and the value of XC will be 1 upon omega C. Done? Because after LCR circuit, the next important thing in this particular chapter is also, I mean, hopefully you all know that, okay, we can rewrite VRMS as V0 by root 2. I can rewrite IRMS as I0 by root 2, all of these things, right? When we are going to talk about something that is called as resonance, resonance is actually a circuit in which the natural frequency of the circuit is equal to the frequency of the applied voltage. So for example, this is going to be the case when XL will become equals to XC. So this will happen when omega L is actually equals to 1 upon omega C, or omega will be actually equals to 1 upon under root LC. So this is the angular resonance frequency. Also we can rewrite this thing as this thing can be written as frequency equals to, this is resonance frequency 1 upon 2 pi under root LC. Now please let me explain each and everything in detail all over again. See what we are trying to say. We are trying to say that we have not used RL circuit, RC circuit, purely L circuit. We have not used any of those. We have said let's quickly draw an LCR circuit and let's draw the impedance of it. Impedance basically means the net. Well, we don't have any another term for impedance, but you can understand that this is something that is called as R equivalent, right? So impedance basically means the entire sum of R, L and C, what hindrance they are producing to flow of current. So the thing is, instead of talking about individual elements, we have derived it and then we have talked about all the formulas. Now if someone tells you that we have got only R and L but no C, just substitute Xc equals to 0. Just substitute Xc equals to 0. If they say that you have got R and C but no L, just substitute XL equals to 0. Or if someone says you don't have resistance in a circuit, you only have XL and XC, what you can do is you can just put R equals to 0, right? Now the next thing is, let's suppose that we have got a circuit in which we have got all the three elements, right? We have got a circuit in which we have got all the three elements, but still we want the current to be maximum. So what we are going to do is we can arrange the frequency in such a way, if this is the frequency, XL and XC will cancel out each other, and at this frequency, circuit will behave as purely resistive circuit. Now think about it. We were discussing that current is actually equals to, or Vrms is actually equals to IRMS, or see, the thing is, any current is actually equals to V divided by impedance. Is that clear? Now if we are going to say that we want to actually have the minimum value of this impedance, the minimum value of this impedance can be nothing but R. Z minimum is actually R. Is that clear? Please. And when this value is going to be minimum, this current will be maximum. So at this particular frequency, two things is happening. The circuit is behaving as purely resistive and we are getting a maximum current at this point. So you must also be able to draw the graph of this resonance circuit and also define a factor that is called as Q factor. So this is maximum current V by R. That's what we have written, maximum current as V by R, because now you don't have any impedance or any capacitive reactance, any inductive reactance or capacitive reactance. You only have resistance. That's what you have written. So this is maximum current, right? This is maximum current divided by 2. That means there are going to be two frequencies, F1 and F2, at which you are going to get 1 by root 2 times of the maximum current, and this width will be known as the bandwidth, right? And if you are going to write down this formula, that is Q factor, this is your Q factor, this is actually nothing but XL divided by R, XC divided by R, or 2 pi FR L divided by R, right? Please understand once again, this is nothing but omega into L. Omega can be written as 2 pi F into L. Quick. How we got 2 upon, by how we got this? If you want to have maximum current, you will need minimum impedance, and for minimum impedance, XL must be equals to XC. They will cancel out each other, and if they will cancel out each other, then omega, this will become omega square. This will become omega square. At this step, this will become omega square upon 1 upon LC. So omega will be 1 upon under root LC. That's how we have got it. Tell me if you have any doubt. Quick. Quick. Not I mean quality Q factor is not very important, but still you can do it. Okay, now let's move on. Let's start some questions. The reactance of a capacitor of a capacitance C connected to an AC source of frequency omega is X. If the okay, ठीक है, let's quickly start it in pole. We have got a capacitor of capacitance C connected to an AC source of frequency omega. It is X. Okay, so capacitive reactance is X. Now they are saying that the capacitance of the capacitor is doubled. See how easy it is. And the frequency of the source is tripled. Then you have to find out the new reactance. Just a second. What are you saying? Have it. Acha. So sorry. Over here. Yeah. ठीक है. Fine. Happy. Now let's move on. Quick दोस्तों, alternating current. Are we getting answer? Quite easy now. X C dash will be nothing but 1 upon omega dash times C dash. So 1 upon, well, you can simply rewrite this thing as 3 times of omega, and you can rewrite this thing as 2 times of C. This will be 1 upon 6 omega C. Right? A option is going to be the correct now. Any doubts? Quickly tell me. Which of the following, by the way, option is A is correct. 100%, very good. But only 2 were able to answer it. Why? Quick. Which of the following statements about LCR circuit connected to an AC source is correct? If the frequency of the source is increased, the impedance of the circuit first decreases, then increases. If the net reactance XL minus XC of circuit becomes equal to its resistance, then the current leads the voltage by 45 degree. At resonance, the voltage drop across the inductor is more than that. Acha, theek hai. At resonance, the voltage. Okay, so till now, if you are able to understand the resonance, you know, by at resonance, XL is actually equals to XC. Is that clear? So whatever the potential drop is at L is exactly equals to at C. And I have also explained it to you that if let's suppose this is the potential drop at resistance, and this is at inductor, this is at capacitor, this is at resistance. So these will cancel out each other because they are equal. So it can't be C and D. So now quickly write down the answer. Quick दोस्तों. I have given you a hint. Good. See, this impedance triangle will solve many of your problems. If you remember, in the very start also we talked about something like this. So here we had XL minus XC. Here we have got R. So you can draw Z over here, right? This is going to be, let's say this is going to be phi. This is your XL minus XC. So what I am trying to say is that tan phi is nothing but the magnitude of XL minus XC divided by R. Now what they are saying, if the net reactance XL minus XC of a circuit becomes equals to its resistance, if this thing becomes equal, that means XL minus XC becomes equal to R, then definitely this will be 1, and this, in this case phi will be pi by 4. So option B is absolutely correct, which makes option 1 as wrong, and you will note it down. Quick. Not A, it's going to be B. Quickly see. And ask your doubt if you have any. Okay, this was not part of poll, no worries. But if you have any doubt, please let me know. Can we move on to the next one? Can we move on? An inductor, a capacitor and a resistor are connected in series across an AC source of voltage. If the frequency of the source is decreased gradually, the reactance of, then you have got options. Easy. This one is easy, easier than the last one. Opening poll for this particular question. Think about it. You have got an inductor and a capacitor and a resistance, right? This does not depend upon the frequency. XL is omega L. XC is 1 upon omega C. So we know that if this is actually directly proportional to omega, this thing is inversely proportional to omega. So now you can easily answer it. For if you are decreasing it, for inductor it decreases, for capacitor it increases, isn't it? Clear? Very easy peasy. Quickly tell me दोस्तों. Quick. Acha, by the way, there's one more thing. I think average powers derivation has been also, if I'm not wrong, it has been removed. But still remember the basic formula. Okay, let me find one more question for you. I think it has been removed. But still, have a look at the formula of average power once. Please have a look at average power and solve this question right now. See, this thing is I was talking about. I think I remember they said that they're going to only ask the qualitative treatment for this particular thing. The formula that came out to be as I naught by root 2 V naught by root 2 times cos phi, and cos phi is the power factor. Okay, and remember it. Cos phi is very important. Cos phi is your R by Z, right? And for right now, do this problem. Do this one. An electrical lamp is designed to operate at 110 volt DC and 11 ampere current. Okay. If the lamp is operated on 220 volt and 50 hertz AC source, see, this is the thing. Whenever they talk about something like this, na, first of all, you all know that this is actually nothing but VRMS. This particular value is actually VRMS. Alright. And when they are saying that this particular device is working in DC, then what we can actually do is we can find out the resistance. So resistance will be V by I. So 110 divided by current is 11, that is going to be 10 ohms. So you have got what resistance is going to be, right? If the lamp is operated in this, then find out the inductance. Now you can find out the inductance. You have got VRMS, you have got current, find it out quick. I'll convert it into integer type. By the way, what was the answer for the last question that we did it in poll? It was A, right? Okay, I think it was B. Still, no worries. Quickly, write down the answer for this particular question. See, if it is designed to operate at 11 ampere, na, current should remain 11 ampere, right? Now we know that resistance is 10 ohm. What else do we need to know? We need to find out the inductance. What we are going to do in the next step is, this part was completely AC, completely DC. So this was the DC part. It is now over. Now let's come back to our AC part. In AC part, we are going to say that impedance can be written as VRMS divided by IRMS, and which I am saying that should be 11 amperes. And VRMS is actually 220 divided by 11. So this is going to be 20. So Z will be under root of R square, which is square of 10, plus XL square is equals to 20. So XL square will be 400 minus 100. So XL will be 10 root 3. So which will come out to be 2 pi F equals to 10 root 3. They have already given 2 pi F. Acha, by the way, this is omega into L. So L will be 10 root 3 divided by 2 pi into frequency was 50 hertz. This is going to be nearly your answer. Solve it down. Solve it down. Nearly you will get as 0.55 millihenry. Okay. Quickly tell me in the chat box if everything's clear till this point. No. You don't have. Quick. Is it all good? See, if it is all good, I'm coming to EM waves. Coming to EM waves. Well, let me check AC generator. Just give me a second. Let me check. You are asking about AC generator. No, AC generator is in the course. It's not deleted. AC generator is not deleted. AC generator is not deleted, but it was not part of the last year problems. As far as I can see, it is not part of the last year questions. Okay. Now let's talk about electromagnetic waves. In electromagnetic waves also, derivation of displacement current will not be asked, right? Displacement current derivation will not be asked, but yes, please remember remember the why do we talk about displacement current? Remember all of those things. Okay, no break abhi no break. We have just given the break. Displacement current is the current due to changing electric field between the plates of the capacitor, right? See, one thing is clear. Let's suppose we have got a capacitor over here. Now you know what conduction current is, right? You all know what conduction current is. Conduction current is nothing but I, and that is dq by dt. So whenever we are going to talk about conduction current, we'll simply write it as I c equals to dq by dt, right? But what will happen if charge keeps on coming on this plate? The electric field in between of it, that is E, which is actually nothing but sigma upon epsilon naught or q upon a epsilon naught. Because this is actually, charge is changing continuously. So we are going to say that there is a changing electric field also. And because of this changing electric field, we have got displacement current. You don't have to derive it, but remembering its definition is equally important, okay, like before. And now this is one of the page from NCERT in which we have got all the equations of electromagnetism till now. This was your Gauss law, E dot A equals to Q upon epsilon naught. This was Gauss law for magnetism. This is very important for closed loops, because we said that magnetic field lines form closed loop. Then we discussed Faraday's law in electromagnetic induction. In this particular part, we are saying that this was Ampere's law, and this is the correction of Maxwell's. So this is your displacement current that we are talking about. This thing is your displacement current, ID, that is epsilon naught d phi by dt. So remember it. Very important. They might ask you in MCQ or something like that. Other than that, they will not ask you to derive it, right? So again, qualitative treatment only. This was Ampere's law. This thing is Maxwell's correction to Ampere's law. So this thing is now called as Ampere-Maxwell law. Mu naught times of ID. This is because of changing electric field inside a capacitor, right? So this was related with the displacement current part of the capacitor. Now after this, we talk about EM waves. This is now become really factual, and NCERT will help you a lot in this particular chapter. We are going to talk about different things. We are going to talk about properties of EM waves. We are going to discuss how EM waves are produced. We are going to say that oscillating charges produces EM waves. Oscillating charges produces EM wave, right? And then in this properties of EM wave, we are going to talk about everything else, like for example as sources, what are the sources, what are the uses, and everything like that, right? So this is now become really important. So notes are going to play a crucial role over here. So first of all, when we are going to talk about EM wave, first let's define what EM waves are. EM waves can be defined as a changing electric field which produces a changing magnetic field, right? And this gives rise to a transverse wave called as EM wave or electromagnetic waves. The time varying electric and magnetic field mutually perpendicular to each other and also perpendicular to the direction of propagation, and we have got an example over here. Please understand, this is an example in which the electric and magnetic field are perpendicular to each other and direction z of propagation. That means the electromagnetic wave is traveling in z direction. Electric field is oscillating in x direction, magnetic field is oscillating in y direction, and the wave is propagating, the EM wave is propagating in z direction, which is perpendicular to both x and y. Now please understand how you are going to write it down. This is the way, I mean, you might have seen this type of equations in class 11th also in waves. So similar kind of a thing, kz minus omega t, kz minus omega t, k is wave number. This z basically tells you in which direction the EM wave is traveling. Yeah, accelerating charges also, oscillating and accelerating charges both can do. Surya, accelerating charges is also fine. The difference between conduction current and displacement current, conduction current was old simple definition, rate of flow of charges is conduction current. Displacement current is because of change in electric field, right? Change in electric field. This thing is important. Please remember how you are going to write it down, right? Also, one more thing, direction of EM wave. Direction of EM wave will be found out by the direction of EM wave will be found out by E cross B, that will be actually equals to C. Like in this one you can see we have got I cap, J cap, K cap, that's a simple trick. So I cross J will be actually equals to K, right? So please remember, whenever you will be asked about the direction of electromagnetic wave, that will be also found, that will be found out by the cross product of these two things. Acha, by the way, it would be better if you'll write something like this, giving them unit vector. This is the best way, right? What was the second point? Direction of EM wave is a vector product of electric field and magnetic field. I have already explained. Is there any doubt? Quickly tell me in the chat box. Is there any doubt with the direction of magnetic field? Everything will be sorted. No break, abhi. But there is a lot of role in of electric field and magnetic field in EM wave here. Okay, good. Acha, we are going to talk about some properties also of EM wave. Let me check. I think I have got them. But before that, let's begin with some questions. And I'm starting the poll also for this. Let first read it. The phase difference between the electric field and magnetic field in an electromagnetic wave propagating along z axis is easy. 60 seconds will be more than sufficient. Quick. Do you remember what phase difference is, right? We talked about phase difference, slight phase difference in alternating current. See, by meaning of this phase difference, na, we mean to say ki, I mean, let's suppose when electric field is getting its maxima, at the same time as magnetic field is also getting its maxima. If that is the case, then we say that they are in same phase. Are you getting it what I said? For example, if you are going to see a diagram for EM wave, let's suppose this is your, and this is magnetic field. So when this is getting its maximum value, magnetic field is also getting maximum value. When electric field is getting 0, magnetic field is also getting 0. When this one is getting its minimum value, magnetic field is also getting its minimum value. So we are saying that they have got no phase difference, right? So please don't write 90 degree. They are oscillating at 90 degree. They are oscillating at 90 degree to each other and to the propagation of EM wave, but the phase difference is 0. Very simple thing. Hopefully you have got it. Quickly tell me in the chat box. Now also we'll start some questions related with the uses. Quick. So this was, I think the correct answer was 0, that is A. Let's start this one. Why only 33.33 got it correct? What was the C option? By 90 degree nahi hoga. If everyone's ready, everyone's good na? 90 degrees incorrect. A is going to be the correct. Alright. Let's quickly move to electromagnetic waves used to purify water. 60 seconds. Electromagnetic waves used to purify water, very basic thing. If you will walk to your kitchen, you will see, we will check your RO machines, you will see something over there. Quick. Correct? Very, very good. By infrared nahi, ultraviolet rays है इसका. Infrared. Ultraviolet rays is the correct answer, not infrared. B option. Very good. Let's move. Name the parts of the electromagnetic spectrum which are also known as heat waves. So please remember, heat waves are known as infrared. Infrared waves are also known as heat waves. All right. And the observed that are absorbed by the ozone layer. Which waves are absorbed by the ozone layer? Can you tell me? Ozone layer. Quick, quick, quick. Why do we use sunscreen? Why do we use sunscreen? X-rays, nahi. UV rays, ultraviolet rays, right? Correct. UV rays or ultraviolet waves, whatever you want to call them. These are some easy peasy questions from this chapter. Generally, they ask questions like this only. So it will be better that if you will actually read the NCERT thoroughly and try to memorize things, right? Because if question will come in MCQ, that will be easy. But if they'll ask you to write something like this, you must remember these things. Good. Acha, what? Write briefly one method each production and detection of these radiation. Can you write down? Can you do it? Can you write down one method each for production and detection of these radiations? quickly in the chat box. Sir, is this the easiest? Well, yes, I think easiest of all the chapters. That's what I think. Quick. So for yeah, this for infrared waves, the correct answer would be heated bodies. Right, and for ultraviolet waves, it would be current passing through gas, right? And detection of ultra infrared is something that is called as point contact diodes. And for these, it's known as ultraviolet detector. I think the device itself is known as something like this. Again, please check this thing in NCERT once. That's it. This was from 2024. This was from 2024. Let's move on to the next one. Quick. Which of the following electromagnetic radiation has the least wavelength? The electromagnetic wavelength which will have the least wavelength will have the maximum frequency. And energy. So think about it. Quickly do it. 60 seconds. Least wavelength, EM wave having least wavelength will have maximum energy and maximum frequency as E equals to h mu. Good, very good. Very good. So correct answer is going to be option A. Poll is not stopped. Very good. Great. E and B represents the electric and magnetic field of an electromagnetic wave respectively. The direction of propagation of the wave is going to be along E cross B, right? Is going to be along E cross B. Ajay, let me see if we can find out some Okay. If other than this, please don't forget to read the NCERT, and also add one more formula for magnitude, that E naught divided by B naught is actually equals to speed of light. So please also remember this formula in case they ask you any numerical. Yes. Done? Acha, let me do one thing. Before starting optics, let me complete. Okay, we can start optics as well. I was thinking of starting a dual nature of radiation, but let's first complete the optics. Yes, actually the thing is, leadership board for all the poll friends. Leadership board till now looks something like this. Kevin, very good. Hilaria, Saundarya, I think all three are from Yakin batch. Very good. Good. Achal, chalo, now let's talk about optics. In optics, again, see, for a very long time after magnetism, we haven't studied a derivation, right? Seriously, here you can actually expect 2 or 3 derivations from like mirror formula, lens maker formula, some things like that. So it is important for you to read those derivation, remember those derivation. The only trouble you are going to get is in those similar triangles kind of a thing. Other than that, you will face no problem. How to remember? Acha, let me, sir, E by B is used for derivation of energy relation. Yes, yes, you can find energy using that as well. See, the thing is, you are not going to face any trouble in derivation in optics unless and until you forget the assumptions of paraxial rays, angles, and all of those things, right? Chalo, let's quickly move. The first thing that we are going to see over here is very basic thing, है ना? First few things to are quite basic, which are actually nothing but laws of reflection and all of those things. So not going to waste your time. Laws of reflection. Hopefully everyone knows this, all of these things. ठीक है? Laws of reflection is the very first thing in which you are going to learn that angle I is actually equals to angle R, and they all lie in the same plane. The first derivation that you are going to see in your NCERT is for a spherical surface. By the way, plane mirror, you might get a question from plane mirror as MCQ. They might just ask you that what are the characteristics of plane mirror, image formed by plane mirror. Very easy. The image will be always virtual, always of same size, will be formed at same distance from mirror, right? All of these things. So if object is somewhere over here, image will be also at this point, at this distance on the other side, right? Simple things. Focal length of a plane mirror is infinite. So before spherical mirrors, you don't have a lot of things to do, right? After this, when you are going to talk about focal length of spherical mirrors, at this point you will have you will start deriving things. This is the derivation for F equals to R by 2. Although very less chances of CBSE to ask this, but still remember it that focal length is actually equals to R by 2. These rays are called as paraxial rays, which means that these rays are called as paraxial rays, which means that these are close to principal axis, which further means that these thetas are going to be small, right? So in this case, I'm going to simply write tan theta is theta. So theta will be written as tan theta will be written as MD. That MP and MD are going to be the same thing. So MP divided by CP, and tan 2 theta can be written as MP divided by FD. So all of these things, this is going to be the focal length, this is going to be the radius of curvature. Write down in the chat box if everything's clear. Hopefully all of these things are quite easy to understand, right? Is that clear? Clear? Can we move on? Now the next thing is mirror equation. Although mirror equation is quite easy for you, mirror equation is quite easy, which is nothing but 1 upon F equals to 1 upon V minus 1 upon U. It is very easy. Plus U. Mirror, we are not talking about lens. For concave, we usually take this thing as positive. For convex, we take this thing as negative. Generally, we take object distance as negative. If V comes out to be positive, that means it's a virtual image. If V comes out to be negative, that means it's a real image. And if you're talking about magnification, you'll have two formulas, minus V by U and HI by HO. All right. But you might ask, someone might ask you to actually derive this formula. This is the thing. This is the mirror formula. Concave negative and convex positive. Concave negative and convex positive. Why? Because you have got concave like this is considered as pole, and generally we take this thing to be negative and this side to be positive. All right, is it all good? Good. Quickly write down in the chat box, quick. And if you have got a virtual image over here, it will be read as with a positive sign. Clear? See, now the thing is, I'll let you read the mirror derivation, and it's not that difficult. We have used a concave mirror case. Remember the concave mirror cases. If the object is beyond C, then image is between C and F, right? So this is one of the case we have used over here, and we have tried to find out the formula. See, this is the object over here. You can use only two rays. One of the rays parallel and it is passing through focus, and these rays are getting intersected between C and F, as I have told you. Hopefully you remember ray diagrams from grade 10th as well, right? So this is going to be the focal length, this is going to be the image distance. Now what are the triangles that you need to understand over here? You need to take two triangles which are A dash, B dash, F and MPF. See, what are A dash, B dash and F? A dash, B dash and F. This is the triangle that I am talking about. This is the triangle. All right. And next triangle is your MPF. MPF. This is the triangle. And please understand that we are assuming that this is a straight line, MP. MPF. And because they are similar, we are going to write B dash A dash upon PM is equals to B dash F upon FP. Now see, you don't have any other option other than this to actually remember these things. You will have to practice one or twice and you will get it. The thing is, they might ask you the derivation of mirror formula. They have done this. They have done this in last few years, right? So please understand, this is the only way. All you can do is you can remember it from this path, that you will consider these cases. Object will be beyond C, image will be between C and F. We have got para-axial rays, that means this MP will be considered as a straight line, and then two triangles, one A dash, B dash, F and second MPF. Right now B dash, A dash is actually the corresponding side to B dash. A dash is obviously going to be PM and B dash F is corresponding to FP. Is it all good till this point? Quickly tell me in the chat box. Very good, right? So after this, PM can be also written as AB. Can you please see, this PM can be also written as AB. So that's what we have done at this point. So we have written, instead of PM, we have written it as AB or BA. Now since angle APB and A dash P dash B, what is APB? APB. APB. This is the angle. This is actually the angle of incidence. And A dash. This is actually angle of reflection. These are also equal. Absolutely. These are also equal. So if these are equal, these triangles are also going to be similar. Then you are going to again write down the proportionalities of sides. Please quickly see. B dash A dash, B dash A dash upon BA is equals to B dash P upon BP, right? Now you have got two equations. First is this, which is B dash A dash divided by BA is equals to B dash F upon FP. So this is your first equation. And this is your second equation. and if you'll closely see, their left hand sides are equal, so we can equate their right hand sides as well. So B dash F will get equate to B dash P upon BP, and that's the last part of your derivation, dosto. After this, you will be able to get to your formula. Just substitute the value of B dash P and FP. Right, quite boring derivation because lots of elementary school level maths, right? But still, this is the only way you will have to do it. No other way. No other way. Bhai, yeah, this is an English medium channel, my dear friend. Chalo, quickly, let's move. Quick. And from here you can derive that formula, that is 1 upon F equals to 1 by V plus 1 by U. All right. So now the thing is, similarly you can do more things from, like for example, let's also do the lens maker formula by yourself. Lens maker formula, which comes out to be 1 upon F equals to 1 upon V minus 1 upon U. First is this, I mean important for basic calculations, and next is refraction at surfaces, refraction at curved, at spherical surfaces. And the formula for this one is, this is refractive index, mu2 upon V minus mu1 upon U equals to mu2 minus mu1 upon R. So please remember this formula also. All right. Is it clear? Is it clear? We'll use these formulas when we are going to talk about when we are going to talk about optical instruments also, right? When we are going to talk about optical instruments also. So let's start with simple microscope. Then we'll cover each and everything, all of those TIR and all of those topics through our questions. So we are not going to leave those. We are going to solve those through objective and theoretical questions. Now please understand, why do we require optical instruments? Get this concept clear. If you'll get it, if you'll understand it now here the concept work. Initially what we were seeing that similar triangles, all of those all maths was coming in. This is actually something which you can actually understand. This is an unaided eye. This is called as unaided eye. If you are seeing an object with an unaided eye, the angle that is angle which is subtended at an eye is actually known as angle of, normally that this thing is known as visual angle with instrument and maximum visual angle for unaided eye. Why it is called as maximum visual angle? The reason is that there is a condition. You cannot actually make this object closer than the near point, right? After that we will not be able to actually clearly see objects. So this is the maximum, this is the minimum distance, minimum separation between an unaided eye and an object, right? So alpha can be actually written as H upon D. And please remember, these angles are small, that's why we are not writing it as tan or anything like that, right? Now if you are going to use a convex lens, so using a convex lens, what will it do? First of all, you will have to make an erect image. So for that you will place the object between focus and the optical center. So it will create an enlarged image, and now we are going to write beta over here. Please understand, when we are going to write this beta, now this beta will have a value as H upon U, and we'll write it with a negative sign. Obviously, you can write this thing also D with a negative sign. No worries. We have got negative sign over here. That's why I'm telling you. So beta can be written as H upon U. So magnifying power, this is the most basic concept. What is magnifying power? Magnifying power is the visual angle at instrument divided by maximum visual angle at unaided eye, right? So magnifying power will be H upon minus U, and this was H upon minus D. So this comes out to be D by U. That means for U, magnifying power will be D upon U. This is for a simple microscope. First of all, start to remember this. Why? Because when you are going to talk about compound microscope, there will be no difference, but now we are going to use two microscopes, two simple microscopes, right? So first of all, this is very important to understand that we have used a formula that is D by U. Now we have got two different cases over here. What are the two different cases? Two different cases are when the image is formed at infinity. When image is formed at infinity, this particular case is actually known as relaxed eye. Relaxed eye means that when image is obtained at infinity, there is minimum strain on our eyes. There is minimum strain. And when is going to be the maximum strain? When image is formed at the minimum distance for clear vision. Is that clear? Quickly tell me in the chat box, is it all good? Quick. Right? So these are the two specific cases that we are going to talk about when image is formed at the minimum distance. That means when you are going to talk about, for this particular case, this object, when this object will be at focus, its image will be formed at infinity. So when U will be actually equals to focus, that will be a case for minimum strain, or what you can say a relaxed eye position, right? When U will be actually equals to F. So this means that we can actually write the magnifying power for this one as, this one will be D divided by F. Can you please write down in the chat box if everything's clear? Quick. Clear? So I'll explain the sign convention. See, there is nothing difficult about sign convention. Just imagine that you have got, just imagine this to be the origin. Anything that falls before this origin point, mark it as negative. So this U will be negative, this V will be negative, and that's what we have done in these formulas. That's why we have written minus U and minus D. Is it clear? Quickly tell me in the chat box. Quick. Done? And when you are going to talk about that the image, when image is formed at the minimum distance, what do you mean by that? So it means that V should be actually equals to minus D. V should be actually equals to minus D. So find what U is going to be for that. So you can use 1 upon focal length equals to 1 upon V minus 1 upon U. So 1 upon F equals plus 1 upon U equals to 1 upon, or simply what I'll say is 1 upon U equals to 1 upon V minus 1 upon F. And this one is going to be 1 upon D minus 1 upon F. So 1 upon U will be 1 by D plus 1 by F. So for this U, you are going to get the image at the minimum distance. Please quickly tell me if you have any doubt till this point, then we'll move on. Quick. Is everything good? Everything's clear, right? Also, because we have already used this sign of this sign that u will be negative now, so we'll write a positive sign, because we know that we have kept this u negative sign over here. So when we are going to put the value, we'll get magnifying power as d into 1 by d plus 1 by f. So you will get 1 plus d by f. So please remember the magnification for this particular thing, that is 1 plus d by f. Now let me know in the chat box if you have any doubt, because see, if you are able to understand, these two specific cases, again and again we are going to use the same thing. Please don't spam. Quickly write down in the chat box if everything's clear. Quick. 1 plus d by f. All good? Clear? See, this is the minimum magnifying power which we are using, and this is the maximum magnifying power that we can use. After this, when you are going to talk about a compound microscope, first of all, compound microscope is combination of two simple microscopes, in which this lens is called as objective lens, this lens is called as eyepiece lens. You have got an object over here at a certain distance u. First you enlarge this object using this objective lens, and this is your image, right? This is your image, which is a real image. Now this real image is acting as an object for the eyepiece lens, and again we are seeing an enlarged image at this point. So if you want to know the total magnification of the compound microscope, it will be the product of magnification produced by objective lens times magnification produced by eyepiece lens. Now let me explain how this is going to work. This will work in a way that, let's suppose you want that your final image, who is creating the final image? Eyepiece is creating the final image. You want the final image should be such that there must be minimum strain on our eyes, which means a normal adjustment. Is that clear? Which is the minimum power. So in that case, please understand, this was your V. I don't think if I've got written over here, this thing is known as doston VO, isn't it? If I want a case in which the final image should be at infinity, then this VO should be such that this distance is focal length. Are you getting it, what I'm trying to say? If UE is actually equals to FE, obviously with sign convention, if I'm going to get an image at the focus of this eyepiece, then the image that will be produced further by this eyepiece will be at infinity, which will be, see, that's what I was saying. If you understood simple microscope, compound microscope will be really easy. Now please tell me if you are facing a doubt in this one, when I'm saying that for the minimum magnification, minimum strain we are having this case. Are you having a doubt? Quick, tell me. Okay, let me explain it again. No worries. See here. No worries. Please see. Everything was clear at this point? Everything was clear at this point? Tell me. Everything was clear at this point? Are you comfortable? Yes, sir. If I'm going to actually move this object in this direction towards the focus, the image will be formed at infinity, and my eyes will have less strain. Is that clear? Right? And if I'll move this object towards this point, this will start to get magnified, and the maximum magnification is not determined by this distance, dosto. Maximum magnification is determined by this distance. the final image that you are seeing should be at a distance of d from your eyes, right? I mean, forget that you have got a lens over here. Your brain doesn't know lens. Your brain right now doesn't know that you have got lens in front of you. Your brain is creating an image. So the maximum magnification can be produced when this image will be at a distance of d from here. So that's why I have said that let's say that v is actually equals to minus d, and I found out what u is going to be. So this is the maximum magnification case, correct? And this is the minimum magnification case when image is at infinity. Now what I am saying is, what is the final image over here? Who is creating the final image? This thing is creating the final image. Eyepiece is creating the final image. So basically what a human eye is saying is, human eye has got to do nothing with this objective lens. Human eye is seeing this final image. So if you want to have the least strain on human eye, what you will do is you will try to make this image at infinity. So for making this image at infinity, the object for this lens should be at its focus. That's what I am saying. Is that clear now? If the object will be at focus for this eyepiece, it will create an image at infinity. Khatam, right? Next case, if you will ask me, sir, what is going to be the case for maximum strain, maximum power, then I will say that this thing should be at a d distance from this eye. All right, clear? Okay, good. Your concept is now getting cleared. Now please understand how we are going to write it down. So this is your normal formula, lens maker formula, 1 by VE eyepiece, 1 by UE, 1 by FE, right? We are saying, see, we are saying that the this is, by the way, this is for eyepiece, na? We are not talking about objective. This is for eyepiece. Now we are saying कि final image should be at infinity, because we started our point like this. So UE must be FE. So we have done nothing. Now you have understood. Now all of you now know this, that okay sir, if UE will be equals to FE, we can write it down. So magnifying power will be, magnifying power was initially, it was magnification due to objective lens and magnification due to eyepiece, right? So that means this is going to be VO by UO. Sir, very simple thing. Magnification of any lens can be written as V by U of any lens. So VO by UO, and for this eyepiece, all we have written is D by FE, because that's what we derived in our previous case. This D by U, and this D by U should be, this U should be FE. So finally the formula turns out to be V0 by U0 D by FE. So this is magnification of objective lens, and this is magnification of eyepiece. Tell me if you have any doubt, dosto. Quick. Other than this, now V0 upon U0, or we have just converted this V0. We have just converted this 1 upon V0 minus 1 upon U0 into 1 upon F0. We have just converted these things, and that's how we have got this formula. After things, nothing is left. All you need to do is you need to remember these formulas. And length of tube, this is quite important. Length of tube is going to be VO plus FE. VO, this is VO, and this is, in this particular, this was basically UE. So length of tube is nothing but VO plus UE, and modulus of that VO plus UE, but in this case UE is actually equals to FE, that's why it is VO plus FE. Is it clear? Quick. Write down in the chat if you are getting it. Quickly write down. Can we move on to the next part? That is when you will have image at least distance. So see, again we are not changing, we are not doing anything with this. This is just magnification produced by objective lens. Now this is again 1 plus d by fe. So if you will remember the simple microscope cases, all the cases have been covered. This was the simple microscope. It was d by f, so we wrote d by f in this first case. D by f along with v naught by u naught. Alright. Maximum magnification was 1 plus d by f. So now over here maximum magnification is 1 plus d by f e. E basically means eyepiece. Come on, quickly write down in the chat box if now this is all good. Quick, quick, quick. No need to spam anything. Quickly. All good? Now it's all good? Clear. Good, good, good. Very good. So now in this case again see VO plus UE. You're going to simply write it as UE. No doubt about it. So one more derivation is completed, and similarly if you'll ask me now, you will get now astronomical telescope also. I mean conceptually there is no difference. So again over here also visual angle subtended at instrument divided by visual angle at unaided eye, it will become as minus h upon ue, h dash upon fo. This will become fo divided by ue. I don't have a diagram with me right now, but you can match the diagram for with the NCERT one. You will get everything. Again, if image is formed at infinity, 1 by v, instead of this you are going to write it as 1 by infinity. So you will know what u is. So ue will be equals to fe. Same thing. So magnifying power will come out to be as fo divided by fe. And length of tube, please remember length of tube in this one is actually fo plus fe. Clear? Everything's good? Done? Now let's move. And now I want you to solve some questions on this. Let's solve this one. Let's solve some numerical from compound microscope. Quick, dosto. Quick. Of the focal length of the objective and the eyepiece of the microscope are, so focal, you will have to solve it. Focal length of objective is 1 centimeter. Focal length of eyepiece is 2 centimeter respectively. If the tube length of the microscope is 10 centimeter, so it is 10 centimeter. This was, if you remember, this was VO plus UE. The magnification obtained by the microscope for most suitable viewing. Most suitable viewing basically means that the minimum magnification, which is actually nothing but D by F, if you remember. Chalo doston, quickly do it. See, this was the case I was talking about, D by F, minimum magnification. When image is at infinity, magnifying power is going to be D by F, right? And for tube length, for compound microscope, sorry, this was the case. H1 upon H, use any formula that you want, length of tube will be L equals to V naught by Fe. Come on, let's quickly do it. Timer, 90 seconds. Let's start. See, the thing is, you will have to अच्छा ठीक है चलो, first solve it, then I'll explain. See, now I'll explain it. All you need to do is you already know that the formula of magnification will be V naught by U naught into 1 plus D upon Fe. So first we need to find out what these V naught and U naught are going to be. Okay. So, and for that what you can actually do is, you can first we know that this thing can be written as 1 plus 25 centimeter divided by Fe. Fe was 2 centimeter, right? So first use the 1 upon Fe equals to 1 upon Ve minus 1 upon Ue. First find out this Ue. After finding out Ue, substitute it in this value. From here get to know what V naught is going to be. From this V naught, again use Lenz's formula, 1 by V naught minus 1 by U naught is equals to 1 by F naught. You know what F naught is, you know what V naught is, you can get to know what U naught is going to be. As soon as you know U naught, you can again come back to your magnification formula and you will get to your answer. Please write down in the chat boxes that is exactly what you have done. Again I am explaining length of tube. From length of tube, first of all you will have to find out what U is. After finding out UE, you can find it out V naught is going to be, then U naught, and then finally this formula. Quick. Any more doubts? All right. Let's check another question. A ray of light is incident normally on one face of an equilateral triangle. Okay. So let's say we have got an equilateral prism, something like this. A ray of light is incident normally on one of the faces of the equilateral triangle in this way, right? So if this is the case, this angle I will be 0 degree, angle R will be 0 degree, it will go undeviated. This is 90 degree, this is 60 degree, so this is going to be 30 degree. Is it all good? Quickly tell me in the chat box. So if I'm going to draw a normal over here, if I'm going to draw a normal at this point, this angle is going to be 60 degree, right? Now what they are saying? They are saying that when the prism is completely immersed in a transparent medium, it is observed that the emergent ray grazes the adjacent face. Find the refractive index of the medium. All right. What is the refractive index of glass? It is mu. So this one has got refractive index as mu. What's happening? Please quickly see. I told you that I'm going to explain the another topics using these questions. Ray comes, it goes undeviated through the glass. At this particular point, it retraces the boundary, right? That means angle of refraction is 90 degree. And let's suppose this is mu dash that we want to find out. Okay, let's use the Snell's law, normal Snell's law. We'll use mu into sine 60 is equals to mu dash into sine 90. So mu dash will be actually equals to mu root 3 by 2 times of mu. Tell me if you have any doubt. And this, if you are going to closely see, of course, I mean, you don't have to look for this root 3 by 2, but both mathematically and theoretically you can understand it, that if a ray is actually grazing the boundary, that means this is actually a critical angle. We'll cover all the remaining concepts from this point. This is the critical angle. At this angle of refraction is becoming 90°, right? Which also means that surely this is going to be a rarer medium and this is going to be a denser medium, because TIR can only takes place when a ray is going from a denser medium into a rarer medium. Is that all clear? Quickly write down in the chat box if this is all good. Correct answer would be root 3 by 2. दोस्तों quickly write down in the chat. Everything sorted? Can we move on? Chalo, let's move. Acha, again we have got a question form for passage. Let's read it out. A prism is an optical medium bounded by three refracting surfaces. A ray of light suffers successive refractions on passing through its two surfaces and deviates by a certain angle from its original path. The refractive index of the material of the prism is given by, this is actually nothing but mu equals to Snell's law. They have used Snell's law, A plus minimum deviation divided by 2 whole divided by sine of A by 2. Right? If the angle of incidence, on the second surface is greater than and called critical angle, the ray will not be refracted from the second. We know each and everything. Let's quickly move to the questions. Question says the critical angle for glass is θ1, that for water is θ2. The critical angle for glass water surface would be. Chalo, let's quickly do it. Array, okay, what was the answer for that one? What was the poll question? I think it was 1.25 if I remember the last one. D. Good. Quickly, let's start this question as poll. 90 seconds. Quick. The critical angle for glass is θ1 and for water is θ2. Find the critical angle for glass water surface. Quick. You don't need that passage for these things. Which theta? Which theta are you talking about? But if you already know the formulas now, you can easily do it. Answer. Quick. See, if they are saying that the critical angle for glass water would be, let's suppose that the critical angle for glass water is theta, right? For glass water, it is theta, right? So we are going to write something as sine theta is equals to mu g divided by mu w, and when you are going to talk about the critical angle for glass, so you are going to obviously talk about something like this, that let's suppose that you have got air on this side and you have got glass on the another side. So you'll write an equation in such a way that this is sine theta 1 times 1 equals to mu g into sine 90. Please see, whenever you have got a boundary like this, an interface, you have got a denser medium on this side and you have got a rarer medium on this side, and they say that okay, this is, let's suppose, normal, and we are getting an ray incident, something like this. This is the critical angle theta c, and this is r, which is 90 degree. So write down one equation for glass and air, write down one equation for water and air, and we have already written one equation for glass and water, and compare it. You easily get greater than theta 2. Simple 3 equations is required. Answer is going to be C. Very good. Surya, Rashik, Kevin, Swati, Saundarya. Good, good, good. Please understand these things, and also please remember, let's suppose that the refractive index of this one is mu d, this one is mu r. So you can also apply this, you can again rewrite the equation as sine theta c times mu r is equals to sine 90 into mu d. So sine theta c would be mu d upon mu r. Come on, let's move to the next question. When a ray of light of wavelength lambda and frequency mu is refracted into a denser medium, which changes? Which thing is changed? Quick, 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 quick. Which thing will change? When a ray of light of wavelength lambda and frequency mu, please always remember that frequency is actually a property of source. It is a property of source. So it will not change, and this is the reason that whenever you see a color of a light inside a swimming pool, the color does not changes, right? So if it has moved into a denser medium, definitely speed will go down, and because speed goes down, frequency is constant, so wavelength will also decrease, speed will also decrease, but mu will remain unchanged. So very easy. This is again from last year. Quick. Everything's fine? See, is everyone's comfortable with this answer? Let's move. Let's move to the next one. The critical angle for a ray of light passing from glass to water is minimum for? Come on. Just a second here. I think I've done one mistake. This is not from rarer to denser. Now this is from denser to rarer. Also here also. Please rewrite this equation. Other than this, everything is correct. Okay. Rewrite this equation. This is from denser to rarer. Now let's again come back over here. Bhai, please remember that whenever a ray of light will move from denser to rarer, it will move away from the normal. Na? It will move away from the normal, isn't it? So if this is the case, it will move away from the normal like this. So if you're going to increase the angle at a point, it will graze this path. So tell me which answer is going to be correct. Quick. The critical angle for a ray of light passing from is minimum for. Take 60 seconds. Quick. Just remember one thing, that mu is actually inversely proportional to lambda. Everyone's comfortable with that thing, na? Clear? Everything's fine? Yes, absolutely. Violet has the minimum wavelength. So it has got maximum mu. So it has got minimum critical angle. Minimum critical angle. Because the thing is, let's suppose it has got refractive index as mu and it has got refractive index as 1. Let's suppose that it is air. So that's what you will write over here as IC. So sine IC will be actually equals to 1 upon mu. Done? So D is going to be the correct answer. Okay, good. Utkarsh, Anil, Varsha, Shashwat, Kevin, everyone good. Tell me if you have any doubt. Can we move ahead? Acha, what about this particular thing? Can we solve this question? I have just now solved it. A ray of light is incident normally on the prism of refractive index √2 as shown in the figure. After it strikes face AC, it will. Let's start. 90 seconds. Quickly. So if it is striking perpendicular to the surface, angle of incidence would be 0, angle of refraction would be 0, this angle is 60 degree, this angle is 90 degree, this angle will be 30 degree, right? Acha, what they are asking first of all? Okay. By the way, if refractive index is √2, mu will be, IC will be sine inverse 1 by mu. That is 45 degrees. So 45 degree is the critical angle, dosto. And right now this angle is coming out to be 60 degree. So if angle of incidence is greater than the critical angle, it will not graze, it will actually fall back into the same medium. So it will fall back into the same medium, and this will be, again this will be 60 degree, this will be 30 degree, this was 60 degree, so this will be 90 degree, and it will pass something like this. Quickly tell me in the chat box, it will actually go straight, undeviated, refract and go out, undergo TIR. Undergo TIR should be the correct answer. D should be. Come on, quick chat. Any doubt at this point? D is correct. It will follow the law of reflection. Actually, very good. We have done some questions from this as well. All right. Chalo, now let's talk about wave optics and then we'll also start. By the way, yeah, we can start wave optics. Okay, let's start quickly. Quick. Let's start wave optics. In wave optics, again, some of the parts are going to be law based and theoretical, and you will also have some derivations, like for example as the starting of this chapter, that is the Huygens principle, wherever we are going to talk about the Huygens principle, right? At the very start, first try to understand what do we mean by a wavefront, and this is just an example of wavefront. I'll explain it. It is locus of points which oscillate in phase is called wavefront. Thus a wavefront is defined as the surface of constant phase. That means all of the particles in a wavefront will oscillate in phase, or they are in constant phase difference. The speed with which the wavefront moves outwards from the surface, it's called the speed of the wave. You already know what we are trying to talk about here is that these are nothing but these are plane wavefronts. These are plane wavefront. It all depends upon the sources of the light, right? It all depends upon the sources of the light. If you have got point source, then the wavefront are going to be spherical. Something like this, right? And what do we mean by this, that we have got a plane wavefront? This means that these light rays are coming from infinity. All right, is it all clear? If you have got a source something like this, then the wavefront is going to be a cylindrical wavefront. All right. So first is understand the definition of wavefront. Then we are going to talk about the Huygens principle. Huygens principle basically said, now these are some of the things that you will need to remember. Okay. Each point of the wavefront is the source of a secondary wave disturbance. That means, let's suppose this was the source of disturbance, and from this source we created a primary wavefront. So this is called a primary wavefront, and on this primary wavefront we have got different points which are acting as a secondary sources, right? So each point on the wavefront is the source of the secondary disturbance, and the wavelets emanating means which are spreading out, they are spreading out in the direction with the speed of the wave. These wavelets emanating from the wavefront are usually referred to as secondary wavelets. That means after this, these wavefronts are going to be called as secondary wavefront. And if we draw a common tangent to this spheres, we obtain a new position of the wavefront at the latter time. Is it all clear? Quickly tell me in the chat box, can you remember these things? Quick. Huygens principle and the definition of wavefront, right? Now see, this is actually important to you because using the Huygens principle, you can be asked to actually prove the law of reflection and refraction. So this is very important. Then again, in both of those laws, again you will have to use those similarity of triangles, right? Got it? Quick. So if you'll ask me now, this thing is very easy. That is refraction of plane wave and the reflection of plane wave. It is very easy, but I'll explain the diagram to you. See what this diagram basically says. First of all, how you are going to actually draw this diagram in exam. So this is the separation of the two medias, and these are the rays which are coming. Okay, these are the light waves, light rays, not waves, light rays. And you need to remember one fact over here, that these light rays are always perpendicular to wavefront, So this is a very important thing. So if you want to draw an incident wavefront, these are the two rays, you will draw an incident wavefront something like this, which is perpendicular to these rays. Now please try to understand, when we are drawing an angle of incidence over here, this angle of incidence, or what you can call as this angle of incidence, is between the incident wavefront and the plane, right? These are angles between the planes. Also you can, if this is I, this is going to be 90 minus I, this will be I, right? Now between these two rays, this point is activated a little before, and according to Huygens principle, each of these points will start to behave like secondary sources, right? They will start to behave as secondary sources. This is the second point you need to remember. The third point is, at this particular point, the wave will actually change the direction, because this is now new medium. This was, let's say this was medium 1, and when the light will travel into another medium, its speed will get decreased. V1 is less than V2. So in this medium, speed will get decreased. So let's suppose after time t, this wavefront, this particular point reaches to this point. Please try to understand what I'm saying. When this ray hit this point, the same point which was at same phase was over here, right? Now this will take certain time to reach to this point, and what is going to be that time? Let's suppose that time will be t. So this distance can be written as speed into time, so v1 into t. So this is the distance. Acha, in that same time, this point will cover a different distance, that is v2 into t. Why different distance? Because now you have got different speed over here. Write down in the chat if you have any doubt. Two things. So now theoretically what you should do is, you should draw an arc at a distance of v2 times t somewhere over here, and then draw a common tangent from this point to this point, and this is your refracted wavefront. And then the last step is going to be comparing these two triangles, this triangle and this triangle. That's it. Quick. We are going to talk about YDAC. We are going to solve YDAC. So don't worry about it. We are going to solve YDAC, so don't worry about it. Once again, the time in which this point will reach to this point is, let's say, t. In the same time, this point will cover a different distance, because it has got different speed now. All right. Now if you are going to ask me about the YDAC experiment, similarly you can draw the diagram for reflection of plane wave also. Now this is quite easy, because now they travel same distance, right? Again, very easy. After this we'll start YDAC experiment. This is incident ray, this is incident ray, and this is incident wavefront. So this is angle of incidence. This is angle of incidence. And right now, draw angle of reflection as different. Don't use law of reflection. That's what we need to prove. Okay. So now what we are saying is, again, let's suppose this point got activated a little sooner, right? Now in how much time this point will take? So let's say this will take actually some time t. So this distance will be v times t. Is that clear? In the same time, this point will actually move somewhere over here. So mark a distance. This should be v times t. Write down in the chat if you are understanding what I'm talking about. Quick. Is it clear? The only difference is now in this is going to be the same distance. So we have marked the same distance over here. And in the same time, it reached this point. So now draw a common tangent. That's it. So this is called as reflected wavefront. Clear? Done? And then again you have got two triangles. These are the two triangles. Again compare them, you will get your answer. That is I is equals to R. Fine. Let's move now. Let's first talk about interference, then we'll talk about YDAC, then diffraction, then we'll move to another topic. Good. Now the thing is, first of all, what do we mean by interference? Interference basically means, let's suppose at a single point, two light waves are traveling, having intensity I1 and intensity I2. And they are going to actually superimpose each other at a particular point. And that at point you are going to write down the net intensity. And the formula for that net intensity is this. The general formula is this. Please understand. This is the general formula. That is I1 plus I2 plus 2 under root I1, I2 and cos phi, where phi is the phase difference between them, between these two. Right? Also remember that intensity is directly proportional to the square of amplitude. Intensity is directly proportional to the square of amplitude. So if someone says to you, find out the maximum and minimum intensity, first of all, let's find it out. What do we mean by maximum and minimum intensity? Maximum intensity would mean we are talking about a specific case in which cos phi is giving you maximum value, which should be cos phi should be actually plus 1. Now you know what are those values going to be. Is that clear? Like 0, 2 pi, 4 pi. Is it clear? So it's going to be 2 and pi, right? So at cos phi equals to plus 1, I max can be written as I1 plus I2 plus 2 under root I1 under root I2. So this thing can be written as under root of I1 plus under root of I2 whole square. That's how we got this I max as under root I1 plus under root I2 whole square. Now if you are going to talk about the minimum thing, that means the minimum intensity. Minimum intensity will occur when cos phi will give you value as minus 1. That is phi equals to 2n plus 2n minus 1 pi by 2. Please write down in the chat box if everything's clear. Quick. So this is going to be under root I1 minus under root I2. Alright. We were talking about these problems. Sometimes what happens, they give you the ratio of I1 and I2. So I max to I minimum will become under root of I1 by I2 plus 1 divided by under root of I1 by I2 minus 1 and square of this. So if they give you the ratio of I1 upon I2, you can use this thing. let's say they gave you the ratio as K. Done? Clear? And sometimes they also tell you that the sources are coherent. So in that case, I1 and I2 both are going to be same, which will become as I0, right? So please also remember that in a specific case when I1 and I2 are same, when I1 and I2 are same, which is, let's say, which is equals to I0, this will become 2 times of I0, so that will be just, the net intensity will be 4 I0. The maximum intensity will be 4 I0 and minimum intensity will be, net minimum intensity will be 0. So these are the cases for your YDAC that we are going to talk about, isn't it? That's why we see that for all the bright fringes, the maximum, for bright fringes, the intensity is 4I, and for the dark fringes, the intensity is 0. Is it clear? Quickly tell me in the chat box if everything's fine. Done? Can I move on from interference? So I've explained in interference for a general formula. For specific formula, especially for YDAC, you are going to use this formula. Because what happens in YDAC, we'll see to it. Let's check. See what happens with YDAC experiment is, we have got two slits over here. We have got a single source. So we have got a single source. And then we have got two slits over here. So these two slits acts as a perfect coherent sources. We cannot do something like we have got two bulbs over here and we can expect that they will be in phase. They will never be in phase, right? I mean, sometimes they might be, and then they'll soon run out of phase. So we have got a single source over here, and then we have got two slits. These two slits behave as coherent sources. What do you mean by coherent sources? Sources in which their frequencies are same, wavelengths are same, and most importantly, their phase difference is either 0 or it is constant. Now the thing is, what is happening at this point? At this point, interference is happening. At this point, interference is happening. All right, clear? We'll do some questions also, don't worry, we'll do some questions also. First, let me explain the concept, na? Then only we can do some questions. So at that point, two things can happen. Actually, three things can happen. Either we can have a maxima. Maxima means bright fringe. Bright fringe basically means that the net intensity is going to be, which will be maximum, it will be 4I, 4I0, or it will be minima, which will be a dark fringe, and minimum intensity is going to be, the net intensity is going to be 0. And these are also known as constructive interference and destructive interference. Now the thing is, we could derive the formulas, we could derive the all the formulas over here, but that's again not in course. So you will only you are expected to only learn those formulas, right? Although we have successfully done it. I mean, after this we just have to write 2 or 3 things, like we'll just use some trigono over here and we'll be able to derive it, but we don't need to do it now. Now what we can actually do is, we can remember that the distance of the nth bright fringe from the central bright fringe is this. That is n times of beta, where beta is the fringe width. So this thing is actually known as fringe width, that is lambda capital D by small d. Please remember this formula, this is very important. This is known as fringe width. What do you mean by fringe width? The distance between two successive maximas or minimas, right? So lambda d by small d, and if you want to find out the position of any maxima, n lambda capital D by small d will do it. And this one is the distance of mth dark fringe from central. This is going to be 2m minus 1 beta by 2. Okay, so please remember it from form of beta also. It will be easier for you to remember. Other than this, this will also work. Everything's clear? Done? Remember, what do you mean by diffraction? What is the difference between a diffraction and refraction? Although not much, but over here we'll have a single slit. Most importantly, over at this point, the central maxima will have maximum intensity. In YDAC, generally we saw that the intensities of all the maximas is constant. It's not like you're going to have the maximum, if you're going to have the 4i naught intensity at the central maxima, then it will decrease. It was not like that. Over here it will be maximum intensity will be at central maxima, and soon you will have the intensities will keep on decreasing as you're going to move away from the central maxima, right? So this is very important. And again, the formulas over here, the thing is, for the minima, the formula becomes n lambda by d by a, where d is of course D is this thing, capital D is this thing, A was the size of this slit, and in previous examples small d was the separation between the two slits. Alright, so this is for minima. Please remember the formula: linear width of the central maxima, which will be nothing but 2 times of d lambda by d. Why we are talking about something like this? Because at the central maxima we have got two minimas. So let's find out the separation between those two. So that is going to be 2d lambda by a, right? And then angular width is actually, by the way, we are going to also define angular width in our in the YDAC also. If you are going to talk about angular width at this particular point, it will be beta by capital D. That will be just lambda by small d. Now we are good to go for some numericals. Let's solve some numericals. Like for example is this one. YDAC, easy question, not at all difficult. Let's do it. Quick. In a YDAC experiment, the slits are separated by 0.30 millimeter, 0.30 millimeter, and the screen is kept at 1.5 meter away, 1.5 meter away. The wavelength of light used is 600 nanometer. So this thing can be written as 0.30 into 10 to the power minus 3 meter. This thing is good. This thing is 600 into 10 to the power minus 9 meter. Quickly solve it down, dosto. Calculate the distance between the central fringe and the fourth dark fringe. All right. So you have to do nothing, but you just have to find out the Y4 for the dark fringe. Just apply the formula. That's it. That we have just saw over here. This one. Quickly answer in chat box. You have got each and everything. Quick. Two n minus 1 divided by 2 lambda capital D by small d. Find out the answer. Two n minus 1 lambda capital D by small d, you know each and everything. This will become 8 minus 1. Lambda is actually 600 nanometers. D is 1.5 and small d is 0.30 into 10 to the power minus 3, right? What I can actually do is I can these are 2 points, so this will be 10 to the power 5 right? I can cancel out this, I can write it down 20. This thing will become 3. This is 7, so it's around 2.1 something. Can you please check what's the answer? Quick, quick, quick. What's the answer? What are answer we getting? There's also 1 2 in the bottom. Sorry, that's what we forgot. There's also 1 2 over here. That's it. Quickly find it out. Moving to the next one. In YDAC experiment, interference pattern is not observed when the two coherent sources are infinitely close to each other. The fringe width is proportional to the separation between the two sources. All right, let's do it quickly. Acha, by the way, this was from which thing? I also don't remember. Quickly, let's solve this particular one. Starting the poll, 90 seconds. In YDAC experiment, the interference pattern is not observed when two coherent sources are infinitely close to each other. Well, this is true because the thing is, fringe width is actually lambda capital D by small d, right? So if D is going to decrease, you are not going to actually find the YDAC experiment. So this is absolutely true. Fringe width is proportional to the, it is not proportional, it is actually inversely proportional to D. So reason is correct, but sorry, assertion is correct, but reason is false. Is it good? Quickly, C option is correct. I can move, right? Chalo, let's move on to the next one. So the correct answer for this, that is C. Okay, poll is, stop poll, C. 42.8. Kevin, good. Aditya, Ishan, do you have any doubt? I mean, other students who are not able to get it, do you have any doubt? Let's look at this one. A Young's double slit experiment setup is kept in a medium of refractive index 4/3. So what happens if we keep a YDAC experiment in another medium? What will happen? Are they talking about, obviously wavelength will change, a little tip, right? Wavelength will change, new wavelength will become lambda upon mu. Just this is the thing. Other than that, question is quite easy. They are saying which maximum in this case will coincide with the sixth maximum obtained if the medium is replaced by air. So you have got like two things. One is air, right? Maximum, if the which maximum is in this case is coincide with the sixth maxima. So the sixth maxima is of air, right? So if it is maxima, let me write it something like this. Sixth maxima in air, and we have to find out which positions maxima it is coinciding in that medium which has got refractive index as 4/3. Formula is n lambda capital D by small d. Is that correct? So I'm going to write 6 lambda capital D by small d is equals to this is in that medium, so it will become n lambda by 4/3 capital D by small d, because everything else will remain same. I think 8th is going to be the answer. What you guys say? 8th. Quickly tell me in the chat box if everything's clear with this one. Quick, quick, quick. Done? Two things. One is if you are going to, acha, they might also ask a question. I am recollecting from my memory that they have also asked a question something like, if we dip a YDAC arrangement into a medium of having refractive index as mu, what will happen to the fringe width? You tell me what will happen to the fringe width. The correct, acha, I not started the poll for this one. What will happen to the fringe width? Fringe width is actually lambda capital D by small d. So capital D is the distance of screen from the slits, and small d is the separation of the slits. So beta is just dependent on wavelength. So wavelength becomes lambda by mu. I mean lambda dash becomes lambda by mu, right? So beta will actually become, beta dash will actually become beta by mu. Is that clear? It will get decreased. Fringe width will get decreased. Okay, let's quickly move on to the next one. I have also explained what do we mean by angular fringe width and what do we mean by fringe width. This is a question for all of you. Let's quickly do it. Fringe width decreases, that's absolutely correct. Quick, dosto. In Young's double slit experiment, the screen is moved away from the plane of the slits. Okay, so screen is moved away, which means that capital D is increasing. So we know that beta is written as lambda capital D by small d. So beta will increase here, है ना? Beta will increase, that's for sure. So fringe width will increase, second will increase, but angular fringe width is actually, just now I told you angular fringe width is actually beta by d. Is beta by d, and beta by d is actually lambda by d. So please understand that this is the angular fringe width which will not change, right? We are not changing anything with wavelength. So it should be actually remains constant and what happens, and increases, remains constant and increases. So option C should be correct. What about you guys? What do you say? Is it clear? Done? Can we move on? So now dosto, I think we should start dual nature of radiation and matter, right? Because then we'll enter into modern physics completely. Let's talk about dual nature of radiation and matter, and trust me, almost we have it's like more than 8 hours, but still this chapter is very good, very easy. Why I'm saying very easy? Because if you'll catch the concept of this chapter, you'll be able to solve each and every question. All right, we don't need any breaks. No more breaks. No more breaks. Acha, in dual nature, first of all, we'll talk about electron emission. This is the most important thing. We are going to talk about the electron emission. Let's suppose that we have got a metallic surface over here. We have got a metallic surface, something like this. Right? And some electromagnetic radiation is falling on it. Acha, by the way, I am not talking about all of those Hertz experiment or Leonard's experiment. I'm not going to explain all of those things. We need to do only two things. One is photoelectric effect. The another is our what we can say Einstein's equation, right? Those are the two most important things. Other than that, if you have time, please do it by yourself. But we are going to talk about the two topics from which most of the questions are framed. Now over here, what we actually see is that metals have got free electrons on the surfaces. First of all, not all of these electrons are located at the same type of places. Some might be towards the interior of the surface, some might be on the surface, right? So these, we have got electrons on the surface, and when you throw some electromagnetic radiation, by the way, the thing is, when you are going to study, like for example, is whenever you are going to study any theory, do two things. Talk about what what were the different phenomena that theory was able to explain. Second, what was the failure of that theory. For example, as Huygens principle was able to explain the reflection of light, refraction of light, but it was not able to explain the photoelectric emission, right? Because that's why we are talking about, now we are talking about that light actually acts as a behaves like a material, photon. Okay? Then in this same chapter, then we are going to talk about the dual nature, de Broglie's hypothesis. We are going to say a wavelength has also got wavelength, that is lambda, and also momentum, which is actually a characteristic property of particles, right? So that is what it is. So always remember, whenever you are going to talk about a theory, do both the things. So when an energy is going to fall into it, energy in form of electromagnetic radiation, a part of that energy, which from which we can also write Einstein's equation, but please remember, a part of it will be required, or you can understand it in this way, that a minimum amount of energy is required so that electrons can get ejected. So the main obstruction for electron emission is energy, not intensity, not what we can say, nothing but energy. So energy is required, right? So there, that's why we define something that is called as work function. Work function, which generally is represented in electron volts. So let's suppose a certain material has got a work function of 5 electron volts. So that means minimum 5 electron volt of energy is required so that the electrons can be ejected from it. Now if let's suppose you are just applying 3 electron volt and you are keep on increasing any other physical quantity like intensity of the radiation or anything other than energy, electron emission will not take place. No matter, so this is a very spontaneous phenomena. It's not something like that you keep on giving energy and at a certain point it will eject. It's not like that. It's quite spontaneous, right? So a certain minimum amount of energy is required to give an electron to pull it from the surface of the metal. This minimum energy required by an electron to escape from the metal surface is called the work function of the metal, right? Got it? So this was the first thing. So it means that if what will happen, let's suppose, what will happen if I'll increase the intensity. First of all, what is intensity? Intensity basically means, will generally be defined intensity as power divided by area. We are right now we are saying that let's suppose we have got 2 bulbs over here. I am giving you a very layman example. Okay? Let's suppose we have got 2 bulbs over here. Now suddenly we have increased one more bulb. So what are we trying to do? We are basically trying to increase the intensity of the light, right? But the energy which is coming out of that bulb is not greater than work functions. So there will be no photoelectric emission. First condition is the energy must be greater than the work function. Then next, if you are going to actually increase the intensity, more number of electrons are going to get exposed, more number of electrons are going to get exposed to that energy, and more number of electrons will get ejected out. And that's why we draw a graph like this, that intensity of light is directly proportional to photocurrent, but only when the energy is greater than the work function at the first place. Got it? Done? So this is a very important graph from NCERT, the number of photoelectrons emitted per second, which is actually known as photocurrent. So this thing is actually known as photocurrent. This thing is actually known as photocurrent. Can you please confirm in the chat everything's clear with this point? Moving on to the next graph. All of these graphs are really important and all are from NCERT. Okay? Let's move. Now let's suppose we are talking about something that is called as these are, for this I'll have to actually explain you the experiment. But still, we have got over here as collector plate, retarding potential and photocurrent. What are these things? What we are basically trying to say is, let's suppose that we have got a plate over here, right? This is our target metal, and I've got another plate over here, and this is actually, it is inside an evacuated glass tube. Also over here I've got a slight window so that electromagnetic radiation can come in, and then it is connected with batteries so that we can apply different potentials over here, right? All of those arrangement, not really focusing on this, explaining you the concept so that you can solve the problems. Got it? Now please understand this thing. See what will happen if you are going to actually throw the radiation. First condition is the energy must be greater than the what? Than the work function. Let's suppose it is greater than the work function. Then electrons came out. The number of electrons that are going to came out depends on the intensity, right? So if you have got photocurrent over here and you have got collector plate potential over here, what is that collector plate? So this is this collector plate. So because these are electron, let's supply positive potential over here, right? When you are going to increase this positive potential, more and more number of ejected electrons are going to actually come towards this collector plate, and obviously we have got a galvanometer over here and we'll see that the current reading will start, right? But after a certain point it will saturate because all of the current, all of the electrons will be in the circuit. So that's why it is getting saturated. And why are we seeing I3 is greater than I2 and greater than I1? Because these are intensities. I3 was the largest intensity, that's what we have written over here, then I2, then I1. So it has got more photocurrent, right? But because all of them had same energies, the source was same source, that's why all of them has same stopping potential. Now the next thing comes is what is actually stopping potential. Now what we do is we actually reverse the experiment. We say now we are not trying to catch these electrons. We got some incident radiation over here, electrons ejected out. Now we are trying to stop these electrons. We don't want these electrons to complete the circuit. So for that we are going to actually apply now opposite potential. So we are going to apply a positive potential in this side. That's why we have got negative axis. So this is that stopping potential at which all the electrons are going to get stopped. That's why at this potential there is no photocurrent. Is that clear? Now again, please try to understand. Please try to understand. Now let me break the ice and let me write the Einstein's equation, because with that equation now every concept will get cleared. Einstein wrote a very beautiful equation. He said that okay, the energy that is falling from the radiation will be used in two ways. One is to overcoming the work function, and the remaining energy will present in the form of kinetic energy of electrons. Are you getting it? Bhai, those electrons will have got kinetic energy in a range. Some will have zero. Are you getting it, right? So let's suppose that this is the surface. Some of the electrons are quite beneath the surface. So for that particular electron, all the energy got used up to actually make that electron come out of the surface. So that particular electron has got zero kinetic energy. But some of the electrons were at the surface. So those electrons will have the maximum kinetic energy. So this is an Einstein's equation. So if you want to find out the kinetic energy, what you are going to do is you are going to write maximum kinetic energy is actually equals to E minus phi. So if incident radiation is same, if you are throwing a same incident radiation from a same source, E will be same, and that's why stopping potential will be same. Why stopping potential will be same? Because I mean, who are we stopping? Those moving electrons, right? So they have got same kinetic energy. So that's why all of these have same stopping potential. I'll take some doubts if you have any. Quickly, quick. I'll take some doubts. If you have any doubts, please write down in the chat box. Quickly. No more doubts? Everything's clear? Now again, let's come back to this equation. So this was the equation. E can be written as H into nu work function can be written as h into nu naught plus maximum kinetic energy. This nu naught is called as threshold frequency. This thing is called as threshold frequency. Also, we can rewrite this thing as hc by lambda equals to hc by lambda naught plus maximum kinetic energy. You can also rewrite kinetic energy in another forms as well. Now this thing will be threshold wavelength. So threshold wavelength is the maximum wavelength and threshold frequency is the minimum frequency. Got it? Quick. Let me know if you have any doubt. So kinetic energy's formula is going to be h nu minus nu naught. Now we can look for some questions from this as well. Quick. The quantum nature of light explains the observations on photoelectric effects as there is a minimum frequency of incident radiation below which no electrons are emitted. So, bhai, this is absolutely correct na? There is a minimum frequency of incident radiation below which no electrons are emitted. The maximum kinetic energy of photoelectron depends only on the frequency of the incident radiation. Well, it does depends upon the frequency of the incident radiation, but it also depends upon the work function. If work function is less, kinetic energy will be more, right? Got it? When the metal surface is illuminated, electrons are ejected from the surface after some time. So please remember, I have explained this thing that this process is instantaneous. So this point is wrong. The photoelectric current is independent of the intensity of the radiation. Well, photoelectric current is purely dependent on the intensity of it, right? So the correct answer is going to be option A. Tell me if you have any doubt. Quick. Any doubts? See, you are going to get equations, you are going to get questions like write photoelectric equation of Einstein's, right? Acha, let's see this one. Two beams A and B whose photon energies are 3.3 electron volt and 11.3 electron volt respectively illuminate a metallic surface of work function 2.3 electron volt successively. The ratio of maximum speed of electrons emitted due to the beam A to that of beam B is. Come on, quick. Chat, write down the answer. So for beam A, whose photon energies are 3.3 electron volt, right? So we are going to use a basic thing that E equals to work function plus maximum kinetic energy. That means maximum kinetic energy will be written as E minus 5. So E minus 5 is going to be dosto 3.3 minus 2.3, which is actually nothing but 1. So half mv square is actually equals to 1 electron volt. So this is for A. Is it all clear? This is for A. Next is for let's write it for B. So for B we are going to write maximum kinetic energy for B is going to be 11.3 minus 2.3. So it is going to be 9 dosto. So that means this one is going to be half m v. By the way, this is VA, this is VB. This is going to be 9. So let's take a ratio of them. This will get cancelled out. So VA by VB will be actually equals to 1:3. So 1:3 should be the answer. Option C. Quick. All good? Can we move on? Let's solve this question. The waves associated with a moving electron, hopefully no poles are working now. The waves associated with a moving electron and a moving proton have the same wavelength. It implies they have the, tell me. Quick, 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 dosto, this is quite easy. 60 seconds. Waves have got same wavelength, right? The waves associated with a moving electron and a moving proton. If you remember, lambda is actually equals to h by p. And they are saying that lambda is same. So if wavelength is same of two moving electron and proton, it means that their momentum is also going to be same, na? So their momentum is also going to be same. Simple de Broglie's wavelength. Let me know, dosto, if you have any doubt. Can we move? Next question. Acha, last one will have A as answer. Very, very good. Priyesh, Harima, Nishan. Good, good, good. Next one. Acha, theek hai. Assertion says in photoelectric effect, the kinetic energy of the emitted photoelectrons increases with increase in intensity. What do you have to say about this? Come on. What do you have to say about this? Quick. No, MCQ doesn't require any steps. Just solve your answer, write down the answer, that's it. I took a break, na? I took a break. I'm quite recharged. Chalo, quickly tell me, bhai, kinetic energy does not depend upon the intensity. Kinetic energy depends upon the what? Depends upon what? Kinetic energy depends upon incident radiation, right? If you are going to keep work function as constant, isn't it? So, first assertion is false. Photoelectric current depends upon the wavelength of the incident radiation. Think about it. Photoelectric current depends upon the intensity of the radiation. Quickly, doston, tell me, see, that I actually told you that you just need to learn the graphs and Einstein's equation. Most of the questions are from these two topics only. And we saw one question from de Broglie's hypothesis. Is that clear? Got it? Quick. But we don't have an option that both are false, right? So please select the correct option for this one. Quickly. D. D is going to be correct. Reason is false. Assertion B. Yeah, D is going to be correct. Absolutely. D is going to be correct. We have got the option. Fine. Alright, dosto. So we have almost covered this thing also. One more question from graph. Which of the following graphs correctly represents the variation of a particle momentum associated with de Broglie wavelength? So we know that de Broglie wavelength is inversely proportional to momentum. We have got H over there. So the graph is going to be something like this. Again, D. Done? Now let's talk about atoms and nuclei. Now let's talk about atoms and nuclei so that we can finish our we can finish modern physics. Almost everything is finished in modern physics. And then see, I'll do one thing. If you will think that okay sir, let's have some more questions on semiconductors, on some more questions on these things, we have got still 2 days, 19th and 20th. So I'll come back, not live but on recorded sessions, because now obviously I can't expect you to again join a live session, right? So now study by yourself. I'll try to actually come up with some of the videos on derivation, some of the videos on more PYQs, stuff like that, right? Got it? My name is Subrat Sharma. Now let's quickly start atoms and nuclei. See, in this chapter, start with, if you're going to talk about the very most important thing, start with the Rutherford's experiment, because it is quite important, right? Rutherford experiment is basically when you have got beams of alpha particles which are bombarded on a thin gold foil, right? And then we see that how they get scattered, right? So what we observed, there is a very small number of particles which are scattering backwards, like 1 in 8,000. And then we have got we have got over here as a detector microscope which will detect the number of particles which are actually which are deflecting at certain angles, and then you will also draw that graph of angle and the number of particles, right? So also remember that graph. So basically we all know, you must have studied Rutherford's in the chemistry part also. In physics mainly we are going to talk about things like impact parameter, and we'll see some more questions, but generally Rutherford were able to explain that almost entire volume of atom is actually empty. What he was unable to explain was the stability of an atom, right? He was not able to explain why does actually electron is, if an electron is revolving around an nucleus, why it is still stable. So these are some of the observation. Most of the alpha particles went straight through the gold foil and produces flashes on the screen. Few particles collided with the atoms of the foil, which have scattered or deflected through considerably large angles. Few particles even turned back towards the source itself. The entire positive charge and almost whole mass of the atom is concentrated in small center called nucleus. The electrons could not deflected the path of alpha particle, that is electrons are very light. Electrons revolve around a nucleus circular orbit, around nucleus in circular orbit, but he was not able to explain if electrons are revolving, that means it's an accelerating charge. So it means that it must be throwing off electromagnetic radiation, so it should eventually fall into nucleus, right? He was not able to explain that. So failure of Rutherford model, he couldn't explain the stability of atom, it couldn't explain the discrete nature of hydrogen spectra. All right, done. Hopefully everything's clear till this point. After this, next important thing that we have, we are going to talk about some Rutherford quotients, but still let's move to Bohr model for now. Now Bohr assumed that, first of all, there was an assumption that an electron in an atom moves in a circular orbit around the nucleus under the influence of a Coulomb's force, right? So let's suppose that if you have got a nucleus over here having a charge Ze and an electron over here. So an electron is moving with a electrostatics force. That electrostatics force is going to be K KZE square divided by, this is going to be the radius of the orbit, is equals to, and this will provide the necessary centripetal force, mv square by rn. So please remember, this is the one of the first few equations from which we derive all the other formulas. Like for example, as you can derive from here, you can derive the formula for rn, right? You can derive the formula for v. So this was the first assumption that the Bohr assumed. Next is, or you can say the postulates also. The next postulate was only those orbits are possible in which the orbital angular momentum is equals to the nh upon 2 pi, the integral multiple of h upon 2 pi. So this is the second equation. So please remember, mvr equals to nh upon 2 pi, and the first equation, mv square by rn is equals to kze square by rn square. This was the second equation. The electron moving in such allowed orbit does not radiate electromagnetic radiation. So that's how he was able to explain the stable orbits. All right. Moving on. Now you'll understand some of the formulas from this particular thing. So we used mvrn equals to nh upon 2 pi and mv square by rn equals to kze square by rn. So these two formulas, and using these two formulas we were able to get first this formula. I mean, it will be good if you will remember it in this way, that is 0.529 angstrom, right? So this thing can be also written as Rn, can be also written as n square times 0.529 angstrom. Come on, tell me in the chat box. Everything's clear? Quick. Next is the velocity of the revolving electron. So velocity of the revolving electron, that's what they have did. mvr, this is the angular momentum. mvr, by the way, let me check. I've written mvr. Yeah, mvr. So they have kept rn. This is nothing but this is rn. And then they have found out what velocity comes out to be. So velocity comes out to be E square divided by 2n h epsilon naught. Remember one formula, if they'll ask you to derive it, then you can derive the another formulas as well, right? But please remember these two are very, very important, because these are the postulates of the Bohr's, and after this you can derive each another thing. This is also very important, n square times 0.529 angstrom. All right, this is also very, very important. Got it? Then last is the energy. See, please remember one thing. When you are going to talk about the energy of an electron in the orbit, the total energy is actually equal, the magnitude is actually equals to the magnitude of kinetic energy. This is actually equals to the magnitude of potential energy divided by 2. We have seen these things before as well. This will be applied over here, and energy will be found by two things. One is kinetic energy, half mv square, and another is potential energy, right? Potential energy, we can also use that potential thing, potential into charge. Potential is k q by r, q is E, all of those things. After doing all of those things, this is the answer that you will get, minus 13.6 divided by n square, and of course this is for hydrogen-like atom. Got it? Done? Quick. So dosto, after this, although I mean, if you are going to closely see, this was energy was written as En was written as minus 13.6 divided by n square electron volt for hydrogen like atoms. So if n is equals to 1, it is going to be 13.6 minus 3.40 minus 1.51. These things it will be good if you'll remember it. If you haven't got these things yet, rely on the formula, right? Formula will help you. Nothing wrong with the formula. Got it? Done? And the spectral lines, all of those derivations are not going to come. So you only need to remember the formulas. Derivation is not in your course. So don't worry about how we are going to draw these spectral lines. Hopefully this is not going to come. That's what they have written in the syllabus also, right? So only the names and some of the basic things, please remember it. That will be more than sufficient. Like for example, as whenever the final state of the electron is first ground state, those series are called as Lyman series. Remember two things: for maximum wavelength and minimum wavelength. Remember these two formulas. And then n equals to 2 is Balmer series, n equal to 3 is Paschen series. Usually they are going to talk about these three only, but still these are also important. They are not going to tell you to write all of these things, as far as I know, because I've seen that official document of CBSE. All right. So now I think what we can do is, you can look for these questions, one or two questions. We can look for one or two questions, like for example, as the energy of an electron in the ground state of the hydrogen atom is minus 13.6, the kinetic energy and potential energy in the first excited state is going to be. Come on, do it. Come on. So if energy is actually in the ground state is actually minus 13.6, in the first excited state it's going to be minus 13.6 divided by 4. This is going to be the value of E2, and same value is going to be of kinetic energy also, just the positive part of it. Is that clear? And if you are going to talk about the potential energy, it will be negative times of twice of this energy. Write down the answer in the chat box. Quick, 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 quick. Are we getting the same answer? I mean, options are matching. Tell me, dosto, are options matching or not? Acha, they are not asking in the ground state, huh? So please don't get confused. Acha, this is 4 by the way. This is 4, sorry. This is 4. This will get divided by 2. So I think it will be, see, kinetic energy can't be negative. Hai na? So it will be C. It can't be negative. C option will be correct. Let's move. Electrons are ejected from the surface of the zinc when it is irradiated by a yellow light. Energy associated with a photon of yellow light is more than the work function of zinc. Think about it. Okay, so I mean it got over here. It was meant for dual nature, but still we can do it. Quickly solve this question, dosto. Electrons are ejected from the surface of the zinc from the surface of the zinc when it is irradiated by a yellow light, energy associated with a photon of yellow light is more than the work function of zinc. Is it correct? Absolutely. If it is electrons are getting ejected, that means the energy associated with the photon of yellow light will be greater than that of work function. So both A and R are true, and reason is also the correct explanation. A should be the correct answer, right? Moving on. Acha, please see, this is the thing I was talking about. If you'll remember the formula, if you'll even remember the formula that yes sir, Rn is actually equals to 0.529 times n square angstrom, then these questions are going to be quite easy, right? So that's why remembering formulas will actually help you to score those first 18 marks. Any more doubts? Poll answer for that particular question was, I think, option A. Okay, very good. Very good, everyone. Now, let me give you one more question. From alpha particle. We were meant to solve this question. An alpha particle is moving towards a gold nucleus. The impact parameter is maximum for the scattering angle of 180 degree. The impact parameter in an alpha particle scattering experiment does not depend upon the atomic number of the target nucleus. Solve it down. Acha, impact, you know, all know what impact parameter is, right? Let's suppose that this is the nucleus. And we are getting, this is the line. Although I think again, I believe that this is not in course. Let me check into the latest course, latest syllabus. Maybe it's not. I can't find impact parameter, but still they have just written Rutherford experiment. That's the problem. They've just written the Rutherford experiment, so we'll have to check. Anyway, write down your answer. Write down your answer. This is going to be the impact perimeter. You don't need to remember the formula also for solving this question. But if the scattering angle is 180 degree, right? So the impact parameter will be 0. Because if it is actually scattering something like this, getting repelled, so the D should be 0. The impact parameter in an alpha particle experiment does not depend upon the atomic, it does depend upon the atomic number. At least you should remember the formula this much, that it does depends upon the atomic. So both A and R are actually false. So option D is correct. Option D is correct. Okay, we have not started the poll for this one. Okay, no worries, D is absolutely correct. Okay, so see, now what I'm going to do is, please understand what I'm going to do is, I'm going to now take the two parts, that is one semiconductor and one for nuclei, as I'll upload it on this channel only, so you will have to check it by tomorrow. I'll upload some more videos, some more derivations, right? I'll try to keep them short. I mean to say, I'll not upload each and every derivations. I'll keep them short. I'll pick only, like for example, as 1 or 2 derivations from each chapter. Do those derivations. And as far as semiconductor is concerned, I'll get that to you as well, right? Got it? So that will be all for today. Thank you so much. All the very best. The best thing that you can do right now is improve your preparation. Don't worry about, sir, what's going to happen. I've got this much. I'm not getting this particular thing. I'm not getting this particular thing. Set up a plan. If you're facing a trouble in a particular topic, leave that for few time. Then again, come back, watch some YouTube videos, watch some classes, again come back to that topic after some time, and set up a plan, right? Don't do this thing like you're studying current electricity for now for some time, then you're starting another chapter. Don't do that. Got it? Everything's clear? So PYQs and revision, not just PYQ. I'll not suggest you to just do PYQ. PYQ and revision is also very important. All right. So now we'll meet tomorrow, and tomorrow we are going to talk about the rest of the topics. I'm not going to come live. We are going to I'm going to upload some videos in recorded form. Okay. All right. Bye bye. Thank you so much, everyone. Thank you. Good night and best of luck. Keep preparing. Bye. Bye, everyone.